The Project Gutenberg ebook of the first 6 books of the Elements of Euclid. This ebook is for the use of anyone anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. You may copy it, give it away or reuse it under the terms of the Project Gutenberg license included with this ebook or online at www.gutenberg.org. If you are not located in the United States, you will have to check the laws of the country where you are located before using this ebook. Title: The First 6 Books of the Elements of Euclid. Author: Euclid John Casey. Release date: April 14, 2007. Ebook number 21076. Most recently updated, July 18, 2022. Language: English. Credits: Joshua Hutchinson, Keith Edkins, and the online distributed proofreading team at https://www.pgdp.net. This file was produced from images from the Cornell University Library, Historical Mathematics Monographs Collection. Revised by Richard Tunsing. Start of the Project Gutenberg ebook. The first 6 books of the Elements of Euclid. Production note: Cornell University Library produced this volume to replace the irreparably deteriorated original. It was scanned using Xerox software and equipment at 600 dots per inch resolution and compressed prior to storage using CHIT Group 4 compression. The digital data were used to create Cornell's replacement volume on paper that meets the ANSI standard Z39.48-1984. The production of this volume was supported in part by the Commission on Preservation and Access and the Xerox Corporation. Digital file copyright by Cornell University Library 1991. Transcriber's note: the index has been regenerated to fit the pagination of this edition. Despite the author's stated hope that few misprints have escaped detection, there were several, which have here been corrected and noted at the end of the text. Cornell University Library _______________________ The Evan Wilhelm Evans Mathematical Seminary Library _______________________ The Gift of Lucy and Augustus Waite. The Elements of Euclid. Now ready _________________________ Price 3s. A treatise on elementary trigonometry, with numerous examples and questions for examination. Third edition, revised and enlarged, price 3s. 6d, cloth. A sequel to the first 6 books of the Elements of Euclid, containing an easy introduction to modern geometry, with numerous examples. Third edition, price 4s. 6d, or in 2 parts, each 2s. 6d. The Elements of Euclid, Books I6, and Propositions IXXI, of Book 11, together with an appendix on the cylinder, sphere, cone, and sea, with copious annotations and numerous exercises. Price 6s. A key to the exercises in the first 6 books of Casey's Elements of Euclid. Price 7s. 6d. A treatise on the analytical geometry of the point, line, circle, and conic sections, containing an account of its most recent extensions, with numerous examples. Price 8s. Dublin, Hodges, Figgis, and Co. London, Longmans and Co. The first 6 books of the Elements of Euclid, and Propositions IXXI. Of Book 11, and an appendix on the cylinder, sphere, cone, etc. with copious annotations and numerous exercises. By Johncasey, LLD, FRS, Fellow of the Royal University of Ireland, Member of Council, Royal Irish Academy, Member of the Mathematical Societies of London and France, and Professor of the Higher Mathematics and of Mathematical Physics in the Catholic University of Ireland. 3rd edition, revised and enlarged. Dublin, Hodges, Figgis, & Co., Grafton St. London, Longmans, Green, & Co. 1885. Dublin, printed at the University Press, by Ponsonby and Weldrick. Preface. This edition of the Elements of Euclid, undertaken at the request of the principals of some of the leading colleges and schools of Ireland, is intended to supply a want much felt by teachers at the present day, the production of a work which, while giving the unrivaled original in all its integrity, would also contain the modern conceptions and developments of the portion of geometry over which the elements extend. A cursory examination of the work will show that the editor has gone much further in this latter direction than any of his predecessors, for it will be found to contain, not only more actual matter than is given in any of theirs with which he is acquainted, but also much of a special character, which is not given, so far as he is aware, in any former work on the subject. The great extension of geometrical methods in recent times has made such a work a necessity for the student, to enable him not only to read with advantage, but even to understand those mathematical writings of modern times which require an accurate knowledge of elementary geometry, and to which it is in reality the best introduction. In compiling his work, the editor has received invaluable assistance from the late Reverend Professor Townsend, SFTCD. The book was rewritten and considerably altered in accordance with his suggestions, and to that distinguished geometer it is largely indebted for whatever merit it possesses. The questions for examination in the early part of the first book are intended as specimens, which the teacher ought to follow through the entire work. Every person who has had experience in tuition knows well the importance of such examinations in teaching elementary geometry. The exercises, of which there are over 800, have been all selected with great care. Those in the body of each book are intended as applications of Euclid's propositions. They are for the most part of an elementary character, and may be regarded as common property, nearly every one of them having appeared already in previous collections. The exercises at the end of each book are more advanced, several are due to the late Professor Townsend, some are original, and a large number have been taken from two important French works, Catalan's Theorems et Problems de Géométrie élémentaire, and the Traité de Géométrie, by Rauch and Decumbe Raus. The second edition has been thoroughly revised and greatly enlarged. The new matter includes several alternative proofs, important examination questions on each of the books, an explanation of the ratio of incommensurable quantities, the first 21 propositions of Book 11, and an appendix on the properties of the prism, pyramids, cylinder, sphere, and cone. The present edition has been very carefully read throughout, and it is hoped that few misprints have escaped detection. The editor is glad to find from the rapid sale of former editions, each 3,000 copies, of his book, and its general adoption in schools, that it is likely to accomplish the double object with which it was written, viz. To supply students with a manual that will impart a thorough knowledge of the immortal work of the great Greek geometer, and introduce them, at the same time, to some of the most important conceptions and developments of the geometry of the present day. John Casey, 86, South Circular Road, Dublin. November, 1885. Contents: The Elements of Euclid. underscore 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 introduction. Geometry is the science of figured space. Figured space is of 1, 2, or 3 dimensions, according as it consists of lines, surfaces, or solids. The boundaries of solids are surfaces, of surfaces, lines, and of lines, points. Thus it is the province of geometry to investigate the properties of solids, of surfaces, and of the figures described on surfaces. The simplest of all surfaces is the plane, and that department of geometry which is occupied with the lines and curves drawn on a plane is called plane geometry. That which demonstrates the properties of solids, of curved surfaces, and the figures described on curved surfaces, is geometry of 3 dimensions. The simplest lines that can be drawn on a plane are the right line and circle, and the study of the properties of the point, the right line, and the circle, is the introduction to geometry, of which it forms an extensive and important department. This is the part of geometry on which the oldest mathematical book in existence, namely, Euclid's Elements, is written, and is the subject of the present volume. The conic sections and other curves that can be described on a plane form special branches, and complete the divisions of this, the most comprehensive of all the sciences. The student will find in Chasley's Aperçu historique a valuable history of the origin and the development of the methods of geometry. Underscore 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 underscore. In the following work, when figures are not drawn, the student should construct them from the given directions. The propositions of Euclid will be printed in larger type, and will be referred to by Roman numerals enclosed in brackets. Thus 3xxxii will denote the 32nd proposition of the third book. The number of the book will be given only when different from that under which the reference occurs. The general and the particular enunciation of every proposition will be given in one. By omitting the letters enclosed in parentheses we have the general enunciation, and by reading them, the particular. The annotations will be printed in smaller type. The following symbols will be used in them. Circle will be denoted by triangle, parallelogram, parallel lines, perpendicular. In addition to these we shall employ the usual symbols plus, and C of algebra, and also the sign of congruence, namely. This symbol has been introduced by the illustrious Gauss. Book I Theory of Angles, Triangles, Parallel Lines, and Parallelograms. Underscore 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 definitions. The point. A point is that which has position but not dimensions. A geometrical magnitude which has 3 dimensions, that is, length, breadth, and thickness, is a solid. That which has 2 dimensions, such as length and breadth, is a surface, and that which has but 1 dimension is a line. But a point is neither a solid, nor a surface, nor a line, hence it has no dimensions, that is, it has neither length, breadth, nor thickness. The line. A line is length without breadth. A line is space of 1 dimension. If it had any breadth, no matter how small, it would be space of 2 dimensions, and if in addition it had any thickness it would be space of 3 dimensions, hence a line has neither breadth nor thickness. 3. The intersections of lines and their extremities are points. 4. A line which lies evenly between its extreme points is called a straight or right line, such as a B. If a point move without changing its direction it will describe a right line. The direction in which a point moves is called its sense. If the moving point continually changes its direction it will describe a curve, hence it follows that only one right line can be drawn between 2 points. The following illustration is due to Professor Henrici. If we suspend a weight by a string, the string becomes stretched, and we say it is straight, by which we mean to express that it has assumed a peculiar definite shape. If we mentally abstract from this string all thickness, we obtain the notion of the simplest of all lines, which we call a straight line. The plane. A surface is that which has length and breadth. A surface is space of two dimensions. It has no thickness, for if it had any, however small, it would be space of three dimensions. 6. When a surface is such that the right line joining any two arbitrary points in it lies wholly in the surface, it is called a plane. A plane is perfectly flat and even, like the surface of still water, or of a smooth floor Newcomb. Figures. 7. Any combination of points, of lines, or of points and lines in a plane, is called a plane figure. If a figure be formed of points only, it is called a stigmatic figure, and if of right lines only, a rectilineal figure. 8. Points which lie on the same right line are called collinear points. A figure formed of collinear points is called a row of points. The angle. 9. The inclination of two right lines extending out from one point in different directions is called a rectilineal angle. X. The two lines are called the legs, and the point the vertex of the angle. A right line drawn from the vertex and turning about it in the plane of the angle, from the position of coincidence with one leg to that of coincidence with the other, is said to turn through the angle, and the angle is the greater as the quantity of turning is the greater. Again, since the line may turn from one position to the other in either of two ways, two angles are formed by two lines drawn from a point. Thus if AB, AC be the legs, a line may turn from the position AB to the position AC in the two ways indicated by the arrows. The smaller of the angles thus formed is to be understood as the angle contained by the lines. The larger, called a reentrant angle, seldom occurs in the elements 11. Designation of angles. A particular angle in a figure is denoted by three letters, as BAC, of which the middle one, A, is at the vertex, and the other two along the legs. The angle is then read BAC. 12. The angle formed by joining two or more angles together is called their sum. Thus the sum of the two angles ABC, PQR is the angle of R, formed by applying the side QP to the side BC, so that the vertex Q shall fall on the vertex B, and the side QR on the opposite side of BC from BA. 13. When the sum of two angles BAC, CAD is such that the legs BA, AD form one right line, they are called supplements of each other. Hence, when one line stands on another, the two angles which it makes on the same side of that on which it stands are supplements of each other. 14. When one line stands on another, and makes the adjacent angles at both sides of itself equal, each of the angles is called a right angle, and the line which stands on the other is called a perpendicular to it. Hence a right angle is equal to its supplement. 15. An acute angle is one which is less than a right angle, as A16. An obtuse angle is one which is greater than a right angle, as BAC. The supplement of an acute angle is obtuse, and conversely, the supplement of an obtuse angle is acute. 17. When the sum of two angles is a right angle, each is called the complement of the other. Thus, if the angle BAC be right, the angles BAD, DAC are complements of each other. Concurrent lines. 18. Three or more right lines passing through the same point are called concurrent lines. 19. A system of more than three concurrent lines is called a pencil of lines. Each line of a pencil is called a ray, and the common point through which the rays pass is called the vertex. The triangle. XX. A triangle is a figure formed by three right lines joined end to end. The three lines are called its sides. XXI. A triangle whose three sides are unequal is said to be scalene, as a triangle having two sides equal, to be isosceles, as B, and having all its sides equal, to be equilateral, as CXXII. A right-angled triangle is one that has one of its angles a right angle, as D. The side which subtends the right angle is called the hypotenuse. XXIII. An obtuse angled triangle is one that has one of its angles obtuse, as EXXIV. An acute angled triangle is one that has its three angles acute, as FXXV. An exterior angle of a triangle is one that is formed by any side and the continuation of another side. Hence a triangle has 6 exterior angles, and also each exterior angle is the supplement of the adjacent interior angle. The polygon XXVI. A rectilineal figure bounded by more than 3 right lines is usually called a polygon. XXVII. A polygon is said to be convex when it has no reentrant angle. XXVII. A polygon of 4 sides is called a quadrilateral. XXIX. A quadrilateral whose 4 sides are equal is called a lozenge. XXX. A lozenge which has a right angle is called a square. XXXI. A polygon which has 5 sides is called a pentagon, one which has 6 sides, a hexagon, and so on. The circle XXXII. A circle is a plane figure formed by a curved line called the circumference, and is such that all right lines drawn from a certain point within the figure to the circumference are equal to one another. This point is called the center XXXII. A radius of a circle is any right line drawn from the center to the circumference, such as CD. The diameter of a circle is a right line drawn through the center and terminated both ways by the circumference, such as a b. From the definition of a circle it follows at once that the path of a movable point in a plane which remains at a constant distance from a fixed point is a circle, also that any point P in the plane is inside, outside, or on the circumference of a circle according as its distance from the center is less than, greater than, or equal to, the radius. Postulates. Let it be granted that a right line may be drawn from any one point to any other point. When we consider a straight line contained between 2 fixed points which are its ends, such a portion is called a finite straight line. A terminated right line may be produced to any length in a right line. Every right line may extend without limit in either direction or in both. It is in these cases called an indefinite line. By this postulate a finite right line may be supposed to be produced, whenever we please, into an indefinite right line. A circle may be described from any center, and with any distance from that center as radius. If there be 2 points A and B, and if with any instruments, such as a ruler and pen, we draw a line from A to B, this will evidently have some irregularities, and also some breadth and thickness. Hence it will not be a geometrical line no matter how nearly it may approach to one. This is the reason that Euclid postulates the drawing of a right line from one point to another. For if it could be accurately done there would be no need for his asking us to let it be granted. Similar observations apply to the other postulates. It is also worthy of remark that Euclid never takes for granted the doing of anything for which a geometrical construction, founded on other problems or on the foregoing postulates, can be given. Axioms. Things which are equal to the same, or to equals, are equal to each other. Thus, if there be 3 things, and if the first, and the second, be each equal to the third, we infer by this axiom that the first is equal to the second. This axiom relates to all kinds of magnitude. The same is true of axioms 2, 3, 4, v, 6, 7, 9, but 8, x, 11, 12, are strictly geometrical. 2 if equals be added to equals the sums will be equal. 3 if equals be taken from equals the remainders will be equal. 4 if equals be added to unequals the sums will be unequal. V if equals be taken from unequals the remainders will be unequal. 6. The doubles of equal magnitudes are equal. 7. The halves of equal magnitudes are equal. 8. Magnitudes that can be made to coincide are equal. The placing of one geometrical magnitude on another, such as a line on a line, a triangle on a triangle, or a circle on a circle, and c, is called superposition. The superposition employed in geometry is only mental, that is, we conceive one magnitude placed on the other, and then, if we can prove that they coincide, we infer, by the present axiom, that they are equal. Superposition involves the following principle, of which, without explicitly stating it, Euclid makes frequent use. Any figure may be transferred from one position to another without change of form or size. 9. The whole is greater than its part. This axiom is included in the following, which is a fuller statement. 9. The whole is equal to the sum of all its parts. Two right lines cannot enclose a space. This is equivalent to the statement, if two right lines have 2 points common to both, they coincide in direction, that is, they form but one line, and this holds true even when one of the points is at infinity. 11. All right angles are equal to one another. This can be proved as follows. Let there be two right lines AB, CD, and two perpendiculars to them, namely, F, GH, then if AB, CD be made to coincide by superposition, so that the point E will coincide with G, then since a right angle is equal to its supplement, the line F must coincide with GH. Hence the angle AEF is equal to CGH. 12. If two right lines, AB, CD, meet a third line, AC, so as to make the sum of the two interior angles, BAC, ACD, on the same side less than two right angles, these lines being produced shall meet at some finite distance. This axiom is the converse of Prop 17, Book I. Explanation of terms. Axioms. Elements of human reason, according to Dugald Stewart, are certain general propositions, the truths of which are self-evident, and which are so fundamental, that they cannot be inferred from any propositions which are more elementary. In other words, they are incapable of demonstration. That two sides of a triangle are greater than the third is, perhaps, self-evident, but it is not an axiom, inasmuch as it can be inferred by demonstration from other propositions, but we can give no proof of the proposition that things which are equal to the same are equal to one another, and, being self-evident, it is an axiom. Propositions which are not axioms are properties of figures obtained by processes of reasoning. They are divided into theorems and problems. A theorem is the formal statement of a property that may be demonstrated from known propositions. These propositions may themselves be theorems or axioms. A theorem consists of two parts, the hypothesis, or that which is assumed, and the conclusion, or that which is asserted to follow therefrom. Thus, in the typical theorem, the hypothesis is that X is Y, and the conclusion is that Z is W. Converse theorems. Two theorems are said to be converse, each of the other, when the hypothesis of either is the conclusion of the other. Thus the converse of the theorem, I, is from the two theorems, I, and, 2, we may infer two others, called their contrapositives. Thus the contrapositive of, I, is, if Z is not W, then X is not Y. 3, of, 2, is, if X is not Y, then Z is not W. 4. The theorem, 4, is called the obverse of, I, and, 3, the obverse of, 2. A problem is a proposition in which something is proposed to be done, such as a line to be drawn, or a figure to be constructed, under some given conditions. The solution of a problem is the method of construction which accomplishes the required end. The demonstration is the proof, in the case of a theorem, that the conclusion follows from the hypothesis, and in the case of a problem, that the construction accomplishes the object proposed. The enunciation of a problem consists of two parts, namely, the data, or things supposed to be given, and the quicita, or things required to be done. Postulates are the elements of geometrical construction, and occupy the same relation with respect to problems as axioms do to theorems. A corollary is an inference or deduction from a proposition. A lemma is an auxiliary proposition required in the demonstration of a principal proposition. A secant or transversal is a line which cuts a system of lines, a circle, or any other geometrical figure. Congruent figures are those that can be made to coincide by superposition. They agree in shape and size, but differ in position. Hence it follows, by axiom 8, that corresponding parts or portions of congruent figures are congruent, and that congruent figures are equal in every respect. Rule of identity. Under this name the following principle will be sometimes referred to: if there is but one x and one y, then, from the fact that x is y, it necessarily follows that y is x. Syllabus. Prop. I problem. On a given finite right line, AB, to construct an equilateral triangle. Solution: with A as center, and AB as radius, describe the circle BCD, post 3. With B as center, and BA as radius, describe the circle ACE, cutting the former circle in C join CA, CB, post I. Then ABC is the equilateral triangle required. Democrat: because A is the center of the circle BCD, AC is equal to AB, DEFXXXII. Again, because B is the center of the circle ACE, BC is equal to BA. Hence we have proved AC equals AB, and BC equals AB. But things which are equal to the same are equal to one another, axiom I, therefore AC is equal to BC, therefore the three lines AB, BC, CA are equal to one another. Hence the triangle ABC is equilateral, DEFXXI, and it is described on the given line AB, which was required to be done. Questions for examination. 1. What is the datum in this proposition? 2. What is the quicitum? 3. What is a finite right line? 4. What is the opposite of finite? 5. In what part of the construction is the third postulate quoted? And for what purpose? Where is the first postulate quoted? 6. Where is the first axiom quoted? 7. What use is made of the definition of a circle? What is a circle? 8. What is an equilateral triangle? Exercises. The following exercises are to be solved when the pupil has mastered the first book 1. If the lines AF, BF be joined, the figure ACBF is a lozenge. 2. If A be produced to D and E, the triangles CDF and CEF are equilateral. 3. If CA, CB be produced to meet the circles again in G and H, the points G, F, H are collinear, and the triangle GCH is equilateral. 4. If CF be joined, CF2 equals 3 of 2. 5. Describe a circle in the space ACB, bounded by the line AB and the two circles. Prop. 2. Problem. From a given point, A, to draw a right line equal to a given finite right line, BC. Solution: join AB, post I, on AB describe the equilateral triangle ABDI. With B as center, and BC as radius, describe the circle EC, post 3. Produce DB to meet the circle EC in E, post 2. With D as center, and A as radius, describe the circle EFG, post 3. Produce D to meet the circle in FAF is equal to BC. Democrat: because D is the center of the circle EFG, DF is equal to D, DEFXXXII. And because DAB is an equilateral triangle, D is equal to DB, DEFXXI. Hence we have DF equals D, and d equals db, and taking the latter from the former, the remainder af is equal to the remainder b, axiom 3. Again, because b is the center of the circle EC, bc is equal to b, and we have proved that af is equal to b, and things which are equal to the same thing are equal to one another, axiom I. Hence af is equal to bc. Therefore from the given point A the line AF has been drawn equal to BC. It is usual with commentators on Euclid to say that he allows the use of the rule and compass. Were such the case, this proposition would have been unnecessary. The fact is, Euclid's object was to teach theoretical and not practical geometry, and the only things he postulates are the drawing of right lines and the describing of circles. If he allowed the mechanical use of the rule and compass, he could give methods of solving many problems that go beyond the limits of the geometry of the point, line, and circle. See notes D, F at the end of this work. Exercises. 1. Solve the problem when the point A is in the line BC itself. 2. Inflect from a given point A to a given line BC, a line equal to a given line. State the number of solutions. Prop. 3. Problem. From the greater, of two given right lines to cut off a part equal to, C, the less. Solution. From A, one of the extremities of a draw the right line AD equal to C2, and with A as center, and AD as radius, describe the circle EDF. Post 3. Cutting ab in EAE shall be equal to C Democrat because A is the center of the circle EDF, AE is equal to AD, DEF XXXII, and C is equal to AD, constant, and things which are equal to the same are equal to one another, axiom I. Therefore AE is equal to C, wherefore from ab, the greater of the two given lines, apart, AE, has been out. Off equal to C, the less. Questions for examination. 1. What previous problem is employed in the solution of this? 2. What postulate? 3. What axiom in the demonstration? 4. Show how to produce the less of two given lines until the whole produced line becomes equal to the greater. Prop. 4. Theorem. If two triangles, BAC, EDF, have two sides, BA, AC, of one equal respectively to two sides, ED, DF, of the other, and have also the angles, A, D, included by those sides equal, the triangles shall be equal in every respect, that is, their bases or third sides, BC, F, shall be equal, and the angles, B, C, at the base of one shall be respectively equal to the angles, E, F, at the base of the other, namely, those shall be equal to which the equal sides are opposite. Democrat. Let us conceive the triangle BAC to be applied to EDF, so that the point A shall coincide with D, and the line AB with D, and that the point C shall be on the same side of D as F, then because AB is equal to D, the point B shall coincide with E. Again, because the angle BAC is equal to the angle EDF, the line AC shall coincide with DF, and since AC is equal to DF, HIP, the point C shall coincide with F, and we have proved that the point B coincides with E. Hence 2 points of the line BC coincide with 2 points of the line F, and since two right lines cannot enclose a space, BC must coincide with F. Hence the triangles agree in every respect, therefore BC is equal to F, the angle B is equal to the angle E, the angle C to the angle F, and the triangle BAC to the triangle EDF. Questions for examination. 1. How many parts in the hypothesis of this proposition? ANS 3. Name them. 2. How many in the conclusion? Name them. 3. What technical term is applied to figures which agree in everything but position? ANS. They are said to be congruent. 4. What is meant by superposition? 5. What axiom is made use of in superposition? 6. How many parts in a triangle? ANS 6, namely, 3 sides and 3 angles. 7. When it is required to prove that two triangles are congruent, how many parts of one must be given equal to corresponding parts of the other? ANS. In general, any 3 except the 3 angles. This will be established in props. 8 and XXVI, taken along with 4. 8. What property of two lines having two common points is quoted in this proposition? They must coincide. Exercises. 1. The line that bisects the vertical angle of an isosceles triangle bisects the base perpendicularly. 2. If two adjacent sides of a quadrilateral be equal, and the diagonal bisects the angle between them, their other sides are equal. 3. If two lines be at right angles, and if each bisect the other, then any point in either is equally distant from the extremities of the other. 4. If equilateral triangles be described on the sides of any triangle, the distances between the vertices of the original triangle and the opposite vertices of the equilateral triangles are equal. This proposition should be proved after the student has read PROPXXXII. Prop. V theorem. The angles, ABC, ACB, at the base, BC, of an isosceles triangle are equal to one another, and if the equal sides, AB, AC, be produced, the external angles, DEC, ECB, below the base shall be equal. Democrat in BD take any point F, and from AE, the greater, cut off AG equal to AF3. Join BG, CF, post I. Because AF is equal to AG, constant, and AC is equal to AB, hip, the two triangles FAC, GAB have the sides FA, AC in one respectively equal to the sides GA, AB in the other, and the included angle A is common to both triangles. Hence for the base FC is equal to GB, the angle AFC is equal to AGB, and the angle ACF is equal to the angle ABG. Again, because AF is equal to AG, constant, and AB to AC, hip, the remainder, BF, is equal to CG, axiom 3, and we have proved that FC is equal to GB, and the angle BFC equal to the angle CGB. Hence the two triangles BFC, CGB have the two sides BF, FC in one equal to the two sides CG, GB in the other, and the angle BFC contained by the two sides of one equal to the angle CGB contained by the two sides of the other. Therefore for these triangles have the angle FBC equal to the angle GCB, and these are the angles below the base. Also the angle FCB equal to GBC, but the whole angle FCA has been proved equal to the whole angle GBA. Hence the remaining angle ACB is equal to the remaining angle ABC, and these are the angles at the base. Observation: the great difficulty which beginners find in this proposition is due to the fact that the two triangles ACF, ABG overlap each other. The teacher should make these triangles separate, as in the annexed diagram, and point out the corresponding parts, thus AF equals AG, AC equals AB, angle FAC equals angle GAB. Hence for angle ACF equals angle ABG. And angle AFC equals angle AGB. The student should also be shown how to apply one of the triangles to the other, so as to bring them into coincidence. Similar illustrations may be given of the triangles BFC, CGB. The following is a very easy proof of this proposition. Conceive the ACB to be turned, without alteration, round the line AC, until it falls on the other side. Let ACD be its new position, then the angle ADC of the displaced triangle is evidently equal to the angle ABC, with which it originally coincided. Again, the two SBAC, CAD have the sides BA, AC of one respectively equal to the sides AC, AD of the other, and the included angles equal, therefore for the angle ACB opposite to the side AB is equal to the angle ADC opposite to the side AC, but the angle ADC is equal to ABC, therefore ACB is equal to ABC. COR every equilateral triangle is equiangular. DEF a line in any figure, such as AC in the preceding diagram, which is such that, by folding the plane of the figure round it, one part of the diagram will coincide with the other, is called an axis of symmetry of the figure. Exercises. 1. Prove that the angles at the base are equal without producing the sides. Also by producing the sides through the vertex. 2. Prove that the line joining the point A to the intersection of the lines CF and BG is an axis of symmetry of the figure. 3. If two isosceles triangles be on the same base, and be either at the same or at opposite sides of it, the line joining their vertices is an axis of symmetry of the figure formed by them. 4. Show how to prove this proposition by assuming as an axiom that every angle has a bisector. 5. Each diagonal of a lozenge is an axis of symmetry of the lozenge. 6. If 3 points be taken on the sides of an equilateral triangle, namely, one on each side, at equal distances from the angles, the lines joining them form a new equilateral triangle. Prop. 6. Theorem. If two angles, B, C, of a triangle be equal, the sides, AC, AB, opposite to them are also equal. Democrat if AB, AC are not equal, one must be greater than the other. Suppose AB is the greater, and that the part BD is equal to AC join CD, post I. Then the two triangles DBC, ACB have BD equal to AC, and BC common to both. Therefore the two sides DB, BC in one are equal to the two sides AC, CB in the other, and the angle DBC in one is equal to the angle ACB in the other, HIP. Therefore for the triangle DBC is equal to the triangle ACB the less to the greater, which is absurd, hence AC, AB are not unequal, that is, they are equal. Questions for examination. 1. What is the hypothesis in this proposition? 2. What proposition is this the converse of? 3. What is the obverse of this proposition? 4. What is the obverse of PROPV? 5. What is meant by an indirect proof? 6. How does Euclid generally prove converse propositions? 7. What false assumption is made in the demonstration? 8. What does this assumption lead to? Prop. 7. Theorem. If two triangles, ACB, ADB, on the same base, AB, and on the same side of it have one pair of conterminous sides, AC, AD, equal to one another, the other pair of conterminous sides, BC, BD, must be unequal. Democrat 1. Let the vertex of each triangle be without the other. Join CD. Then because AD is equal to AC, HIP, the triangle ACD is isosceles, therefore the angle ACD is equal to the angle ADC, but ADC is greater than BDC, axiom 9, therefore ACD is greater than BDC, much more is BCD greater than BDC. Now if the side BD were equal to BC, the angle BCD would be equal to BDCV, but it has been proved to be greater. Hence BD is not equal to BC. 2. Let the vertex of one triangle ADB fall within the other triangle ACB. Produce the sides AC, AD to E and F. Then because AC is equal to AD, HIP, the triangle ACD is isosceles, and V the external angles ECD, FDC at the other side of the base CD are equal, but ECD is greater than BCD, axiom 9. Therefore FDC is greater than BCD, much more is BDC greater than BCD, but if BC were equal to BD, the angle BDC would be equal to BCDV, therefore BC cannot be equal to BD3. If the vertex D of the second triangle fall on the line BC, it is evident that BC and BD are unequal. Questions for examination. 1. What use is made of PROP7? ANS. As a lemma to PROP8. 2. In the demonstration of PROP7. The contrapositive of PROPV occurs, show where. 3. Show that two circles can intersect each other only in one point on the same side of the line joining their centers, and hence that two circles cannot have more than 2 points of intersection. Prop. 8 theorem. If two triangles, ABC, DEF, have two sides, AB, AC, of one respectively equal to two sides, DE, DF, of the other, and have also the base, BC, of one equal to the base, F, of the other, then the two triangles shall be equal, and the angles of one shall be respectively equal to the angles of the other, namely, those shall be equal to which the equal sides are opposite. Democrat, let the triangle ABC be applied to DEF, so that the point B will coincide with E, and the line BC with the line F, then because BC is equal to F, the point C shall coincide with F. Then if the vertex A fall on the same side of F as the vertex D, the point A must coincide with D, for if not, let it take a different position G, then we have EG equal to BA, and BA is equal to ED, HIP. Hence, axiom I. EG is equal to ED, in like manner, FG is equal to FD, and this is impossible. 7. Hence the point A must coincide with D, and the triangle ABC agrees in every respect with the triangle DEF, and therefore the three angles of one are respectively equal to the three angles of the other, namely, A to D, B to E, and C to F, and the two triangles are equal. This proposition is the converse of 4, and is the second case of the congruence of triangles in the elements. Philo's proof. Let the equal bases be applied as in the foregoing proof, but let the vertices be on the opposite sides, then let BGC be the position which EDF takes. Join AG. Then because BG equals BA, the angle BAG equals BGA. In like manner the angle CAG equals CGA. Hence the whole angle BAC equals BGC, but BGC equals EDF, therefore BAC equals EDF. Prop. 9 problem. To bisect a given rectilineal angle, BAC. Solution in AB. Take any point D, and cut off 3. AE equal to AD. Joined A, post I, and upon it, on the side remote from A, describe the equilateral triangle DEF I. Join AF. AF bisects the given angle BAC. Democrat, the triangles DAF, EAF have the side AD equal to AE, constant, and AF common, therefore the two sides DA, AF are respectively equal to EA, AF, and the base DF is equal to the base F, because they are the sides of an equilateral triangle, DEFXXI. Therefore 8. The angle DAF is equal to the angle EAF, hence the angle BAC is bisected by the line AF. COR. The line AF is an axis of symmetry of the figure. Questions for examination. 1. Why does Euclid describe the equilateral triangle on the side remote from A? 2. In what case would the construction fail, if the equilateral triangle were described on the other side of DA? Exercises. 1. Prove this proposition without using PROP8. 2. Prove that AF is perpendicular to DA. 3. Prove that any point in AF is equally distant from the points D and E. 4. Prove that any point in AF is equally distant from the lines AB, AC. Prop. X problem. To bisect a given finite right line, AB. Solution. Upon AB describe an equilateral triangle ACBI. Bisect the angle ACB by the line CD9, meeting AB in D, then AB is bisected in D. Democrat the two triangles ACD, BCD, have the side AC equal to BC, being the sides of an equilateral triangle, and CD common. Therefore the two sides AC, CD in one are equal to the two sides BC, CD in the other, and the angle ACD is equal to the angle BCD, constant. Therefore the base AD is equal to the base DB4. Hence AB is bisected in D exercises. 1. Show how to bisect a finite right line by describing two circles. 2. Every point equally distant from the points A, B is in the line CD. Prop. 11. Problem. From a given point, C, in a given right line, AB, to draw a right line perpendicular to the given line. Solution. In AC take any point D, and make CE equal to CD3. Upon to describe an equilateral triangle DFEI. Join CF. Then CF shall be at right angles to AB. Democrat the two triangles DCF, ECF have CD equal to CE, constant, and CF common, therefore the two sides CD, CF in one are respectively equal to the two sides CE, CF in the other, and the base DF is equal to the base F, being the sides of an equilateral triangle, DEFXXI, therefore 8 the angle DCE is equal to the angle ECF, and they are adjacent angles. Therefore, DEF 13, each of them is a right angle, and CF is perpendicular to AB at the point C. Exercises. 1. The diagonals of a lozenge bisect each other perpendicularly. 2. Prove PROP 11. Without using PROP 8. 3. Erect a line at right angles to a given line at one of its extremities without producing the line. 4. Find a point in a given line that shall be equally distant from two given points. 5. Find a point in a given line such that, if it be joined to two given points on opposite sides of the line, the angle formed by the joining lines shall be bisected by the given line. 6. Find a point that shall be equidistant from three given points. Prop. 12. Problem. To draw a perpendicular to a given indefinite right line, AB, from a given point, C, without it. Solution. Take any point D on the other side of AB, and describe, post 3, a circle, with C as center, and CD as radius, meeting AB in the points F and G. Bisect FG in HX. Join CH, post I. CH shall be at right angles to AB. Democrat join CF, CG. Then the two triangles FHC, GHC have FH equal to GH, constant, and HC common, and the base CF equal to the base CG, being radii of the circle FDG, DEFXXXII. Therefore the angle CHF is equal to the angle change 8, and, being adjacent angles, they are right angles, DEF 13. Therefore CH is perpendicular to AB. Exercises. 1. Prove that the circle cannot meet AB in more than 2 points. 2. If one angle of a triangle be equal to the sum of the other two, the triangle can be divided into the sum of two isosceles triangles, and the base is equal to twice the line from its middle point to the opposite angle. Prop. 13. Theorem. The adjacent angles, ABC, ABD, which one right line, AB, standing on another, CD, makes with it are either both right angles, or their sum is equal to two right angles. Democrat. If AB is perpendicular to CD, as in figure 1, the angles ABC, ABD are right angles. If not, draw B perpendicular to CD 11. Now the angle CBA is equal to the sum of the two angles CBE, EBA, DEF 11. Hence, adding the angle ABD, the sum of the angles CBA, ABD is equal to the sum of the three angles CBE, EBA, ABD. In like manner, the sum of the angles CBE, EBD is equal to the sum of the three angles CBE, EBA, ABD. And things which are equal to the same are equal to one another. Therefore the sum of the angles CBA, ABD is equal to the sum of the angles CBE, EBD, but CBE, EBD are right angles, therefore the sum of the angles CBA, ABD is two right angles. Or thus, denote the angle EBA by theta, then evidently the angle CBA equals right angle plus theta, the angle ABD equals right angle theta, therefore CBA plus ABD equals two right angles. COR1 the sum of two supplemental angles is two right angles. COR2 two right lines cannot have a common segment. COR3 the bisector of any angle bisects the corresponding reentrant angle. COR4 the bisectors of two supplemental angles are at right angles to each other. COR5 the angle EBA is half the difference of the angles CBA, ABD. Prop. 14, Theorem. If at a point, B, in a right line, BA, two other right lines, CB, BD, on opposite sides make the adjacent angles, CBA, ABD, together equal to two right angles, these two right lines form one continuous line. Democrat if BD be not the continuation of CB, let B be its continuation. Now, since CBE is a right line, and BA stands on it, the sum of the angles CBA, AB is two right angles, 13, and the sum of the angles CBA, ABD is two right angles, HIP, therefore the sum of the angles CBA, AB is equal to the sum of the angles CBA, ABD. Reject the angle CBA, which is common, and we have the angle AB equal to the angle ABD, that is, a part equal to the whole, which is absurd. Hence BD must be in the same right line with CB. Prop. 15 Theorem. If two right lines, AB, CD, intersect one another, the opposite angles are equal, CEA equals DEB, and BEC equals AED. Democrat because the line AE stands on CD, the sum of the angles CEA, AED is two right angles 13, and because the line CE stands on AB, the sum of the angles BEC, CEA is two right angles, therefore the sum of the angles CEA, AED is equal to the sum of the angles BEC, CEA. Reject the angle CEA, which is common, and we have the angle AED equal to BEC. In like manner, the angle CEA is equal to DEB. The foregoing proof may be briefly given, by saying that opposite angles are equal because they have a common supplement. Questions for examination on props. 13, 14, 15. 1. What problem is required in Euclid's proof of prop 13? 2. What theorem? ANS. No theorem, only the axioms. 3. If two lines intersect, how many pairs of supplemental angles do they make? 4. What relation does prop 14 bear to prop 13? 5. What three lines in prop 14 are concurrent? 6. What caution is required in the enunciation of prop 14? 7. State the converse of prop 15. Prove it. 8. What is the subject of props 13, 14, 15? ANS angles at a point. Prop. 16 Theorem. If any side, BC, of a triangle, ABC, be produced, the exterior angle, ACD, is greater than either of the interior non-adjacent angles. Democrat bisect AC in EX. Join B, post I. Produce it, and from the produced part cut off F equal to B3. Join CF. Now because EC is equal to EA, constant, and F is equal to EB, the triangles CEF, AEB have the sides CE, F in one equal to the sides AE, EB in the other, and the angle CEF equal to AEB 15. Therefore for the angle ECF is equal to EAB, but the angle ACD is greater than ECF, therefore the angle ACD is greater than EAB. In like manner it may be shown, if the side AC be produced, that the exterior angle BCG is greater than the angle ABC, but BCG is equal to ACD 15. Hence ACD is greater than ABC. Therefore ACD is greater than either of the interior non-adjacent angles A or B of the triangle ABC. COR1 The sum of the three interior angles of the triangle BCF is equal to the sum of the three interior angles of the triangle ABC. COR2 The area of BCF is equal to the area of ABC. COR3 The lines BA and CF, if produced, cannot meet at any finite distance. 4. If they met at any finite point x, the triangle CAX would have an exterior angle BAC equal to the interior angle ACX. Prop. 17 Theorem. Any two angles, B, C, of a triangle, ABC, are together less than two right angles. Democrat produce BC to D, then the exterior angle ACD is greater than ABC 16, to each add the angle ACB, and we have the sum of the angles ACD, ACB greater than the sum of the angles ABC, ACB, but the sum of the angles ACD, ACB is two right angles 13. Therefore the sum of the angles ABC, ACB is less than two right angles. In like manner we may show that the sum of the angles A, B, or of the angles A, C, is less than two right angles. COR1 Every triangle must have at least two acute angles. COR2 If two angles of a triangle be unequal, the lesser must be acute. Exercise. Prove Prop 17. Without producing a side. Prop. 18 Theorem. If in any triangle, ABC, one side, AC, be greater than another, AB, the angle opposite to the greater side is greater than the angle opposite to the less. Democrat from AC cut off AD equal to AB 3. Join BD, post I. Now since AB is equal to AD, the triangle ABD is isosceles, therefore V the angle ADB is equal to ABD, but the angle ADB is greater than the angle ACB 16, therefore ABD is greater than ACB. Much more is the angle ABC greater than the angle ACB. Or thus, from A as center, with the lesser side of as radius, describe the circle bed, cutting BC in E join AE. Now since AB is equal to AE, the angle AEB is equal to AB, but AEB is greater than ACB, 16, therefore AB is greater than ACB. Exercises. 1. If in the second method the circle cut the line CB produced through B, prove the proposition. 2. This proposition may be proved by producing the less side. 3. If two of the opposite sides of a quadrilateral be respectively the greatest and least, the angles adjacent to the least are greater than their opposite angles. 4. In any triangle, the perpendicular from the vertex opposite the side which is not less than either of the remaining sides falls within the triangle. Prop. 19 Theorem. If one angle, B, of a triangle, ABC, be greater than another angle, C, the side, AC, which at opposite to the greater angle is greater than the side, AB, which is opposite to the less. Democrat if AC be not greater than AB, it must be either equal to it or less than it. Let us examine each case 1. If AC were equal to AB, the triangle ACB would be isosceles, and then the angle B would be equal to CV, but it is not by hypothesis, therefore AB is not equal to AC2. If AC were less than AB, the angle B would be less than the angle C18, but it is not by hypothesis, therefore AC is not less than AB, and since AC is neither equal to AB nor less than it, it must be greater. Exercises. 1. Prove this proposition by a direct demonstration. 2. A line from the vertex of an isosceles triangle to any point in the base is less than either of the equal sides, but greater if the point be in the base produced. 3. Three equal lines could not be drawn from the same point to the same line. 4. The perpendicular is the least line which can be drawn from a given point to a given line, and of all others that may be drawn to it, that which is nearest to the perpendicular is less than any one more remote. 5. If in the figure, Prop 16, of B the greatest side of the ABC, BF is the greatest side of the FBC, and the angle BFC is less than half the angle ABC. 6. If ABCBA having of not greater than AC, a line AG, drawn from A to any point G in BC, is less than AC. For the angle ACB18 is not greater than ABC, but AGC16 is greater than ABC, therefore AGC is greater than AC. Hence AC is greater than AG. Prop. XX theorem. The sum of any two sides, BA, AC, of a triangle, ABC, is greater than the third. Democrat produce BA to D, post 2, and make AD equal to AC3. Join CD. Then because AD is equal to AC, the angle ACD is equal to ADC, V, therefore the angle BCD is greater than the angle BDC, hence the side BD opposite to the greater angle is greater than BC opposite to the less 19. Again, since AC is equal to AD, adding BA to both, we have the sum of the sides BA, AC equal to BD. Therefore the sum of BA, AC is greater than BC. Or thus, bisect the angle BAC by AE9. Then the angle BEA is greater than EAC, but EAC equals EAB, constant, therefore the angle BEA is greater than EAB. Hence AB is greater than B19. In like manner AC is greater than EC. Therefore the sum of BA, AC is greater than BC. Exercises. 1. In any triangle, the difference between any two sides is less than the third. 2. If any point within a triangle be joined to its angular points, the sum of the joining lines is greater than its semi-perimeter. 3. If through the extremities of the base of a triangle, whose sides are unequal, lines be drawn to any point in the bisector of the vertical angle, their difference is less than the difference of the sides. 4. If the lines be drawn to any point in the bisector of the external vertical angle, their sum is greater than the sum of the sides. 5. Any side of any polygon is less than the sum of the remaining sides. 6. The perimeter of any triangle is greater than that of any inscribed triangle, and less than that of any circumscribed triangle. 7. The perimeter of any polygon is greater than that of any inscribed, and less than that of any circumscribed, polygon of the same number of sides. 8. The perimeter of a quadrilateral is greater than the sum of its diagonals. DEF. A line drawn from any angle of a triangle to the middle point of the opposite side is called a median of the triangle. 9. The sum of the three medians of a triangle is less than its perimeter. 10. The sum of the diagonals of a quadrilateral is less than the sum of the lines which can be drawn to its angular points from any point except the intersection of the diagonals. Prop. XXI theorem. If two lines, BD, CD, be drawn to a point, D, within a triangle from the extremities of its base, BC, their sum is less than the sum of the remaining sides, BA, CA, but they contain a greater angle. Democrat 1. Produce BD, post 2, to meet AC in A. Then, in the triangle BA, the sum of the sides BA, AE is greater than the side BXX, to each add EC, and we have the sum of BA, AC greater than the sum of B, EC. Again, the sum of the sides DA, EC of the triangle DEC is greater than DC, to each add BD, and we get the sum of B, EC greater than the sum of BD, DC, but it has been proved that the sum of BA, AC is greater than the sum of B, EC. Therefore much more is the sum of BA, AC greater than the sum of BD, DC. 2. The external angle BDC of the triangle DEC is greater than the internal angle BEC16, and the angle BEC, for a like reason, is greater than BAC. Therefore much more is BDC greater than BAC. Part may second be proved without producing either of the sides BD, DC. Thus, join AD and produce it to meet BC in F, then the angle BDF is greater than the angle BAF16, and FDC is greater than FAC. Therefore the whole angle BDC is greater than BAC. Exercises. 1. The sum of the lines drawn from any point within a triangle to its angular points is less than the perimeter. Compare EX2, last prop. 2. If a convex polygonal line ABCD lie within a convex polygonal line AM and D terminating in the same extremities, the length of the former is less than that of the latter. Prop. XXII problem. To construct a triangle whose three sides shall be respectively equal to three given lines, A, B, C, the sum of every two of which is greater than the third. Solution: take any right line A, terminated at D, but unlimited towards E, and cut off 3. DF equal to A, FG equal to B, and GH equal to C. With F as center, and FD as radius, describe the circle KDL, post 3, and with G as center, and GH as radius, describe the circle KHL, intersecting the former circle in K join KF, KG. KFG is the triangle required. Democrat: since F is the center of the circle KDL, FK is equal to FD, but FD is equal to A, constant, therefore, axiom I. FK is equal to A. In like manner GK is equal to C, and FG is equal to B, constant, hence the three sides of the triangle KFG are respectively equal to the three lines A, B, C. Questions for examination. 1. What is the reason for stating in the enunciation that the sum of every two of the given lines must be greater than the third? 2. Prove that when that condition is fulfilled the two circles must intersect. 3. Under what conditions would the circles not intersect? 4. If the sum of two of the lines were equal to the third, would the circles meet? Prove that they would not intersect. Prop. XXII problem. At a given point, A, in a given right line, AB, to make an angle equal to a given rectilineal angle, def. Solution: in the sides ed, F of the given angle take any arbitrary points D and F join DF, and construct XXII the triangle BAC, whose sides, taken in order, shall be equal to those of def, namely, AB equal to ed, AC equal to F, and CB equal to FD, then the angle BAC will be equal to def. Hence it is the required angle. Exercises. 1. Construct a triangle, being given two sides and the angle between them. 2. Construct a triangle, being given two angles and the side between them. 3. Construct a triangle, being given two sides and the angle opposite to one of them. 4. Construct a triangle, being given the base, one of the angles at the base, and the sum or difference of the sides. 5. Given 2 points, one of which is in a given line, it is required to find another point in the given line, such that the sum or difference of its distances from the former points may be given. Show that 2 such points may be found in each case. Prop. XXIV theorem. If two triangles, ABC, def, have two sides, AB, AC, of one respectively equal to two sides, D, DF, of the other, but the contained angle, BAC, of one greater than the contained angle, EDF, of the other, the base of that which has the greater angle is greater than the base of the other. Democrat of the two sides of AC, let AB be the one which is not the greater, and with it make the angle BAG equal to EDFXXIII. Then because AB is not greater than AC, AG is less than AC 19, Exer 6. Produce AG to H, and make A equal to DF or AC 3. Join BH, CH. In the triangles BA, EDF, we have AB equal to D, HIP, A equal to DF, constant, and the angle BA equal to the angle EDF, constant, therefore the base for BH is equal to F. Again, because A is equal to AC, constant, the triangle ACH is isosceles, therefore the angle ACH is equal to AHCV, but ACH is greater than BCH, therefore AHC is greater than BCH, much more is the angle BHC greater than BCH, and the greater angle is subtended by the greater side 19. Therefore BC is greater than BH, but BH has been proved to be equal to F, therefore BC is greater than F. The concluding part of this proposition may be proved without joining CH, thus BG plus GH BHXX, AG plus GC ACXX, therefore BC plus ABH plus AC, but A equals AC, constant, therefore BC is BH. Or thus, bisect the angle CAH by AO. Join O. Now in the SCAO, how we have the sides CA, AO in one equal to the sides A, AO in the other, and the contained angles equal, therefore the base OC is equal to the base O4, to each add BO, and we have BC equal to the sum of BO, O, but the sum of BO, O is greater than BHXX. Therefore BC is greater than BH, that is, greater than F. Exercises. 1. Prove this proposition by making the angle ABH to the left of AB. 2. Prove that the angle BCA is greater than EFD. Prop. XXV theorem. If two triangles, ABC, DEF, have two sides, AB, AC, of one respectively equal to two sides, D, DF, of the other, but the base, BC, of one greater than the base, F, of the other, the angle, A, contained by the sides of that which has the greater base is greater than the angle, D, contained by the sides of the other. Democrat if the angle A be not greater than D, it must be either equal to it or less than it. We shall examine each case 1. If A were equal to D, the triangles ABC, DEF would have the two sides of AC of one respectively equal to the two sides D, DF of the other, and the angle A contained by the two sides of one equal to the angle D contained by the two sides of the other. Henceforth, BC would be equal to F, but BC is, by hypothesis, greater than F, hence the angle A is not equal to the angle D2. If A were less than D, then D would be greater than A, and the triangles DEF, ABC would have the two sides D, DF of one respectively equal to the two sides of AC of the other, and the angle D contained by the two sides of one greater than the angle A contained by the two sides of the other. Hence XXIV. F would be greater than BC, but F, HIP, is not greater than BC. Therefore A is not less than D, and we have proved that it is not equal to it, therefore it must be greater. Or thus, directly, construct the triangle AC, whose three sides AG, GC, CA shall be respectively equal to the three sides D, F, FD of the triangle DEF XXII. Join BG. Then because BC is greater than F, BC is greater than CG. Hence 18 the angle BGC is greater than GBC, and make XXIII, the angle BGH equal to GBH, and join A. Then 6. BH is equal to GH. Therefore the triangles ABH, AC have the sides AB, A of one equal to the sides AG, A of the other, and the base BH equal to GH. Therefore 8 the angle BA is equal to GA. Hence the angle BAC is greater than CAG, and therefore greater than EDF. Exercise. Demonstrate this proposition directly by cutting off from BC a part equal to F. Prop. XXVI theorem. If two triangles, ABC, DEF, have two angles, B, C, of one equal respectively to two angles, E, F, of the other, and a side of one equal to a side similarly placed with respect to the equal angles of the other, the triangles are equal in every respect. Democrat. This proposition breaks up into two according as the sides given to be equal are the sides adjacent to the equal angles, namely BC and F, or those opposite equal angles. 1. Let the equal sides be BC and F, then if to be not equal to AB, suppose GE to be equal to it. Join GF, then the triangles ABC, GEF have the sides AB, BC of one respectively equal to the sides GE, F of the other, and the angle ABC equal to the angle GEF, HIP, therefore for the angle ACB is equal to the angle GFE, but the angle ACB is, HIP, equal to DFE, hence GFE is equal to DFE a part equal to the whole, which is absurd, therefore AB and A are not unequal, that is, they are equal. Consequently the triangles ABC, DEF have the sides AB, BC of one respectively equal to the sides DE, F of the other, and the contained angles ABC and DEF equal, therefore for AC is equal to DF, and the angle BAC is equal to the angle EDF. 2. Let the sides given to be equal be AB and A, it is required to prove that BC is equal to F, and AC to DF. If BC be not equal to F, suppose BG to be equal to it. Join AG. Then the triangles ABG, DEF have the two sides AB, BG of one respectively equal to the two sides DE, F of the other, and the angle ABG equal to the angle DEF, therefore for the angle AGB is equal to DFE, but the angle ACB is equal to DFE, HIP. Hence, axiom I, the angle AGB is equal to ACB, that is, the exterior angle of the triangle AC is equal to the interior and non-adjacent angle, which 16 is impossible. Hence BC must be equal to F, and the same as in 1, AC is equal to DF, and the angle BAC is equal to the angle EDF. This proposition, together with 4 and 8, includes all the cases of the congruence of two triangles. Part I may be proved immediately by superposition. For it is evident if ABC be applied to DEF, so that the point B shall coincide with E, and the line BC with F, since BC is equal to F, the point C shall coincide with F, and since the angles B, C are respectively equal to the angles E, F, the lines BA, CA shall coincide with ED and FD. Hence the triangles are congruent. DEF. If every point on a geometrical figure satisfies an assigned condition, that figure is called the locus of the point satisfying the condition. Thus, for example, a circle is the locus of a point whose distance from the center is equal to its radius. Exercises. 1. The extremities of the base of an isosceles triangle are equally distant from any point in the perpendicular from the vertical angle on the base. 2. If the line which bisects the vertical angle of a triangle also bisects the base, the triangle is isosceles. 3. The locus of a point which is equally distant from two fixed lines is the pair of lines which bisect the angles made by the fixed lines. 4. In a given right line find a point such that the perpendiculars from it on two given lines may be equal. State also the number of solutions. 5. If two right-angled triangles have equal hypotenuses, and an acute angle of one equal to an acute angle of the other, they are congruent. 6. If two right-angled triangles have equal hypotenuses, and a side of one equal to a side of the other, they are congruent. 7. The bisectors of the three internal angles of a triangle are concurrent. 8. The bisectors of two external angles and the bisector of the third internal angle are concurrent. 9. Through a given point draw a right line, such that perpendiculars on it from two given points on opposite sides may be equal to each other. 10. Through a given point draw a right line intersecting two given lines, and forming an isosceles triangle with them. Parallel lines. DEFI. If two right lines in the same plane be such that, when produced indefinitely, they do not meet at any finite distance, they are said to be parallel. DEF2. A parallelogram is a quadrilateral, both pairs of whose opposite sides are parallel. DEF3. The right line joining either pair of opposite angles of a quadrilateral is called a diagonal. DEF4. If both pairs of opposite sides of a quadrilateral be produced to meet, the right line joining their points of intersection is called its third diagonal. DEFV. A quadrilateral which has one pair of opposite sides parallel is called a trapezium. DEF6. If from the extremities of one right line perpendiculars be drawn to another, the intercept between their feet is called the projection of the first line on the second. DEF7. When a right line intersects two other right lines in two distinct points, it makes with them 8 angles, which have received special names in relation to one another. Thus, in the figure 1, 2, 7, 8 are called exterior angles, 3, 4, 5, 6, interior angles. Again, 4, 6, 3, 5 are called alternate angles. Lastly, 1, 5, 2, 6, 3, 8, 4, 7 are called corresponding angles. Prop. XXVII theorem. If a right line, F, intersecting two right lines, AB, CD, makes the alternate angles, AEF, EFD, equal to each other, these lines are parallel. Democrat. If AB and CD are not parallel, they must meet, if produced, at some finite distance. If possible, let them meet in G, then the figure EGF is a triangle, and the angle AEF is an exterior angle, and EFD a non-adjacent interior angle. Hence 16. AEF is greater than EFD, but it is also equal to it, HIP, that is, both equal and greater, which is absurd. Hence AB and CD are parallel. Or thus, bisect F in O, turn the whole figure round O as a center, so that F shall fall on itself, then because OE equals of, the point E shall fall on F, and because the angle AEF is equal to the angle EFD, the line EA will occupy the place of FD, and the line FD the place of EA, therefore the lines AB, CD interchange places, and the figure is symmetrical with respect to the point O. Hence, if AB, CD meet on one side of O, they must also meet on the other side, but two right lines cannot enclose a space, axiom X, therefore they do not meet at either side. Hence they are parallel. Prop. XXVII theorem. If a right line, F, intersecting two right lines, AB, CD, makes the exterior angle, EGB, equal to its corresponding interior angle, GHD, or makes two interior angles, BGH, GHD, on the same side equal to two right angles, the two right lines are parallel. Democrat 1. Since the lines AB, F intersect, the angle AC is equal to EGB 15, but EGB is equal to GHD, HIP, therefore AC is equal to GHD, and they are alternate angles. Hence XXVII. AB is parallel to CD. 2. Since AC and BGH are adjacent angles, their sum is equal to two right angles 13, but the sum of BGH and GHD is two right angles, HIP, therefore rejecting the angle BGH we have AC equal GHD, and they are alternate angles, therefore AB is parallel to CD XXVII. Prop. XXIX theorem. If a right line, F, intersect two parallel right lines, AB, CD, it makes one. The alternate angles, AC GHD, equal to one another, 2. The exterior angle, EGB, equal to the corresponding interior angle, GHD, 3. The two interior angles, BGH, GHD, on the same side equal to two right angles. Democrat if the angle AC be not equal to GHD, one must be greater than the other. Let AC be the greater, to each add BGH, and we have the sum of the angles AC, BGH greater than the sum of the angles BGH, GHD, but the sum of AC, BGH is two right angles, therefore the sum of BGH, GHD is less than two right angles, and therefore, axiom 12, the lines of CD, if produced, will meet at some finite distance, but since they are parallel, HIP, they cannot meet at any finite distance. Hence the angle AC is not unequal to GHD, that is, it is equal to it. 2. Since the angle EGB is equal to AC 15, and GHD is equal to AC 1, EGB is equal to GHD, axiom I. 3. Since AC is equal to GHD, 1, add hemoglobin to each, and we have the sum of the angles AC, hemoglobin equal to the sum of the angles GHD, hemoglobin, but the sum of the angles AC, hemoglobin 13 is two right angles, therefore the sum of the angles BGH, GHD is two right angles. Exercises. 1. Demonstrate both parts of PROPXXVII without using PROPXXVII. 2. The parts of all perpendiculars to two parallel lines intercepted between them are equal. 3. If ACD, BCD be adjacent angles, any parallel to AB will meet the bisectors of these angles in points equally distant from where it meets CD. 4. If through the middle point O of any right line terminated by two parallel right lines any other secant be drawn, the intercept on this line made by the parallels is bisected in O5. Two right lines passing through a point equidistant from two parallels intercept equal portions on the parallels. 6. The perimeter of the parallelogram, formed by drawing parallels to two sides of an equilateral triangle from any point in the third side, is equal to twice the side. 7. If the opposite sides of a hexagon be equal and parallel, its diagonals are concurrent. 8. If two intersecting right lines be respectively parallel to two others, the angle between the former is equal to the angle between the latter. 4. If AB, AC be respectively parallel to D, DF, and if AC, D meet in G, the angles A, D are each equal to GXXIX. Prop. XXX theorem. If two right lines, AB, CD, be parallel to the same right line, F, they are parallel to one another. Democrat draw any secant GHK. Then since AB and F are parallel, the angle AC is equal to GHFXXIX. In like manner the angle GHF is equal to HKDXXIX. Therefore the angle AGK is equal to the angle GKD, axiom I. Hence XXVII. AB is parallel to CD. Prop. XXXI problem. Through a given point, C, to draw a right line parallel to a given right line. Solution: take any point D in AB. Join CD, post I, and make the angle DCF equal to the angle ADCXXII. The line CE is parallel to AB XXVII. Exercises. 1. Given the altitude of a triangle and the base angles, construct it. 2. From a given point draw to a given line a line making with it an angle equal to a given angle. Show that there will be two solutions. 3. Prove the following construction for trisecting a given line of. Describe an equilateral ABC. Bisect the angles A, B by the lines AD, BD, meeting in D, through D draw parallels to AC, BC, meeting of in E, F, E, F are the points of trisection of a B. 4. Inscribe a square in a given equilateral triangle, having its base on a given side of the triangle. 5. Draw a line parallel to the base of a triangle so that it may be 1. Equal to the intercept it makes on one of the sides from the extremity of the base, 2. Equal to the sum of the two intercepts on the sides from the extremities of the base, 3. Equal to their difference. Show that there are two solutions in each case. 6. Through two given points in two parallel lines draw two lines forming a lozenge with the given parallels. 7. Between two lines given in position place a line of given length which shall be parallel to a given line. Show that there are two solutions. Prop. XXXII theorem. If any side, AB, of a triangle, ABC, be produced, to D, the external angle, CBD, is equal to the sum of the two internal non-adjacent angles, A, C, and the sum of the three internal angles is equal to two right angles. Democrat draw B parallel to AC XXXI. Now since BC intersects the parallels B, AC, the alternate angles EBC, ACB are equal XXIX. Again, since AB intersects the parallels B, AC, the angle EBD is equal to BAC XXIX, hence the whole angle CBD is equal to the sum of the two angles ACB, BAC, to each of these add the angle ABC and we have the sum of CBD, ABC equal to the sum of the three angles ACB, BAC, ABC, but the sum of CBD, ABC is two right angles 13, hence the sum of the three angles ACB, BAC, ABC is two right angles. COR1 If a right-angled triangle be isosceles, each base angle is half a right angle. COR2 If two triangles have two angles in one respectively equal to two angles in the other, their remaining angles are equal. COR3 Since a quadrilateral can be divided into two triangles, the sum of its angles is equal to four right angles. COR4 If a figure of n sides be divided into triangles by drawing diagonals from any one of its angles there will be, n2, triangles, hence the sum of its angles is equal to, n2, right angles. COR5 If all the sides of any convex polygon be produced, the sum of the external angles is equal to four right angles. COR6 Each angle of an equilateral triangle is 2/3 of a right angle. COR7 If one angle of a triangle be equal to the sum of the other two, it is a right angle. COR8 Every right-angled triangle can be divided into two isosceles triangles by a line drawn from the right angle to the hypotenuse. Exercises. 1. Trisect a right angle. 2. Any angle of a triangle is obtuse, right, or acute, according as the opposite side is greater than, equal to, or less than, twice the median drawn from that angle. 3. If the sides of a polygon of n sides be produced, the sum of the angles between each alternate pair is equal to 2, and 4, right angles. 4. If the line which bisects the external vertical angle be parallel to the base, the triangle is isosceles. 5. If two right-angled SABC, ABD be on the same hypotenuse of B, and the vertices C and D be joined, the pair of angles subtended by any side of the quadrilateral thus formed are equal. 6. The three perpendiculars of a triangle are concurrent. 7. The bisectors of two adjacent angles of a parallelogram are at right angles. 8. The bisectors of the external angles of a quadrilateral form a circumscribed quadrilateral, the sum of whose opposite angles is equal to two right angles. 9. If the three sides of one triangle be respectively perpendicular to those of another triangle, the triangles are equiangular. 10. Construct a right-angled triangle, being given the hypotenuse and the sum or difference of the sides. 11. The angles made with the base of an isosceles triangle by perpendiculars from its extremities on the equal sides are each equal to half the vertical angle. 12. The angle included between the internal bisector of one base angle of a triangle and the external bisector of the other base angle is equal to half the vertical angle. 13. In the construction of PROP 18. Prove that the angle DBC is equal to half the difference of the base angles. 14. If A, B, C denote the angles of A, prove that A plus B, B plus C, C plus A, will be the angles of A formed by any side and the bisectors of the external angles between that side and the other sides produced. Prop. XXXIII theorem. The right lines, AC, BD, which join the adjacent extremities of two equal and parallel right lines, AB, CD, are equal and parallel. Democrat join BC. Now since AB is parallel to CD, and BC intersects them, the angle ABC is equal to the alternate angle DCBXXIX. Again, since AB is equal to CD, and BC common, the triangles ABC, DCB have the sides of BC in one respectively equal to the sides DC, CB in the other, and the angles ABC, DCB contained by those sides equal, therefore for the base AC is equal to the base BD, and the angle ACB is equal to the angle CBD, but these are alternate angles, hence XXVII. AC is parallel to BD, and it has been proved equal to it. Therefore AC is both equal and parallel to BD. Exercises. 1. If two right lines of BC be respectively equal and parallel to two other right lines D, F, the right line AC joining the extremities of the former pair is equal to the right line DF joining the extremities of the latter. Two right lines that are equal and parallel have equal projections on any other right line, and conversely, parallel right lines that have equal projections on another right line are equal. 3. Equal right lines that have equal projections on another right line are parallel. 4. The right lines which join transversely the extremities of two equal and parallel right lines bisect each other. Prop. Thirsiv theorem. The opposite sides, AB, CD, AC, BD, and the opposite angles, A, D, B, C, of a parallelogram are equal to one another, and either diagonal bisects the parallelogram. Democrat join BC. Since AB is parallel to CD, and BC intersects them, the angle ABC is equal to the angle BCD XXIX. Again, since BC intersects the parallels AC, BD, the angle ACB is equal to the angle CBD, hence the triangles ABC, DCB have the two angles ABC, ACB in one respectively equal to the two angles BCD, CBD in the other, and the side BC common. Therefore XXVI. AB is equal to CD, and AC to BD, the angle BAC to the angle BDC, and the triangle ABC to the triangle BDC. Again, because the angle ACB is equal to CBD, and DCB equal to ABC, the whole angle ACD is equal to the whole angle ABD. COR1 If one angle of a parallelogram be a right angle, all its angles are right angles. COR2 If two adjacent sides of a parallelogram be equal, it is a lozenge. COR3 If both pairs of opposite sides of a quadrilateral be equal, it is a parallelogram. COR4 If both pairs of opposite angles of a quadrilateral be equal, it is a parallelogram. COR5 If the diagonals of a quadrilateral bisect each other, it is a parallelogram. COR6 If both diagonals of a quadrilateral bisect the quadrilateral, it is a parallelogram. COR7 if the adjacent sides of a parallelogram be equal, its diagonals bisect its angles. COR8 if the adjacent sides of a parallelogram be equal, its diagonals intersect at right angles. COR9 in a right-angled parallelogram the diagonals are equal. COR10 if the diagonals of a parallelogram be perpendicular to each other, it is a lozenge. COR11 if a diagonal of a parallelogram bisect the angles whose vertices it joins, the parallelogram is a lozenge. Exercises. 1. The diagonals of a parallelogram bisect each other. 2. If the diagonals of a parallelogram be equal, all its angles are right angles. 3. Divide a right line into any number of equal parts. 4. The right lines joining the adjacent extremities of two unequal parallel right lines will meet, if produced, on the side of the shorter parallel. 5. If two opposite sides of a quadrilateral be parallel but not equal, and the other pair equal but not parallel, its opposite angles are supplemental. 6. Construct a triangle, being given the middle points of its three sides. 7. The area of a quadrilateral is equal to the area of a triangle, having two sides equal to its diagonals, and the contained angle equal to that between the diagonals. Prop. XXXV theorem. Parallelograms on the same base, BC, and between the same parallels are equal. Democrat 1. Let the sides AD, DF of the parallelograms AC, BF opposite to the common base BC terminate in the same point D, then thirds of each parallelogram is double of the triangle BCD. Hence they are equal to one another. 2. Let the sides AD, F, figures, alpha, beta, opposite to BC not terminate in the same point. Then because ABCD is a parallelogram, AD is equal to BC thirds, and since BCEF is a parallelogram, F is equal to BC, therefore, C fig. Alpha, take away ed, and in fig. Beta, add ed, and we have in each case AE equal to DF, and BA is equal to CD thirds. Hence the triangles BA, CDF have the two sides BA, AE in one respectively equal to the two sides CD, DF in the other, and the angle BA XXIX equal to the angle CDF, henceforth the triangle BA is equal to the triangle CDF, and taking each of these triangles in succession from the quadrilateral BAFC, there will remain the parallelogram BCFE equal to the parallelogram BCDA. Or thus, the triangles AB, DCF have thirds of the sides AB, B in one respectively equal to the sides DC, CF in the other, and the angle AB equal to the angle DCF XXIX, EX8. Hence the triangle AB is equal to the triangle DCF, and, taking each away from the quadrilateral BAFC, there will remain the parallelogram BCFE equal to the parallelogram BCDA. Observation by the second method of proof the subdivision of the demonstration into cases is avoided. It is easy to see that either of the two parallelograms ABCD, EBCF can be divided into parts and rearranged so as to make it congruent with the other. This proposition affords the first instance in the elements in which equality which is not congruence occurs. This equality is expressed algebraically by the symbol equals, while congruence is denoted by, called also the symbol of identity. Figures that are congruent are said to be identically equal. Prop. 30 theorem. Parallelograms, BD, FH, on equal bases, BC, FG, and between the same parallels are equal. Democrat join B, CH. Now since FH is a parallelogram, FG is equal to A thirds, but BC is equal to FG, hip, therefore BC is equal to A, axiom I. Hence B, CH, which join their adjacent extremities, are equal and parallel, therefore BH is a parallelogram.
Again, since the parallelograms BD, BH are on the same base BC, and between the same parallels BC, they are equal XXXV. In like manner, since the parallelograms HB, HF are on the same base and between the same parallels BG, they are equal. Hence BD and FH are each equal to BH. Therefore, axiom I. BD is equal to FH. Exercise prove this proposition without joining B, CH prop. XXXVII theorem. Triangles, ABC, DBC, on the same base, BC, and between the same parallels, AD, BC, are equal. Democrat produce AD both ways. Draw B parallel to AC, and CF parallel to BDXXXI. Then the figures AEBC, DBCF are parallelograms, and since they are on the same base BC, and between the same parallels BC, F they are equal XXXV. Again, the triangle ABC is half the parallelogram AEBC thirsiv, because the diagonal AB bisects it. In like manner the triangle DBC is half the parallelogram DBCF, because the diagonal DC bisects it, and halves of equal things are equal, axiom 7. Therefore the triangle ABC is equal to the triangle DBC. Exercises. 1. If two equal triangles be on the same base, but on opposite sides, the right line joining their vertices is bisected by the base. 2. Construct a triangle equal in area to a given quadrilateral figure. 3. Construct a triangle equal in area to a given rectilineal figure. 4. Construct a lozenge equal to a given parallelogram, and having a given side of the parallelogram for base. 5. Given the base and the area of a triangle, find the locus of the vertex. 6. If through a point O, in the production of the diagonal AC of a parallelogram ABCD, any right line be drawn cutting the sides of BC in the points E, F, and ED, FD be joined, the triangle EFD is less than half the parallelogram. Prop. 38th theorem. Two triangles on equal bases and between the same parallels are equal. Democrat. By a construction similar to the last, we see that the triangles are the halves of parallelograms, on equal bases, and between the same parallels. Hence they are the halves of equal parallelograms 30. Therefore they are equal to one another. Exercises. 1. Every median of a triangle bisects the triangle. 2. If two triangles have two sides of one respectively equal to two sides of the other, and the contained angles supplemental, their areas are equal. 3. If the base of a triangle be divided into any number of equal parts, right lines drawn from the vertex to the points of division will divide the whole triangle into as many equal parts. 4. Right lines from any point in the diagonal of a parallelogram to the angular points through which the diagonal does not pass, and the diagonal, divide the parallelogram into 4 triangles which are equal, 2 by 2. 5. If one diagonal of a quadrilateral bisects the other, it also bisects the quadrilateral, and conversely. 6. If two SABC, ABD be on the same base AB, and between the same parallels, and if a parallel to AB meet the sides AC, BC in the point E, F, and the sides AD, BD in the point G, H, then F equals GH. 7. If instead of triangles on the same base we have triangles on equal bases and between the same parallels, the intercepts made by the sides of the triangles on any parallel to the bases are equal. 8. If the middle points of any two sides of a triangle be joined, the triangle so formed with the two half sides is 1/4 of the whole. 9. The triangle whose vertices are the middle points of two sides, and any point in the base of another triangle, is 1/4 of that triangle. 10. Bisect a given triangle by a right line drawn from a given point in one of the sides. 11. Trisect a given triangle by 3 right lines drawn from a given point within it. 12. Prove that any right line through the intersection of the diagonals of a parallelogram bisects the parallelogram. 13. The triangle formed by joining the middle point of one of the non-parallel sides of a trapezium to the extremities of the opposite side is equal to half the trapezium. Prop. 36 theorem. Equal triangles, BAC, BDC, on the same base, BC, and on the same side of it are between the same parallels. Democrat join AD. Then if AD be not parallel to BC, let AE be parallel to it, and let it cut BD in E join EC. Now since the triangles BEC, BAC are on the same base BC, and between the same parallels BC, AE, they are equal XXXVII, but the triangle BAC is equal to the triangle BDC, HIP. Therefore, axiom I, the triangle BEC is equal to the triangle BDC, that is, a part equal to the whole, which is absurd. Hence AD must be parallel to BC. Prop. XL theorem. Equal triangles, ABC, def, on equal bases, BC, F, which form parts of the same right line, and on the same side of the line, are between the same parallels. Democrat join AD. If AD be not parallel to BF, let AG be parallel to it. Join GF. Now since the triangles GEF and ABC are on equal bases BC, F, and between the same parallels BF, AG, they are equal 38th, but the triangle DEF is equal to the triangle ABC, HIP. Hence GEF is equal to DEF, axiom I. That is, a part equal to the whole, which is absurd. Therefore AD must be parallel to BF. DEF. The altitude of a triangle is the perpendicular from the vertex on the base. Exercises. 1. Triangles and parallelograms of equal bases and altitudes are respectively equal. 2. The right line joining the middle points of two sides of a triangle is parallel to the third, for the medians from the extremities of the base to these points will each bisect the original triangle. Hence the two triangles whose base is the third side and whose vertices are the points of bisection are equal. 3. The parallel to any side of a triangle through the middle point of another bisects the third. 4. The lines of connection of the middle points of the sides of a triangle divide it into four congruent triangles. 5. The line of connection of the middle points of two sides of a triangle is equal to half the third side. 6. The middle points of the four sides of a convex quadrilateral, taken in order, are the angular points of a parallelogram whose area is equal to half the area of the quadrilateral. 7. The sum of the two parallel sides of a trapezium is double the line joining the middle points of the two remaining sides. 8. The parallelogram formed by the line of connection of the middle points of two sides of a triangle, and any pair of parallels drawn through the same points to meet the third side, is equal to half the triangle. 9. The right line joining the middle points of opposite sides of a quadrilateral, and the right line joining the middle points of its diagonals, are concurrent. Prop. XLI theorem. If a parallelogram, ABCD, and a triangle, EBC, be on the same base, BC, and between the same parallels, the parallelogram is double of the triangle. Democrat join AC. The parallelogram ABCD is double of the triangle ABC thirsiv, but the triangle ABC is equal to the triangle EBC XXXVII. Therefore the parallelogram ABCD is double of the triangle EBC. COR1. If a triangle and a parallelogram have equal altitudes, and if the base of the triangle be double of the base of the parallelogram, the areas are equal. COR2. The sum of the triangles whose bases are two opposite sides of a parallelogram, and which have any point between these sides as a common vertex, is equal to half the parallelogram. Prop.
XLII problem. To construct a parallelogram equal to a given triangle, ABC, and having an angle equal to a given angle, D. Solution: bisect AB and E join EC, make the angle BEFXXIII equal to D. Draw CG parallel to AB XXXI, and BG parallel to F. EG is a parallelogram fulfilling the required conditions. Democrat because AE is equal to EB, constant, the triangle AEC is equal to the triangle EBC 38th, therefore the triangle ABC is double of the triangle EBC, but the parallelogram EG is also double of the triangle EBC SLE, because they are on the same base EB, and between the same parallels EB and CG. Therefore the parallelogram EG is equal to the triangle ABC, and it has, constant, the angle BEF equal to D. Hence EG is a parallelogram fulfilling the required conditions. Prop. Sliding theorem. The parallels, F, GH, through any point, K, in one of the diagonals, AC, of a parallelogram divided into four parallelograms, of which the two, BK, KD, through which the diagonal does not pass, and which are called the complements of the other two, are equal. Democrat because the diagonal bisects the parallelograms AC, AK, KC. We have thus of the triangle ADC equal to the triangle ABC, the triangle AHK equal to AEK, and the triangle KFC equal to the triangle KGC. Hence, subtracting the sums of the two last equalities from the first, we get the parallelogram DK equal to the parallelogram KB. COR1 if through a point K within a parallelogram ABCD lines drawn parallel to the sides make the parallelograms DK, KB equal, K is a point in the diagonal AC. COR2 the parallelogram BH is equal to AF, and BF to HC. COR2 supplies an easy demonstration of a fundamental proposition in statics. Exercises. 1. If F, GH be parallels to the adjacent sides of a parallelogram ABCD, the diagonals E, GF of two of the four S into which they divided and one of the diagonals of ABCD are concurrent. Democrat let E, GF meet in M, through M draw MP, MJ parallel to AB, BC. Produce AD, GH, BC to meet MP, and AB, F, DC to meet MJ. Now the complement of equals FJ, to each add the FL, and we get the figure OFL equals CJ. Again, the complement PH equals HK sliding, to each add the OC, and we get the PC equals figure OFL. Hence the PC equals CJ. Therefore they are about the same diagonal sliding, COR1. Hence AC produced will pass through M2. The middle points of the three diagonals AC, BD, F of a quadrilateral ABCD are collinear. Democrat complete the AEBG. Draw DH, CI parallel to AG, BG join IH, and produce, then AB, CD, IH are concurrent, EX1, therefore IH will pass through F join EI, E. Now 11, EX2, 3 the middle points of EI, E, F are collinear, but thirsive, EX1 the middle points of EI, E are the middle points of AC, BD. Hence the middle points of AC, BD, F are collinear. Prop. XLIV problem. To a given, right line, AB, to apply a parallelogram which shall be equal to a given triangle, C, and have one of its angles equal to a given angle, D. Solution: construct the parallelogram BEFG SLI equal to the given triangle C, and having the angle B equal to the given angle D, and so that its side B shall be in the same right line with AB. Through a draw a parallel to BGXXXI, and produce FG to meet it in H join HB. Then because HA and Phi are parallels, and HF intersects them, the sum of the angles AHF, HFE is 2 right angles XXIX, therefore the sum of the angles BHF, HFE is less than 2 right angles, and therefore, axiom 12, the lines HB, Phi, if produced, will meet as at K. Through K draw KL parallel to AB XXXI, and produce HA and GB to meet it in the points L and M. Then AM is a parallelogram fulfilling the required conditions. Democrat the parallelogram AM is equal to GE Slien, but GE is equal to the triangle C, constant, therefore AM is equal to the triangle C. Again, the angle ABM is equal to EBG 15, and EBG is equal to D, constant, therefore the angle ABM is equal to D, and AM is constructed on the given line, therefore it is the parallelogram required. Prop. XLV problem. To construct a parallelogram equal to a given rectilineal figure, ABCD, and having an angle equal to a given rectilineal angle, X. Solution: join BD. Construct a parallelogram e.g. SLI equal to the triangle ABD, and having the angle E equal to the given angle X, and to the right line GH apply the parallelogram HI equal to the triangle BCD, and having the angle GHK equal to X sliv, and so on for additional triangles if there be any. Then EI is a parallelogram fulfilling the required conditions. Democrat because the angles GHK, FEH are each equal to X, constant, they are equal to one another, to each add the angle GHE, and we have the sum of the angles GHK, GHE equal to the sum of the angles FEH, GHE, but since HG is parallel to F, and A intersects them, the sum of FEH, GHE is 2 right angles XXIX. Hence the sum of GHK, GHE is 2 right angles, therefore A, HK are in the same right line 14. Again, because GH intersects the parallels FG, EK, the alternate angles FGH, GHK are equal XXIX, to each add the angle HGI, and we have the sum of the angles FGH, HGI equal to the sum of the angles GHK, HGI, but since GI is parallel to HK, and GH intersects them, the sum of the angles GHK, HGI is equal to 2 right angles XXIX. Hence the sum of the angles FGH, HGI is 2 right angles, therefore FG and GI are in the same right line 14. Again, because EG and HI are parallelograms, F and K are each parallel to GH, hence XXX. F is parallel to K, and the opposite sides EK and Phi are parallel, therefore EI is a parallelogram, and because the parallelogram EG, constant, is equal to the triangle ABD, and HI to the triangle BCD, the whole parallelogram EI is equal to the rectilineal figure ABCD, and it has the angle E equal to the given angle X. Hence EI is a parallelogram fulfilling the required conditions. It would simplify problem SLIV, XLV, if they were stated as the constructing of rectangles, and in this special form they would be better understood by the student, since rectangles are the simplest areas to which others are referred. Exercises. 1. Construct a rectangle equal to the sum of 2 or any number of rectilineal figures. 2. Construct a rectangle equal to the difference of 2 given figures. Prop. XLVI problem. On a given right line, AB, to describe a square. Solution: erect AD at right angles to AB 11, and make it equal to AB 3. Through D draw DC parallel to AB XXXI, and through B draw BC parallel to AD, then AC is the square required. Democrat because AC is a parallelogram, AB is equal to CD thirsiv, but AB is equal to AD, constant, therefore AD is equal to CD, and AD is equal to BC thirsiv. Hence the four sides are equal, therefore AC is a lozenge, and the angle A is a right angle. Therefore AC is a square, DEF_XX. Exercises. 1. The squares on equal lines are equal, and, conversely, the sides of equal squares are equal. 2. The parallelograms about the diagonal of a square are squares. 3. If on the four sides of a square, or on the sides produced, points be taken equidistant from the four angles, they will be the angular points of another square, and similarly for a regular pentagon, hexagon, and C4. Divide a given square into 5 equal parts, namely, 4 right-angled triangles, and a square. Prop. Slay theorem. In a right-angled triangle, ABC, the square on the hypotenuse, AB, is equal to the sum of the squares on the other two sides, AC, BC. Democrat on the sides of BC, CA describes squares Sylvie. Draw CL parallel to AG. Join CG, BK. Then because the angle ACB is right, hip, and ACH is right, being the angle of a square, the sum of the angles ACB, ACH is two right angles, therefore BC, CH are in the same right line 14. In like manner AC, CD are in the same right line. Again, because BAG is the angle of a square, it is a right angle, in like manner CAK is a right angle. Hence BAG is equal to CAK, to each add BAC, and we get the angle CAG equal to CAB. Again, since BG and CK are squares, BA is equal to AG, and CA to AK. Hence the two triangles CAG, CAB have the sides CA, AG in one respectively equal to the sides CA, AB in the other, and the contained angles CAG, CAB also equal. Therefore the triangles are equal, but the parallelogram AL is double of the triangle CAG SLI, because they are on the same base AG, and between the same parallels AG and CL. In like manner the parallelogram A is double of the triangle CAB, because they are on the same base AK, and between the same parallels AK and BH, and since doubles of equal things are equal, axiom 6, the parallelogram AL is equal to A. In like manner it can be proved that the parallelogram BL is equal to BD. Hence the whole square AF is equal to the sum of the two squares A and BD. Or thus, let all the squares be made in reverse directions. Join CG, BK, and through C draw OL parallel to AG. Now, taking the BAC from the right S BAG, CAK, the remaining S CAG, BAC are equal. Hence the S CAG, BAC have the side CA equals AK, and AG equals AB, and the CAG equals BAC, therefore they are equal, and since the SAL, A are respectively the doubles of these triangles, they are equal. In like manner the SBL, BD are equal, hence the whole square AF is equal to the sum of the two squares A, BD. This proof is shorter than the usual one, since it is not necessary to prove that AC, CD are in one right line. In a similar way the proposition may be proved by taking any of the 8 figures formed by turning the squares in all possible directions. Another simplification of the proof would be got by considering that the point A is such that one of the S CAG, BAC can be turned round it in its own plane until it coincides with the other, and hence that they are congruent. Exercises. 1. The square on AC is equal to the rectangle AB.AO, and the square on BC equals AB.BO. 2. The square on CO equals AO.OB. 3. AC2BC2 equals AO2BO2. 4. Find a line whose square shall be equal to the sum of two given squares. 5. Given the base of a triangle and the difference of the squares of its sides, the locus of its vertex is a right line perpendicular to the base. 6. The transverse lines BK, CG are perpendicular to each other. 7. If EG be joined, its square is equal to AC2 plus 4BC2. 8. The square described on the sum of the sides of a right-angled triangle exceeds the square on the hypotenuse by 4 times the area of the triangle, see figure, SLV, EX3. More generally, if the vertical angle of a triangle be equal to the angle of a regular polygon of n sides, then the regular polygon of n sides, described on a line equal to the sum of its sides, exceeds the area of the regular polygon of n sides described on the base by n times the area of the triangle. 9. If AC and BK intersect in P, and through P a line be drawn parallel to BC, meeting up in Q, then CP is equal to PQ. 10. Each of the triangles AGK and BEF, formed by joining adjacent corners of the squares, is equal to the right-angled triangle ABC. 11. Find a line whose square shall be equal to the difference of the squares on two lines. 12. The square on the difference of the sides AC, CB is less than the square on the hypotenuse by 4 times the area of the triangle. 13. If AE be joined, the lines AE, BK, CL, are concurrent. 14. In an equilateral triangle, 3 times the square on any side is equal to 4 times the square on the perpendicular to it from the opposite vertex. 15. On B, a part of the side BC of a square ABCD, is described the square BEFG, having its side BG in the continuation of a B, it is required to divide the figure effect into 3 parts which will form a square. 16. 4 times the sum of the squares on the medians which bisect the sides of a right-angled triangle is equal to 5 times the square on the hypotenuse. 17. If perpendiculars be let fall on the sides of a polygon from any point, dividing each side into 2 segments, the sum of the squares on one set of alternate segments is equal to the sum of the squares on the remaining set. 18. The sum of the squares on lines drawn from any point to one pair of opposite angles of a rectangle is equal to the sum of the squares on the lines from the same point to the remaining pair. 19. Divide the hypotenuse of a right-angled triangle into 2 parts, such that the difference between their squares shall be equal to the square on one of the sides. 20. From the extremities of the base of a triangle perpendiculars are let fall on the opposite sides. Prove that the sum of the rectangles contained by the sides and their lower segments is equal to the square on the base. Prop. Slayat theorem. If the square on one side, of a triangle be equal to the sum of the squares on the remaining sides, AC, CB, the angle, C, opposite to that side is a right angle. Democrat erect CD at right angles to CB11, and make CD equal to CA3. Join BD. Then because AC is equal to CD, the square on AC is equal to the square on CD, to each add the square on CB, and we have the sum of the squares on AC, CB equal to the sum of the squares on CD, CB, but the sum of the squares on AC, CB is equal to the square on AB, HIP, and the sum of the squares on CD, CB is equal to the square on BD Slati. Therefore the square on AB is equal to the square on BD. Hence AB is equal to BD Slv, EX1. Again, because AC is equal to CD, constant, and CB common to the 2 triangles ACB, DCB, and the base AB equal to the base DB, the angle ACB is equal to the angle DCB, but the angle DCB is a right angle, constant. Hence the angle ACB is a right angle. The foregoing proof forms an exception to Euclid's demonstrations of converse propositions, for it is direct. The following is an indirect proof. If CB be not at right angles to AC, let CD be perpendicular to it. Make CD equal CB. Join AD. Then, as before, it can be proved that AD is equal to AB, and CD is equal to CB, constant. This is contrary to Prop 7. Hence the angle ACB is a right angle. Questions for examination on Book I1. What is geometry? 2. What is geometric magnitude? ANS. That which has extension in space. 3. Name the primary concepts of geometry. ANS points, lines, surfaces, and solids. 4. How may lines be divided? ANS into straight and curved. 5. How is a straight line generated? ANS. By the motion of a point which has the same direction throughout. 6. How is a curved line generated? ANS. By the motion of a point which continually changes its direction. 7. How may surfaces be divided? ANS into planes and curved surfaces. 8. How may a plane surface be generated? ANS. By the motion of a right line which crosses another right line, and moves along it without changing its direction. 9. Why has a point no dimensions? 10. Why has a line neither breadth nor thickness? 11. How many dimensions has a surface? 12. What is plane geometry? 13. What portion of plane geometry forms the subject of the first 6 books of Euclid's Elements? ANS. The geometry of the point, line, and circle. 14. What is the subject matter of Book I? 15. How many conditions are necessary to fix the position of a point in a plane? ANS. 2. For it must be the intersection of 2 lines, straight or curved. 16. Give examples taken from Book I. 17. In order to construct a line, how many conditions must be given? ANS. 2. As, for instance, 2 points through which it must pass, or 1 point through which it must pass and a line to which it must be parallel or perpendicular, and C18. What problems on the drawing of lines occur in Book I? ANS 2, 9, 11, 12, XXIII, XXXI, in each of which, except problem 2, there are 2 conditions. The direction in problem 2 is indeterminate. 19. How many conditions are required in order to describe a circle? ANS. 3, as, for instance, the position of the center, which depends on 2 conditions, and the length of the radius, compare post 3. 20. How is a proposition proved indirectly? ANS. By proving that its contradictory is false. 21. What is meant by the obverse of a proposition? 22. What propositions in Book I are the obverse respectively of propositions 4, v, 6, xxvii? 23. What proposition is an instance of the rule of identity? 24. What are congruent figures? 25. What other name is applied to them? ANS. They are said to be identically equal. 26. Mention all the instances of equality which are not congruence that occur in Book I. 27. What is the difference between the symbols denoting congruence and identity? 28. Classify the properties of triangles and parallelograms proved in Book I. 29. What proposition is the converse of PROPXXVI, Part I? 30. Define adjacent, exterior, interior, alternate angles respectively. 31. What is meant by the projection of one line on another? 32. What are meant by the medians of a triangle? 33. What is meant by the third diagonal of a quadrilateral? 34. Mention some propositions in Book I which are particular cases of more general ones that follow. 35. What is the sum of all the exterior angles of any rectilineal figure equal to? 36. How many conditions must be given in order to construct a triangle? ANS. 3, such as the 3 sides, or 2 sides and an angle, and see exercises on Book I. Any triangle is equal to the 4th part of that which is formed by drawing through each vertex a line parallel to its opposite side. 2. The 3 perpendiculars of the first triangle in question 1 are the perpendiculars at the middle points of the sides of the second triangle. 3. Through a given point draw a line so that the portion intercepted by the legs of a given angle may be bisected in the point. 4. The three medians of a triangle are concurrent. 5. The medians of a triangle divide each other in the ratio of 2:1. 6. Construct a triangle, being given two sides and the median of the third side. 7. In every triangle the sum of the medians is less than the perimeter, and greater than 3/4 of the perimeter. 8. Construct a triangle, being given a side and the two medians of the remaining sides. 9. Construct a triangle, being given the three medians. 10. The angle included between the perpendicular from the vertical angle of a triangle on the base, and the bisector of the vertical angle, is equal to half the difference of the base angles. 11. Find in two parallels two points which shall be equidistant from a given point, and whose line of connection shall be parallel to a given line. 12. Construct a parallelogram, being given two diagonals and a side. 13. The smallest median of a triangle corresponds to the greatest side. 14. Find in two parallels two points subtending a right angle at a given point and equally distant from it. 15. The sum of the distances of any point in the base of an isosceles triangle from the equal sides is equal to the distance of either extremity of the base from the opposite side. 16. The three perpendiculars at the middle points of the sides of a triangle are concurrent. Hence prove that perpendiculars from the vertices on the opposite sides are concurrent. CEX2. 17. Inscribe a lozenge in a triangle having for an angle one angle of the triangle. 18. Inscribe a square in a triangle having its base on a side of the triangle. 19. Find the locus of a point, the sum or the difference of whose distance from two fixed lines is equal to a given length. 20. The sum of the perpendiculars from any point in the interior of an equilateral triangle is equal to the perpendicular from any vertex on the opposite side. 21. The distance of the foot of the perpendicular from either extremity of the base of a triangle on the bisector of the vertical angle, from the middle point of the base, is equal to half the difference of the sides. 22. In the same case, if the bisector of the external vertical angle be taken, the distance will be equal to half the sum of the sides. 23. Find a point in one of the sides of a triangle such that the sum of the intercepts made by the other sides, on parallels drawn from the same point to these sides, may be equal to a given length. 24. If two angles have their legs respectively parallel, their bisectors are either parallel or perpendicular. 25. If lines be drawn from the extremities of the base of a triangle to the feet of perpendiculars let fall from the same points on either bisector of the vertical angle, these lines meet on the other bisector of the vertical angle. 26. The perpendiculars of a triangle are the bisectors of the angles of the triangle whose vertices are the feet of these perpendiculars. 27. Inscribe in a given triangle a parallelogram whose diagonals shall intersect in a given point. 28. Construct a quadrilateral, the four sides being given in magnitude, and the middle points of two opposite sides being given in position. 29. The bases of two or more triangles having a common vertex are given, both in magnitude and position, and the sum of the areas is given. Prove that the locus of the vertex is a right line. 30. If the sum of the perpendiculars let fall from a given point on the sides of a given rectilineal figure be given, the locus of the point is a right line. 31. ABC is an isosceles triangle whose equal sides are AB, AC. BC is any secant cutting the equal sides in B, C, so that AB plus AC equals AB plus AC. Prove that BC is greater than BC. 32. A, B are two given points, and P is a point in a given line L. Prove that the difference of AP and PB is a maximum when L bisects the angle APB, and that their sum is a minimum if it bisects the supplement. 33. Bisect a quadrilateral by a right line drawn from one of its angular points. 34. AD and BC are two parallel lines cut obliquely by AB, and perpendicularly by AC, and between these lines we draw bed, cutting AC in E, such that ED equals 2 AB, prove that the angle DBC is 1/3 of ABC. 35 If O be the point of concurrence of the bisectors of the angles of the triangle ABC, and if AO produced meet BC in D, and from O, OE be drawn perpendicular to BC, prove that the angle BOD is equal to the angle CO. 36 If the exterior angles of a triangle be bisected, the three external triangles formed on the sides of the original triangle are equiangular. 37 The angle made by the bisectors of two consecutive angles of a convex quadrilateral is equal to half the sum of the remaining angles, and the angle made by the bisectors of two opposite angles is equal to half the difference of the two other angles. 38 If in the construction of the figure, proposition I, F, kg be joined. 39. Given the middle points of the sides of a convex polygon of an odd number of sides, construct the polygon. 40 Trisect a quadrilateral by lines drawn from one of its angles. 41 Given the base of a triangle in magnitude and position and the sum of the sides, prove that the perpendicular at either extremity of the base to the adjacent side, and the external bisector of the vertical angle, meet on a given line perpendicular to the base. 42 The bisectors of the angles of a convex quadrilateral form a quadrilateral whose opposite angles are supplemental. If the first quadrilateral be a parallelogram, the second is a rectangle; if the first be a rectangle, the second is a square. 43 The middle points of the sides of BC, CA of a triangle are respectively D, E, F. DG is drawn parallel to BF to meet F. Prove that the sides of the triangle DCG are respectively equal to the three medians of the triangle ABC. 44 Find the path of a billiard ball started from a given point which, after being reflected from the four sides of the table, will pass through another given point. 45 If two lines bisecting two angles of a triangle and terminated by the opposite sides be equal, the triangle is isosceles. 46 State and prove the proposition corresponding to exercise 41, when the base and difference of the sides are given. 47 If a square be inscribed in a triangle, the rectangle under its side and the sum of the base and altitude is equal to twice the area of the triangle. 48 If AB, AC be equal sides of an isosceles triangle, and if BD be a perpendicular on AC, prove that BC2 equals 2AC.CD. 49 The sum of the equilateral triangles described on the legs of a right-angled triangle is equal to the equilateral triangle described on the hypotenuse. 50 Given the base of a triangle, the difference of the base angles, and the sum or difference of the sides, construct it. 51 Given the base of a triangle, the median that bisects the base, and the area, construct it. 52 If the diagonals AC, BD of a quadrilateral ABCD intersect in E, and be bisected in the points F, G, then 53. If squares be described on the sides of any triangle, the lines of connection of the adjacent corners are respectively, 1. The doubles of the medians of the triangle, 2. Perpendicular to them. Book 2. Theory of rectangles. Every proposition in the second book has either a square or a rectangle in its enunciation. Before commencing it, the student should read the following preliminary explanations. By their assistance it will be seen that this book, which is usually considered difficult, will be rendered not only easy, but almost intuitively evident. 1. As the linear unit is that by which we express all linear measures, so the square unit is that to which all superficial measures are referred. Again, as there are different linear units in use, such as in this country, inches, feet, yards, miles, and in France, meters, and their multiples or submultiples, so different square units are employed. 2. A square unit is the square described on a line whose length is the linear unit. Thus a square inch is the square described on a line whose length is an inch, A square foot is the square described on a line whose length is a foot, and c3. If we take a linear foot, describe a square on it, divide two adjacent sides each into 12 equal parts, and draw parallels to the sides, we evidently divide the square foot into square inches, and as there will manifestly be 12 rectangular parallelograms, each containing 12 square inches, the square foot contains 144 square inches. In the same manner it can be shown that a square yard contains 9 square feet, and so in general the square described on any line contains n2 times the square described on the nth part of the line. Thus, as a simple case, the square on a line is 4 times the square on its half. On account of this property the second power of a quantity is called its square, and, conversely, the square on a line of is expressed symbolically by ob2. For if a rectangular parallelogram be such that two adjacent sides contain respectively m and n linear units, by dividing one side into m and the other into n equal parts, and drawing parallels to the sides, the whole area is evidently divided into mn square units. Hence the area of the parallelogram is found by multiplying its length by its breadth, and this explains why we say, CDEF4, a rectangle is contained by any two adjacent sides, for if we multiply the length of one by the length of the other we have the area. Thus, if AD be two adjacent sides of a rectangle, the rectangle is expressed by AB.AD. Definitions. If a point C be taken in a line of the parts AC, CB are called segments, and C a point of division. 2. If C be taken in the line of produced, AC, CB are still called the segments of the line of, but C is called a point of external division. 3. A parallelogram whose angles are right angles is called a rectangle. 4. A rectangle is said to be contained by any two adjacent sides. Thus the rectangle ABCD is said to be contained by AB, AD, or by AB, BC, and CV. The rectangle contained by two separate lines such as AB and CD is the parallelogram formed by erecting a perpendicular to AB, at A, equal to CD, and drawing parallels. The area of the rectangle will be AB.CD. 6. In any parallelogram the figure which is composed of either of the parallelograms about a diagonal and the two complements CI, slyene is called a gnomon. Thus, if we take away either of the parallelograms AO, OC from the parallelogram AC, the remainder is called a gnomon. Prop. I theorem. If there be two lines, A, B, C, one of which is divided into any number of parts, BD, D, EC, the rectangle contained by the two lines, A, B, C, is equal to the sum of the rectangles contained by the undivided line, A, and the several parts of the divided line. Democrat erect BF at right angles to BCI, 11 and make it equal to A. Complete the parallelogram BK, DEFB. Through D, E draw DG, A parallel to BF. Because the angles at B, D, E are right angles, each of the quadrilaterals BG, DH, EK is a rectangle. Again, since A is equal to BF, constant, the rectangle contained by A and BC is the rectangle contained by BF and BC, DEFB, but BK is the rectangle contained by BF and BC. Hence the rectangle contained by A and BC is BK. In like manner the rectangle contained by A and BD is BG. Again, since A is equal to BF, constant, and BF is equal to DG ithursive, A is equal to DG. Hence the rectangle contained by A and A is the figure DH, DEFB. In like manner the rectangle contained by A and EC is the figure EK. Hence we have the following identities: rectangle contained by A and BD BG, A, DH, A, EC EK, A, BC BK. But BK is equal to the sum of BG, DH,
ek, I, axiom 9. Therefore the rectangle contained by A and BC is equal to the sum of the rectangles contained by A and BD, A and A and EC. If we denote the lines BD, D, EC by A, B, C, the proposition asserts that the rectangle contained by A, and A plus B plus C is equal to the sum of the rectangles contained by A and B, A and C, or, as it may be written, A plus B plus C, equals A plus AB plus AC. This corresponds to the distributive law in multiplication, and shows that rectangles in geometry, and products in arithmetic and algebra, are subject to the same rules. Illustration: suppose A to be 6 inches, BD, 5 inches, D, 4 inches, EC, 3 inches, then BC will be 12 inches, and the rectangles will have the following values: rectangle A.BC equals 6 times 12 equals 72 square inches. A.BD equals 6 times 5 equals 30, A.DE equals 6 times 4 equals 24, A.EC equals 6 times 3 equals 18, now the sum of the three last rectangles, viz. 30, 24, 18, is 72. Hence the rectangle A.BC equals A.BD plus A.DE plus A.EC. The second book is occupied with the relations between the segments of a line divided in various ways. All these can be proved in the most simple manner by algebraic multiplication. We recommend the student to make himself acquainted with the proofs by this method as well as with those of Euclid. He will thus better understand the meaning of each proposition. COR1 The rectangle contained by a line and the difference of two others is equal to the difference of the rectangles contained by the line and each of the others. COR2 The area of a triangle is equal to half the rectangle contained by its base and perpendicular. Democrat from the vertex C let fall the perpendicular CD. Draw F parallel to AB, and AE, BF each parallel to CD. Then AF is the rectangle contained by AB and BF, but BF is equal to CD. Hence AF equals AB.CD, but isly the triangle ABC is equals half the parallelogram AF. Therefore the triangle ABC is equals AB.CD. Prop. 2 Theorem. If a line, AB, be divided into any two parts, at C, the square on the whole line is equal to the sum of the rectangles contained by the whole and each of the segments, AC, CB. Democrat on AB describe the square ABDF isl and through C draw CE parallel to AFIXXXI. Now, since AB is equal to AF, the rectangle contained by AB and AC is equal to the rectangle contained by AF and AC, but AE is the rectangle contained by AF and AC. Hence the rectangle contained by AB and AC is equal to AE. In like manner the rectangle contained by AB and CB is equal to the figure CD. Therefore the sum of the two rectangles AB.AC, AB.CB is equal to the square on AB. Or thus, AB equals AC plus CB, and AB equals AB. Hence, multiplying, we get AB2 equals AB.AC plus AB.CB. This proposition is the particular case of I when the divided and undivided lines are equal, hence it does not require a separate demonstration. Prop. 3 Theorem. If a line, AB, be divided into two segments, at C, the rectangle contained by the whole line and either segment, CB, is equal to the square on that segment together with the rectangle contained by the segments. Democrat on BC describe the square BCDE isl. Through a draw AF parallel to CD, produce ED to meet AF in F. Now since CB is equal to CD, the rectangle contained by AC, CB is equal to the rectangle contained by AC, CD, but the rectangle contained by AC, CD is the figure AD. Hence the rectangle AC.CB is equal to the figure AD,
and the square on CB is the figure CE. Hence the rectangle AC.CB, together with the square on CB, is equal to the figure AE. Again, since CB is equal to B, the rectangle of .CB is equal to the rectangle AB.BE, but the rectangle AB.BE is equal to the figure AE. Hence the rectangle of .CB is equal to the figure AE. And since things which are equal to the same are equal to one another, the rectangle AC.CB, together with the square on CB, is equal to the rectangle of .CB. Or thus AB equals AC plus CB, CB equals CB. Hence AB.CB equals AC.CB plus CB2. PROP3 is the particular case of PROPI, when the undivided line is equal to a segment of the divided line. Prop. 4 theorem. If a line, AB, be divided into any two parts, at C, the square on the whole line is equal to the sum of the squares on the parts, AC, CB, together with twice their rectangle. Democrat on AB describe a square ABDE. Join EB, through C draw CF parallel to AE, intersecting B and G, and through G draw high parallel to AB. Now since AE is equal to AB, the angle AB is equal to AEBIV, but since B intersects the parallels AE, CF, the angle AEB is equal to CGBIXXIX. Hence the angle CBG is equal to CGB, and therefore I6. CG is equal to CB, but CG is equal to BI and CB to GI. Hence the figure CBIG is a lozenge, and the angle CBI is right. Hence, DEF it is a square. In like manner the figure EFGH is a square. Again, since CB is equal to CG, the rectangle AC.CB is equal to the rectangle AC.CG, but AC.CG is the figure AG, DEF4. Therefore the rectangle AC.CB is equal to the figure AG. Now the figures AG, GD are equal isline, being the complements about the diagonal of the parallelogram AD. Hence the parallelograms AG, GD are together equal to twice the rectangle AC.CB. Again, the figure HF is the square on HG, and HG is equal to AC. Therefore HF is equal to the square on AC, and CI is the square on CB, but the whole figure AD, which is the square on AB, is the sum of the four figures HF, CI, AG, GD. Therefore the square on AB is equal to the sum of the squares on AC, CB, and twice the rectangle AC.CB. Or thus, on AB describe the square ABDE, and cut off A, e.g., DF each equal to CB. Join CF, FG, GH, HC. Now the four SACH, CBF, FDG, GEH are evidently equal, therefore their sum is equal to 4 times the ACH, but the ACH is half the rectangle AC.A, ICOR2, that is, equal to half the rectangle AC.CB. Therefore the sum of the four triangles is equal to 2AC.CB. Again, the figure CFGH is a square islev, COR3, and equal to AC2 plus A2 islai. That is, equal to AC2 plus CB2. Hence the whole figure ABDE equals AC2 plus CB2 plus 2AC.CB. Or thus, AB equals AC plus CB. Squaring, we get AB2 equals AC2 plus 2AC.CB plus CB2. COR1 The parallelograms about the diagonal of a square are squares. COR2 The square on a line is equal to 4 times the square on its half. For let AB equals 2AC, then AB2 equals 4AC2. This COR may be proved by the first book thus, erect CD at right angles to AB, and make CD equals AC or CB. Join AD, DB. Then AD2 equals AC2 plus CD2 equals 2AC2 in like manner DB2 equals 2CB2, therefore AD2 plus DB2 equals 2AC2 plus 2CB2 equals 4AC2. But since the angle ADB is right, AD2 plus DB2 equals AB2, therefore AB2 equals 4AC2. COR3 If a line be divided into any number of parts, the square on the whole is equal to the sum of the squares on all the parts, together with twice the sum of the rectangles contained by the several distinct pairs of parts. Exercises 1. Prove proposition 4. By using propositions 2 and 3. 2. If from the vertical angle of a right-angled triangle a perpendicular be let fall on the hypotenuse, its square is equal to the rectangle contained by the segments of the hypotenuse. 3. From the hypotenuse of a right-angled triangle portions are cut off equal to the adjacent sides, prove that the square on the middle segment is equal to twice the rectangle contained by the extreme segments. 4. In any right-angled triangle the square on the sum of the hypotenuse and perpendicular, from the right angle on the hypotenuse, exceeds the square on the sum of the sides by the square on the perpendicular. 5. The square on the perimeter of a right-angled triangle is equal to twice the rectangle contained by the sum of the hypotenuse and one side, and the sum of the hypotenuse and the other side. Prop. V theorem. If a line, AB, be divided into two equal parts, at C, and also into two unequal parts, at D, the rectangle, AD.dB, contained by the unequal parts, together with the square on the part, CD, between the points of section, is equal to the square on half the line. Democrat on CB describe the square CBEF islev. Join BF. Through D draw DG parallel to CF, meeting BF in H. Through H draw KM parallel to AB, and through A draw AK parallel to CLIXXXI. The parallelogram CM is equal to diisline, COR2, but AL is equal to CMI30, because they are on equal bases AC, CB, and between the same parallels, therefore AL is equal to D, to each add CH, and we get the parallelogram A equal to the gnomon CMG, but A is equal to the rectangle AD.DH, and therefore equal to the rectangle AD.DB, since DH is equal to DB4, COR1, therefore the rectangle AD.DB is equal to the gnomon CMG, and the square on CD is equal to the figure LG. Hence the rectangle AD.DB, together with the square on CD, is equal to the whole figure CBEF, that is, to the square on CB. Or thus AD equals AC plus CD equals BC plus CD, DB equals BC CD, therefore AD.BD equals BC plus CD, BC CD, equals BC2 CD2. Hence AD.BD plus CD2 equals BC2. COR1 The rectangle AD.DB is the rectangle contained by the sum of the lines AC, CD, and their difference, and we have proved it equal to the difference between the square on AC and the square on CD. Hence the difference of the squares on two lines is equal to the rectangle contained by their sum and their difference. COR2 The perimeter of the rectangle A is equal to 2 AB, and is therefore independent of the position of the point D on the line AB, and the area of the same rectangle is less than the square on half the line by the square on the segment between D and the middle point of the line. Therefore, when D is the middle point, the rectangle will have the maximum area. Hence, of all rectangles having the same perimeter, the square has the greatest area. Exercises 1. Divide a given line so that the rectangle contained by its parts may have a maximum area. 2. Divide a given line so that the rectangle contained by its segments may be equal to a given square, not exceeding the square on half the given line. 3. The rectangle contained by the sum and the difference of two sides of a triangle is equal to the rectangle contained by the base and the difference of the segments of the base, made by the perpendicular from the vertex. For the difference of the sides of a triangle is less than the difference of the segments of the base, made by the perpendicular from the vertex. 5. The difference between the square on one of the equal sides of an isosceles triangle, and the square on any line drawn from the vertex to a point in the base, is equal to the rectangle contained by the segments of the base. 6. The square on either side of a right-angled triangle is equal to the rectangle contained by the sum and the difference of the hypotenuse and the other side. Prop. 6 Theorem. If a line, AB, be bisected, at C, and divided externally in any point, D, the rectangle, AD.BD, contained by the segments made by the external point, together with the square on half the line, is equal to the square on the segment between the middle point and the point of external division. Democrat on CD describe the square CDFE islev, and joined A, through B draw BHG parallel to CEIXXXI, meeting D in H, through H draw KLM parallel to AD, and through A draw AK parallel to CL. Then because AC is equal to CB, the rectangle AL is equal to CHI 30, but the complements CH, HF are equal isline, therefore AL is equal to HF. To each of these equals add CM and LG, and we get AM and LG equal to the square CDFE, but AM is equal to the rectangle AD.DM, and therefore equal to the rectangle AD.DB, since DB is equal to DM, also LG is equal to the square on CB, and CDFE is the square on CD. Hence the rectangle AD.DB, together with the square on CB, is equal to the square on CD. Or thus Democrat on CB describe the square CBEF islev. Join BF. Through D draw DG parallel to CF, meeting FB produced in H. Through H draw KM parallel to AB. Through A draw AK parallel to CLIXXXI. The parallelogram CM is equal to D isline, but AL is equal to CMI 30, because they are on equal bases AC, CB, and between the same parallels, therefore AL is equal to D. To each add CH, and we get the parallelogram A equal to the gnomon CMG, but A is equal to the rectangle AD.DH, and therefore equal to the rectangle AD.DB, since DH is equal to DB4, COR1, therefore the rectangle AD.DB is equal to the gnomon CMG, and the square on CB is the figure CE. Therefore the rectangle AD.DB, together with the square on CB, is equal to the whole figure LHGF, that is, equal to the square on LH or to the square on CD. Or thus AD equals AC plus CD equals CD plus CB, BD equals CD CB. Hence AD.DB equals CD plus CB, CD CB, equals CD2 CB2, therefore AD.DB plus CB2 equals CD2. Exercises. 1. Show that proposition 6 is reduced to proposition V by producing the line in the opposite direction. 2. Divide a given line externally, so that the rectangle contained by its segments may be equal to the square on a given line. 3. Given the difference of two lines and the rectangle contained by them, find the lines. 4. The rectangle contained by any two lines is equal to the square on half the sum, minus the square on half the difference. 5. Given the sum or the difference of two lines and the difference of their squares, find the lines. 6. If from the vertex C of an isosceles triangle a line CD be drawn to any point in the base produced, prove that CD2CB2 equals AD.DB. 7. Give a common enunciation which will include propositions V and 6. Prop. 7 Theorem. If a right line, AB, be divided into any two parts, at C, the sum of the squares on the whole line, AB, and either segment, CB, is equal to twice the rectangle, 2 AB.CB, contained by the whole line and that segment, together with the square on the other segment. Democrat onab describe the square ABDE. Join B. Through C draw CG parallel to AE, intersecting B in F. Through F draw HK parallel to AB. Now the square AD is equal to the three figures AK, FD, and GH, to each add the square CK, and we have the sum of the squares AD, CK equal to the sum of the three figures AK, CD, GH, but CD is equal to AK, therefore the sum of the squares AD, CK is equal to twice the figure AK, together with the figure GH. Now AK is the rectangle of .BK, but BK is equal to BC, therefore AK is equal to the rectangle of .BC, and AD is the square on AB, CK the square on CB, and GH is the square on HF, and therefore equal to the square on AC. Hence the sum of the squares on AB and BC is equal to twice the rectangle of .BC, together with the square on AC. Or thus, on AC describe the square ACDE. Produce the sides CD, DE, EA, and make each produced part equal to CB. Join BF, FG, GH, HB. Then the figure BFGH is a square isolav, EX3, and it is equal to the square on AC, together with the four equal triangles HAB, BCF, FDG, GEH. Now isolate the figure BFGH is equal to the sum of the squares on AB, that is, equal to the sum of the squares on AB, BC, and the sum of the four triangles is equal to twice the rectangle of .BC, for each triangle is equal to half the rectangle of .BC. Hence the sum of the squares on AB, BC is equal to twice the rectangle of .BC, together with the square on AC. Or thus, AC equals AB BC, therefore AC2 equals AB2 of .BC plus BC2, therefore AC2 plus 2 of .BC equals AB2 plus BC2. Comparison of 4 and 7. By 4, square on sum equals sum of squares plus twice rectangle. By 7, square on difference equals sum of squares twice rectangle. Cores from 4 and 7. 1 square on the sum of the squares, and the square on the difference of any two lines, are in arithmetical progression. 2 square on the sum plus square on the difference of any two lines equals twice the sum of the squares on the lines, props 9 and x. 3 the square on the square on the difference of any two lines equals 4 times the rectangle under lines, prop 8. Prop 8, theorem. If a line, AB, be divided into two parts, at C, the square on the sum of the whole line, AB, and either segment, BC, is equal to 4 times the rectangle contained by the whole line, AB, and that segment, together with the square on the other segment, AC. Democrat produce AB to D make BD equal to BC. On AD describe the square AEFD isolav. Joined A. Through C, B draw CH, BL parallel to AEIXXXI, and through K, I draw MN, PO parallel to AD. Since CO is the square on CD, and CK the square on CB, and CB is the half of CD, CO is equal to 4 times CK4, COR1. Again, since CG, GI are the sides of equal squares, they are equal isolav, COR1. Hence the parallelogram AG is equal to MII30. In like manner IL is equal to JF, but MI is equal to IL isline. Therefore the four figures AG, MI, IL, JF are all equal, hence their sum is equal to 4 times AG, and the square CO has been proved to be equal to 4 times CK. Hence the gnomon AOH is equal to 4 times the rectangle AK, that is, equal to 4 times the rectangle of .BC, since BC is equal to BK. Again, the figure pH is the square on pi, and therefore equal to the square on AC. Hence the whole figure AF, that is, the square on AD, is equal to 4 times the rectangle of dot BC, together with the square on AC. Or thus, produce BA to D, and make AD equals BC. On DB describe the square DBEF. Cut off BG, EI, FL each equal to BC. Through A and I draw lines parallel to DF, and through G and L, lines parallel to AB. Now it is evident that the four rectangles AG, GI, IL, LA are all equal, but AG is the rectangle AB.BG or AB.BC. Therefore the sum of the four rectangles is equal to 4 AB.BC. Again, the figure NP is evidently equal to the square on AC. Hence the whole figure, which is the square on BD, or the square on the sum of AB and BC, is equal to 4 AB.BC plus AC2. Or thus, AB plus BC equals AC plus 2BC, therefore, AB plus BC, 2 equals AC2 plus 4 AC.CB plus 4BC2 equals AC2 plus 4, AC plus CB, .CB equals AC2 plus 4 AB.BC. Direct sequence from V or 6. Since by V or 6, the rectangle contained by any two lines is equals the square on half their sum the square on half their difference, therefore 4 times the rectangle contained by any two lines equals the square on their sum the square on their difference. Direct sequence of 8. From 4 and 7. By 4, the square on the sum equals the sum of the squares plus twice the rectangle. By 7, the square on the difference equals the sum of the squares twice the rectangle. Therefore, by subtraction, the square on the sum the square on the difference equals 4 times the rectangle. Exercises. 1. In the figure isolate I if f, g, k be joined, prove f2 co2 equals, AB plus BO, 2. 2. Prove gk2 f2 equals 3 AB, AOBO. 3.11x3 occurs in the solution of the problem of the inscription of a regular polygon of 17 sides in a circle. See Note C. Given the difference of two lines equals r, and their rectangle equals 4r2, find the lines. Prop. 9 Theorem. If a line, AB, be bisected, at C, and divided into two unequal parts, at D, the sum of the squares on the unequal parts, AD, DB, is double the sum of the squares on half the line, AC, and on the segment, CD, between the points of section. Democrat erect CE at right angles to AB, and make it equal to AC or CB. Join AE, EB. Draw DF parallel to CE, and FG parallel to CD. Join AF. Because AC is equal to CE, and the angle ACE is right, the angle CEA is half a right angle. In like manner the angle CEB, CBE are half right angles, therefore the whole angle AEF is right. Again, because GF is parallel to CB, and CE intersects them, the angle EGF is equal to ECB, but ECB is right, constant, therefore EGF is right, and GEF has been proved to be half a right angle, therefore the angle GFE is half a right angle IXXXII. Therefore I6. GE is equal to GF. In like manner FD is equal to DB. Again, since AC is equal to CE, AC2 is equal to CE2, but AE2 is equal to AC2 plus CE2 isolate I. Therefore AE2 is equal to 2AC2. In like manner F2 is equal to 2GF2 or 2CD2. Therefore AE2 plus F2 is equal to 2AC2 plus 2CD2, but AE2 plus F2 is equal to AF2 isolate I. Therefore AF2 is equal to 2AC2 plus 2CD2. Again, since df is equal to db, df2 is equal to db2, to each add ad2, and we get ad2 plus df2 equal to ad2 plus db2, but ad2 plus df2 is equal to af2, therefore af2 is equal to ad2 plus db2, and we have proved af2 equal to 2ac2 plus 2cd2. Therefore ad2 plus db2 is equal to 2ac2 plus 2cd2. Or thus, ad equals ac plus cd, db equals ac cd. Square and add, and we get ad2 plus db2 equals 2ac2 plus 2cd2. Exercises. 1. The sum of the squares on the segments of a line of given length is a minimum when it is bisected. 2. Divide a given line internally, so that the sum of the squares on the parts may be equal to a given square, and state the limitation to its possibility. 3. If a line of B bisected in C and divided unequally in D, 4. Twice the square on the line joining any point in the hypotenuse of a right-angled isosceles triangle to the vertex is equal to the sum of the squares on the segments of the hypotenuse. 5. If a line be divided into any number of parts, the continued product of all the parts is a maximum, and the sum of their squares is a minimum when all the parts are equal. Prop. X theorem. If a line, a B, be bisected, at C, and divided externally, at D, the sum of the squares on the segments, AD, DB, made by the external point is equal to twice the square on half the line, and twice the square on the segment between the points of section. Democrat erect CE at right angles to a B, and make it equal to AC or CB. Join AE, EB. Draw DF parallel to CE, and produce EB. Now since DF is parallel to EC, the angle BDF is equals to BCEIXXIX, and I15 the angle DBF is equals to EBC, but the sum of the angles BCE, EBC is less than 2 right angles I17, therefore the sum of the angles BDF, DBF is less than 2 right angles, and therefore axiom 12 the lines EB, DF, if produced, will meet. Let them meet in F. Through F draw FG parallel to a B, and produce EC to meet it in G join AF. Because AC is equal to CE, and the angle ACE is right, the angle CEA is half a right angle. In like manner the angle CEB, CBE are half right angles, therefore the whole angle AEF is right. Again, because GF is parallel to CB, and GE intersects them, the angle EGF is equal to ECBIXXIX, but ECB is right, constant, therefore EGF is right, and GEF has been proved to be half a right angle, therefore IXXXII. GFE is half a right angle, and therefore I6. GE is equal to GF. In like manner FD is equal to DB. Again, since AC is equal to CE, AC2 is equal to CE2, but AE2 is equal to AC2 plus CE2 islai, therefore AE2 is equal to 2AC2. In like manner F2 is equal to 2GF2 or 2CD2, therefore AE2 plus F2 is equal to 2AC2 plus 2CD2, but AE2 plus F2 is equal to AF2 islai. Therefore AF2 is equal to 2AC2 plus 2CD2. Again, since DF is equal to DB, DF2 is equal to DB2, to each add AD2, and we get AD2 plus DF2 equal to AD2 plus DB2, but AD2 plus DF2 is equal to AF2, therefore AF2 is equal to AD2 plus DB2, and AF2 has been proved equal to 2AC2 plus 2CD2. Therefore AD2 plus DB2 is equal to 2AC2 plus 2CD2. Or thus AD equals CD plus AC, BD equals CDAC square and add, and we get AD2 plus BD2 equals 2CD2 plus 2AC2. The following enunciations include propositions 9. and x:1. The square on the sum of any two lines plus the square on their difference equal twice the sum of their squares. 2. The sum of the squares on any two lines it equal to twice the square on half the sum plus twice the square on half the difference of the lines. 3. If a line be cut into two unequal parts, and also into two equal parts, the sum of the squares on the two unequal parts exceeds the sum of the squares on the two equal parts by the sum of the squares of the two differences between the equal and unequal parts. Exercises. 1. Given the sum or the difference of any two lines, and the sum of their squares, find the lines. 2. The sum of the squares on two sides AC, CB of a triangle is equal to twice the square on half the base of B, and twice the square on the median which bisects a B. 3. If the base of a triangle be given both in magnitude and position, and the sum of the squares on the sides in magnitude, the locus of the vertex is a circle. 4. If in the ABC a point D in the base BC be such that prove that the middle point of AD is equally distant from B and C5. The sum of the squares on the sides of a parallelogram is equal to the sum of the squares on its diagonals. Prop. 11. Problem. To divide a given finite line, a B, into two segments, in H, so that the rectangle, AB.BH, contained by the whole line and one segment may be equal to the square on the other segment. Solution on a B. Describe the square ABDC isolated. Bisect AC in E join B. Produce EA to F, and make F equal to EB. On AF describe the square AFGH. H is the point required. Democrat produce GH to K. Then because CA is bisected in E, and divided externally in F, the rectangle CF.AF, together with the square on EA, is equal to the square on F6, but F is equal to EB, constant, therefore the rectangle CF.AF, together with EA2, is equal to EB2 that is isolated I equal to EA2 plus AB2. Rejecting EA2, which is common, we get the rectangle CF.AF equal to AB2. Again, since AF is equal to FG, being the sides of a square, the rectangle CF.AF is equal to CF.FG that is, to the figure CG, and AB2 is equal to the figure AD, therefore CG is equal to AD. Reject the part AK, which is common, and we get the figure FH equal to the figure HD, but HD is equal to the rectangle AB.BH, because BD is equal to AB, and FH is the square on A. Therefore the rectangle AB.BH is equal to the square on A. DEF. A line divided as in this proposition is said to be divided in extreme and mean ratio. COR1. The line CF is divided in extreme and mean ratio at a COR2 if from the greater segment CA of CF we take a segment equal to AF, it is evident that CA will be divided into parts respectively equal to A, HB. Hence, if a line be divided in extreme and mean ratio, the greater segment will be cut in the same manner by taking on it a part equal to the less, and the less will be similarly divided by taking on it a part equal to the difference, and so on, and COR3 let A be divided in extreme and mean ratio in C, then it is evident, COR2, that AC is greater than CB. Cut off CD equals CB, then, COR2, AC is cut in extreme and mean ratio at D, and CD is greater than AD. Next, cut off D equal to AD, and in the same manner we have D greater than EC, and so on. Now since CD is greater than AD, it is evident that CD is not a common measure of AC and CB, and therefore not a common measure of AB and AC. In like manner AD is not a common measure of AC and CD, and therefore not a common measure of AB and AC. Hence, no matter how far we proceed we cannot arrive at any remainder which will be a common measure of AB and AC. Hence, the parts of a line divided in extreme and mean ratio are incommensurable. Exercises. 1. Cut a line externally in extreme and mean ratio. 2. The difference between the squares on the segments of a line divided in extreme and mean ratio is equal to their rectangle. 3. In a right-angled triangle, if the square on one side be equal to the rectangle contained by the hypotenuse and the other side, the hypotenuse is cut in extreme and mean ratio by the perpendicular on it from the right angle. 4. If A be cut in extreme and mean ratio at C, prove that 1. Ob 2 plus BC2 equals 3AC2. 2. Ob plus BC, 2 equals 5AC2. 5. The three lines joining the pairs of points G, B, F, D, A, K, in the construction of proposition 11, are parallel. 6. If CH intersect B in O, AO is perpendicular to CH7. If CH be produced, it meets BF at right angles. 8. ABC is a right-angled triangle having AB equals 2AC, if A be made equal to the difference between BC and AC, AB is divided in extreme and mean ratio at H prop. 12. Theorem. In an obtuse angled triangle, ABC, the square on the side, AB, subtending the obtuse angle exceeds the sum of the squares on the sides, BC, CA, containing the obtuse angle, by twice the rectangle contained by either of them, BC, and its continuation, CD, to meet a perpendicular, AD, on it from the opposite angle. Democrat. Because BD is divided into two parts in C, we have BD2 equals BC2 plus CD2 plus 2BC. CD4 and AD2 equals AD2. Hence, adding, since isolatii BD2 plus AD2 equals AB2, and CD2 plus AD2 equals CA2, we get therefore AB2 is greater than BC2 plus CA2 by 2 BC. CD. The foregoing proof differs from Euclid's only in the use of symbols. I have found by experience that pupils more readily understand it than any other method. Or thus, by the first book, describe squares on the three sides. Draw AE, BF, CG perpendicular to the sides of the squares. Then it can be proved exactly as in the demonstration of isolatii, that the rectangle BG is equal to B, AG to AF, and CE to CF. Hence the sum of the two squares on AC, CB is less than the square on AB by twice the rectangle CE, that is, by twice the rectangle BC. CD. COR1. If perpendiculars from A and B to the opposite sides meet them in H and D, the rectangle AC.CH is equal to the rectangle BC.CD. Exercises. 1. If the angle ACB of a triangle be equal to twice the angle of an equilateral triangle, AB2 equals BC2 plus CA2 plus BC.CA. 2. ABCD is a quadrilateral whose opposite angles B and D are right, and AD, BC produced meet in E, prove AE.DE equals B.CE. 3. ABC is a right-angled triangle, and BD is a perpendicular on the hypotenuse AC, prove AB.DC equals BD.BC. 4. If a line of B divided in C so that AC2 equals 2CB2, prove that AB2 plus BC2 equals 2 AB.AC. 5. If AB be the diameter of a semicircle, find a point C in AB such that, joining C to a fixed point D in the circumference, and erecting a perpendicular CE meeting the circumference in E, CE2CD2 may be equal to a given square. 6. If the square of a line CD, drawn from the angle C of an equilateral triangle ABC to a point D in the side of produced, be equal to 2 AB2, prove that AD is cut in extreme and mean ratio at B prop. 13. Theorem. In any triangle, ABC, the square on any side subtending an acute angle, C, is less than the sum of the squares on the sides containing that angle, by twice the rectangle, BC, CD, contained by either of them, BC, and the intercept, CD, between the acute angle and the foot of the perpendicular on it from the opposite angle. Democrat because BC is divided into two segments in D, and AD2 equals AD2. Hence, adding, since CD2 plus AD2 equals AC2 islai, and BD2 plus AD2 equals AB2, we get BC2 plus AC2 equals AB2 plus 2 BC.CD. Therefore AB2 is less than BC2 plus AC2 by 2 BC.CD. Or thus, describe squares on the sides. Draw AE, BF, CG perpendicular to the sides, then, as in the demonstration of islai, the rectangle BG is equal to B, AG to AF, and CE to CF. Hence the sum of the squares on AC, CB exceeds the square on AB by twice CE, that is, by 2 BC.CD. Observation by comparing the proofs of the pairs of props 4 and 7, V and 6, 9, and X, 12, and 13, it will be seen that they are virtually identical. In order to render this identity more apparent, we have made some slight alterations in the usual proofs. The pairs of propositions thus grouped are considered in modern geometry not as distinct, but each pair is regarded as one proposition. Exercises. 1. If the angle C of the ACB be equal to an angle of an equilateral, AB2 equals AC2 plus BC2 AC.BC. 2. The sum of the squares on the diagonals of a quadrilateral, together with 4 times the square on the line joining their middle points, is equal to the sum of the squares on its sides. 3. Find a point C in a given line AB produced, so that AC2 plus BC2 equals 2AC.BC. Prop. 14. Problem. To construct a square equal to a given rectilineal figure, X. Solution. Construct IXLV the rectangle AC equal to X. Then, if the adjacent sides of BC be equal, AC is a square, and the problem is solved. If not, produce AB2E, and make B equal to BC, bisect AE in F, with F as center and Phi as radius, describe the semicircle H, produce CB to meet it in G. The square described on BG will be equal to X. Democrat join FG. Then because AE is divided equally in F and unequally in B, the rectangle AB.BE, together with FB2 is equal to Phi2V, that is, to FG2, but FG2 is equal to FB2 plus BG2 islai. Therefore the rectangle AB.BE plus FB2 is equal to FB2 plus BG2. Reject FB2, which is common, and we have the rectangle AB.BE equals BG2, but since B is equal to BC, the rectangle AB.BE is equal to the figure AC. Therefore BG2 is equal to the figure AC, and therefore equal to the given rectilineal figure, X. COR the square on the perpendicular from any point in a semicircle on the diameter is equal to the rectangle contained by the segments of the diameter. Exercises. 1. Given the difference of the squares on two lines and their rectangle, find the lines. 2. Divide a given line, so that the rectangle contained by another given line and one segment may be equal to the square on the other segment. Questions for examination on Book 2. 1. What is the subject matter of Book 2? ANS Theory of Rectangles. 2. What is a rectangle? A gnomon. 3. What is a square inch? A square foot? A square perch? A square mile? ANS. The square described on a line whose length is an inch, a foot, a perch, and C4. What is the difference between linear and superficial measurement? ANS linear measurement has but one dimension, superficial has two. 5. When is a line said to be divided internally? When externally. 6. How is the area of a rectangle found? 7. How is a line divided so that the rectangle contained by its segments may be a maximum? 8. How is the area of a parallelogram found?
9. What is the altitude of a parallelogram whose base is 65 meters and area 1430 square meters? 10. How is a line divided when the sum of the squares on its segments is a minimum? 11. The area of a rectangle is 108.60 square meters and its perimeter is 48.20 linear meters, find its dimensions. 12. What proposition in Book 2 expresses the distributive law of multiplication? 13. On what proposition is the rule for extracting the square root founded? 14. Compare isolatii. And 2. 12 and 13. 15. If the sides of a triangle be expressed by x2 plus 1, x2 1, and 2x linear units, respectively, prove that it is right-angled. 16. How would you construct a square whose area would be exactly an acre? Give a solution by isolatii. 17. What is meant by incommensurable lines? Give an example from Book 2. 18. Prove that a side and the diagonal of a square are incommensurable. 19. The diagonals of a lozenge are 16 and 30 meters respectively, find the length of a side. 20. The diagonal of a rectangle is 4.25 perches, and its area is 7.50 square perches, what are its dimensions? 21. The three sides of a triangle are 8, 11, 15, prove that it has an obtuse angle. 22. The sides of a triangle are 13, 14, 15, find the lengths of its medians, also the lengths of its perpendiculars, and prove that all its angles are acute. 23. If the sides of a triangle be expressed by m2 plus n2, m2 n2, and 2mn linear units, respectively, prove that it is right-angled. 24. If on each side of a square containing 5.29 square perches we measure from the corners respectively a distance of 1.5 linear perches, find the area of the square formed by joining the points thus found. Exercises on Book 2. 1. The squares on the diagonals of a quadrilateral are together double the sum of the squares on the lines joining the middle points of opposite sides. 2. If the medians of a triangle intersect in O, OB2 plus BC2 plus CA2 equals 3, OA2 plus OB2 plus OC2. 3. Through a given point O draw three lines OA, OB, OC of given lengths, such that their extremities may be collinear, and that OB equals BC. 4. If in any quadrilateral two opposite sides be bisected, the sum of the squares on the other two sides, together with the sum of the squares on the diagonals, is equal to the sum of the squares on the bisected sides, together with 4 times the square on the line joining the points of bisection. 5. If squares be described on the sides of any triangle, the sum of the squares on the lines joining the adjacent corners is equal to 3 times the sum of the squares on the sides of the triangle. 6. Divide a given line into two parts, so that the rectangle contained by the whole and one segment may be equal to any multiple of the square on the other segment. 7. If P be any point in the diameter above a semicircle, and CD any parallel chord, then 8. If A, B, C, D be four collinear points taken in order, 9. 3 times the sum of the squares on the sides of any pentagon exceeds the sum of the squares on its diagonals, by 4 times the sum of the squares on the lines joining the middle points of the diagonals. 10. In any triangle, 3 times the sum of the squares on the sides is equal to 4 times the sum of the squares on the medians. 11. If perpendiculars be drawn from the angular points of a square to any line, the sum of the squares on the perpendiculars from one pair of opposite angles exceeds twice the rectangle of the perpendiculars from the other pair by the area of the square. 12. If the base above a triangle be divided in D, so that MAD equals NBD, then 13. If the point D be taken in OB produced, so that MAD equals NDB, then 14. Given the base of a triangle in magnitude and position, and the sum or the difference of m times the square on one side and n times the square on the other side, in magnitude,
the locus of the vertex is a circle. 15. Any rectangle is equal to half the rectangle contained by the diagonals of squares described on its adjacent sides. 16. If A, B, C and C be any number of fixed points, and P a variable point, find the locus of P, if A P2 plus B P2 plus C P2 plus and C, be given in magnitude. 17. If the area of a rectangle be given, its perimeter is a minimum when it is a square. 18. If a transversal cut in the points A, C, B 3 lines issuing from a point D, prove that. 19. Upon the segments AC, CB of a line of equilateral triangles are described, prove that if D, D be the centers of circles described about these triangles, 6DD2 equals of 2 plus AC2 plus CB2. 20. If A, B, P denote the sides of a right-angled triangle about the right angle, and the perpendicular from the right angle on the hypotenuse, plus equals. 21. If, upon the greater segment above a line AC, divided in extreme and mean ratio, an equilateral triangle ABD be described, and CD joined, CD2 equals 2 of 2. 22. If a variable line, whose extremities rest on the circumference of two given concentric circles, subtend a right angle at any fixed point, the locus of its middle point is a circle. Book 3. Theory of the circle underscore 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 definitions. I equal circles are those whose radii are equal. This is a theorem, and not a definition. For if two circles have equal radii, they are evidently congruent figures, and therefore equal. From this way of proving this theorem props XXVI, XXIX follow as immediate inferences. 2. A chord of a circle is the line joining 2 points in its circumference. If the chord be produced both ways, the whole line is called a secant, and each of the parts into which a secant divides the circumference is called an arc, the greater the major conjugate arc, and the lesser the minor conjugate arc nucleum. 3. A right line is said to touch a circle when it meets the circle, and, being produced both ways, does not cut it. The line is called a tangent to the circle, and the point where it touches it the point of contact. In modern geometry, a curve is considered as made up of an infinite number of points, which are placed in order along the curve, and then the secant through two consecutive points is a tangent. Euclid's definition for a tangent is quite inadequate for any curve but the circle, and those derived from it by projection, the conic sections, and even for these the modern definition is better. 4. Circles are said to touch one another when they meet, but do not intersect. There are two species of contact: 1. When each circle is external to the other. 2. When one is inside the other. The following is the modern definition of curve contact: when two curves have 2, 3, 4, and c consecutive points common, they have contact of the first, second, third, and c orders. A segment of a circle is a figure bounded by a chord and one of the arcs into which it divides the circumference. 6. Chords are said to be equally distant from the center when the perpendiculars drawn to them from the center are equal. 7. The angle contained by two lines, drawn from any point in the circumference of a segment to the extremities of its chord, is called an angle in the segment. 8. The angle of a segment is the angle contained between its chord and the tangent at either extremity. A theorem is tacitly assumed in this definition, namely, that the angles which the chord makes with the tangent at its extremities are equal. We shall prove this further on. 9. An angle in a segment is said to stand on its conjugate arc x. Similar segments of circles are those that contain equal angles. 11. A sector of a circle is formed of two radii and the arc included between them. To a pair of radii may belong either of the two conjugate arcs into which their ends divide the circle nucleum. 12 concentric circles are those that have the same center. 13 points which lie on the circumference of a circle are said to be concyclic. 14 A cyclic quadrilateral is one which is inscribed in a circle. 15 It will be proper to give here an explanation of the extended meaning of the word angle in modern geometry. This extension is necessary in trigonometry, in mechanics in fact, in every application of geometry, and has been partly given in IDEF 9. Thus, if a line OA revolve about the point O, as in figures 1, 2, 3, 4, until it comes into the position OB, the amount of the rotation from OA to OB is called an angle. From the diagrams we see that in figure 1 it is less than 2 right angles, in figure 2 it is equal to 2 right angles, in figure 3 greater than 2 right angles, but less than 4, and in figure 4 it is greater than 4 right angles. The arrowheads denote the direction or sense, as it is technically termed, in which the line OA turns. It is usual to call the direction indicated in the above figures positive, and the opposite negative. A line such as OA, which turns about a fixed point, is called a ray, and then we have the following definition. 16. A ray which turns in the sense opposite to the hands of a watch describes a positive angle, and one which turns in the same direction as the hands, a negative angle. Prop. I problem. To find the center of a given circle, ADB. Solution: take any 2 points A, B in the circumference. Join a B. Bisect it in C. Erect CD at right angles to a B. Produce DC to meet the circle again in E. Bisect A in F. Then F is the center. Democrat if possible, let any other point G be the center. Join GA, GC, GB. Then in the triangles AC, BCG we have AC equal to CB, constant, CG common, and the base GA equal to GB, because they are drawn from G, which is, by hypothesis, the center, to the circumference. Hence I8 the angle AC is equal to the adjacent angle BCG, and therefore IDEF 13 each is a right angle, but the angle ACD is right, constant, therefore ACD is equal to AC apart equal to the whole, which is absurd. Hence no point can be the center which is not in the line DA. Therefore F, the middle point of DA, must be the center. The foregoing proof may be abridged as follows: because ED bisects AB at right angles, every point equally distant from the points A, B must lie in ED IXEX2, but the center is equally distant from A and B, hence the center must be in ED, and since it must be equally distant from E and D, it must be the middle point of D. COR1 The line which bisects any chord of a circle perpendicularly passes through the center of the circle. COR2 The locus of the centers of the circles which pass through two fixed points is the line bisecting at right angles that connecting the 2 points. COR3 If A, B, C be 3 points in the circumference of a circle, the lines bisecting perpendicularly the chords of B, C intersect in the center. Prop. 2 Theorem. If any 2 points, A, B, be taken in the circumference of a circle 1. The segment, AB, of the indefinite line through these points which lies between them falls within the circle. 2. The remaining parts of the line are without the circle. Democrat 1. Let C be the center. Take any point D in AB. Join CACD-CB. Now the angle ADC is I16 greater than ABC, but the angle ABC is equal to cab IV, because the triangle cab is isosceles, therefore the angle ADC is greater than CAD. Hence AC is greater than CD I19, therefore CD is less than the radius of the circle, consequently the point D must be within the circle. Note on IDEF XXIII. In the same manner every other point between A and B lies within the circle. 2. Take any point E in AB produced either way. Join CE. then the angle ABC is greater than AEC I16, therefore CAB is greater than AEC. Hence CE is greater than CA, and the point E is without the circle. We have added the second part of this proposition. The indirect proof given of the first part in several editions of Euclid is very inelegant. It is one of those absurd things which give many students a dislike to geometry. COR1 three collinear points cannot be concyclic. COR2 a line cannot meet a circle in more than 2 points. COR3 the circumference of a circle is everywhere concave towards the center prop. 3. Theorem. If a line, AB, passing through the center of a circle bisect a chord, CD, which does not pass through the center, it cuts it at right angles. 2. If it cuts it at right angles, it bisects it. Democrat 1. Let O be the center of the circle. Join OC, OD. Then the triangle CEO, DEO have CE equal to ED, HIP, EO common, and OC equal to OD, because they are radii of the circle, hence I8 the angle CEO is equal to DEO, and they are adjacent angles. Therefore IDEF 13 each is a right angle. Hence AB cut CD at right angles. 2. The same construction being made, because OC is equal to OD, the angle OCD is equal to ODCIV, and CEO is equal to DEO, HIP, because each is right. Therefore the triangle CEO, DEO have two angles in one respectively equal to two angles in the other, and the side EO common. Hence IXXVI the side CE is equal to ED. Therefore CD is bisected in E2. May be proved as follows: OC2 equals OE2 plus EC2 islai, and OD2 equals OE2 plus ED2, but OC2 equals OD2, OE2 plus EC2 equals OE2 plus ED2. Hence EC2 equals ED2, and EC equals ED. Observation: the three theorems, namely, COR1, PROPI, and parts 1, 2, of PROP3, are so related, that any one being proved directly, the other two follow by the rule of identity. COR1 the line which bisects perpendicularly one of two parallel chords of a circle bisects the other perpendicularly. COR2 the locus of the middle points of a system of parallel chords of a circle is the diameter of the circle perpendicular to them all. COR3 if a line intersect two concentric circles, its intercepts between the circles are equal. COR4 the line joining the centers of two intersecting circles bisects their common chord perpendicularly. Exercises. 1. If a chord of a circle subtend a right angle at a given point, the locus of its middle point is a circle. 2. Every circle passing through a given point, and having its center on a given line, passes through another given point. 3. Draw a chord in a given circle which shall subtend a right angle at a given point, and be parallel to a given line. Prop. 4. Theorem. Two chords of a circle, AB, CD, which are not both diameters cannot bisect each other, though either may bisect the other. Democrat let O be the center. Let AB, CD intersect in E, then since AB, CD are not both diameters, join OE. If possible let AE be equal to EB, and CE equal to ED. Now, since OE passing through the center bisects AB, which does not pass through the center, it is at right angles to it, therefore the angle AEO is right. In like manner the angle CEO is right. Hence AEO is equal to CEO, that is, a part equal to the whole, which is absurd. Therefore AB and CD do not bisect each other. COR if two chords of a circle bisect each other, they are both diameters. Prop. V theorem. If two circles, ABC, ABD, cut one another in any point, A, they are not concentric. Democrat if possible let them have a common center at O join OA, and draw any other line OD, cutting the circles in C and D respectively. Then because O is the center of the circle ABC, OA is equal to OC. Again, because O is the center of the circle ABD, OA is equal to OD. Hence OC is equal to OD, a part equal to the whole, which is absurd. Therefore the circles are not concentric. Exercises. 1. If two non-concentric circles intersect in one point, they must intersect in another point. 4. Let O be the centers, A the point of intersection, from A let fall the AC on the line OO. Produce AC to B, making BC equals CA, then B is another point of intersection. Two circles cannot have 3 points in common without wholly coinciding. Prop. 6 Theorem. If one circle, ABC, touch another circle, AD, internally in any point, A, it is not concentric with it. Democrat. If possible, let the circles be concentric, and let O be the center of each. Join OA, and draw any other line OD, cutting the circles in the points B, D respectively. Then because O is the center of each circle, HIP, OB, and OD are each equal to OA, therefore OB is equal to OD, which is impossible. Hence the circles cannot have the same center. Prop. 7 Theorem. If from any point, P, within a circle, which is not the center, lines, PA, PB, PC, and C, one of which passes through the center, be drawn to the circumference, then 1. The greatest is the line, PA, which passes through the center 2. The production, PE, of this in the opposite direction is the least. 3 of the others, that which is nearest to the line through the center is greater than every one more remote. 4. Any two lines making equal angles with the diameter on opposite sides are equal. 5. More than two equal right lines cannot be drawn from the given point, P, to the circumference. Democrat. 1. Let O be the center. Join OB. Now since O is the center, OA is equal to OB, to each add op, and we have AP equal to the sum of OB, op, but the sum of OB, op is greater than PBIXX. Therefore PA is greater than PB. 2. Join OD. Then IXX the sum of op, PD is greater than OD, but OD is equal to OEIDEF Therefore the sum of op, PD is greater than OE. Reject op, which is common, and we have PD greater than PE. 3. Join OC, then two triangles POB, POC have the side OB equal to OCIDEF and op common, but the angle POB is greater than POC, therefore IXXIV the base PB is greater than PC. In like manner PC is greater than PD4. Make at the center O the angle POF equal to POD. Join PF. Then the triangles POD, POF have the two sides OP, OD in one respectively equal to the sides OP, of in the other, and the angle POD equal to the angle POF, hence PD is equal to PFI4, and the angle OPD equal to the angle OPF. Therefore PD and PF make equal angles with the diameter. 5. A third line cannot be drawn from P equal to either of the equal lines PD, PF. If possible, let PG be equal to PD, then PG is equal to PF, that is, the line which is nearest to the one through the center is equal to the one which is more remote, which is impossible. Hence 3 equal lines cannot be drawn from P to the circumference. COR1. If two equal lines PD, PF be drawn from a point P to the circumference of a circle, the diameter through P bisects the angle DPF formed by these lines. COR2. If P be the common center of circles whose radii are PA, PB, PC, and C, then 1. The circle whose radius is the maximum line, PA, lies outside the circle AD, and touches it in ADEF4, 2. The circle whose radius is the minimum line, PE, lies inside the circle AD, and touches it in E3. A circle having any of the remaining lines, PD, as radius cuts it in 2 points, D, F. Observation Proposition 7 affords a good illustration of the following important definition. See sequel to Euclid, p13. If a geometrical magnitude varies its position continuously according to any law, and if it retains the same value throughout, it is said to be a constant, such as the radius of a circle revolving round the center, but if it goes on increasing for some time, and then begins to decrease, it is said to be a maximum at the end of the increase. Thus, in the foregoing figure, PA, supposed to revolve round P and meet the circle, is a maximum. Again, if it decreases for some time, and then begins to increase, it is a minimum at the commencement of the increase. Thus PE, supposed as before to revolve round P and meet the circle, is a minimum. Proposition 8. We'll give other illustrations. Prop. 8 theorem. If from any point, P, outside a circle, lines, PA, PB, PC, and C, be drawn to the concave circumference, then 1. The maximum is that which passes through the center 2. Of the others, that which is nearer to the one through the center is greater than the one more remote. Again, if lines be drawn to the convex circumference 3. The minimum is that whose production passes through the center 4. Of the others, that which is nearer to the minimum is less than one more remote. 5. From the given point, P, there can be drawn 2 equal lines to the concave or the convex circumference, both of which make equal angles with the line passing through the center 6. More than 2 equal lines cannot be drawn from the given point, P, to either circumference. Democrat 1. Let O be the center, join OB. Now since O is the center, OA is equal to OB, to each add op, and we have AP equal to the sum of OB, op, but the sum of OB, op is greater than BPIXX. Therefore AP is greater than BP2. Join OC, OD. The two triangles BOP, COP have the side OB equal to OC, and OP common, and the angle BOP greater than COP, therefore the base BP is greater than CPIXXIV. In like manner CP is greater than DP, and C3. Join of. Now in the triangle OFP the sum of the sides of FP is greater than OPIXX, but of is equal to OEIDEFXXX. Reject them, and FP will remain greater than EP4. Join OG, O. The two triangles GOP, FOP have two sides GO, OP in one respectively equal to two sides FO, OP in the other, but the angle GOP is greater than FOP, therefore IXXIV the base GP is greater than FP. In like manner HP is greater than GP. 5. Make the angle POI equal POFIXXIII. Join IP. Now the triangles IOP, FOP have two sides IO, OP in one respectively equal to two sides FO, OP in the other, and the angle IOP equal to FOP, constant, therefore I4. IP is equal to FP6. A third line cannot be drawn from P equal to either of the lines IP, FP. For if possible let PK be equal to PF, then PK is equal to pi, that is, one which is nearer to the minimum equal to one more remote, which is impossible. COR1 if pi be produced to meet the circle again in L, PL is equal to PB. COR2 if two equal lines be drawn from P to either the convex or concave circumference, the diameter through P bisects the angle between them, and the parts of them intercepted by the circle are equal. COR3 if P be the common center of circles whose radii are lines drawn from P to the circumference of HDE, then 1. The circle whose radius is the minimum line, PE, has contact of the first kind with a DEF4. 2. The circle whose radius is the maximum line, PA, has contact of the second kind. 3. A circle having any of the remaining lines, PF, as radius intersects HDE in 2 points, F, I. Prop. 9. Theorem. A point, P, within a circle, ABC, from which more than 2 equal lines, PA, PB, PC, and C, can be drawn to the circumference, is the center democrat. If P be not the center, let O be the center. Join up, and produce it to meet the circle in D and E, then D is the diameter, and P is a point in it which is not the center. Therefore 7. Only 2 equal lines can be drawn from P to the circumference, but 3 equal lines are drawn, HIP, which is absurd. Hence P must be the center. Or thus, since the lines AP, BP are equal, the line bisecting the angle APB 7. COR1 must pass through the center. In like manner the line bisecting the angle BPC must pass through the center. Hence the point of intersection of these bisectors, that is, the point P, must be the center. Prop. X theorem. If 2 circles have more than 2 points common, they must coincide. Democrat, let X be one of the circles, and if possible let another circle Y have 3 points, A, B, C, in common with X, without coinciding with it. Find P, the center of X. Join PA, PB, PC. Then since P is the center of X, the 3 lines PA, PB, PC are equal to one another. Again, since Y is a circle and P a point, from which 3 equal lines PA, PB, PC can be drawn to its circumference, P must be the center of Y. Hence X and Y are concentric, which V is impossible. COR2 circles not coinciding cannot have more than 2 points common. Compare I, axiom X, that 2 right lines not coinciding cannot have more than 1 point common. Prop. 11. Theorem. If one circle, CPD, touch another circle, APB, internally at any point P, the line joining the centers must pass through that point. Democrat, let O be the center of APB. Join up. I say the center of the smaller circle is in the line up. If not, let it be in any other position such as E. Join OE, EP, and produce OE through E to meet the circles in the points C, A. Now since E is a point in the diameter of the larger circle between the center and A, EA is less than EP7-2, but EP is equal to EC, HIP, being radii of the smaller circle. Hence EA is less than EC, which is impossible, consequently the center of the smaller circle must be in the line up. Let it be H, then we see that the line joining the centers passes through the point P. Or thus, since EP is a line drawn from a point within the circle APB to the circumference, but not forming part of the diameter through E, the circle whose center is E and radius EP cut 7, COR2 APB in P, but it touches it, HIP, also in P, which is impossible. Hence the center of the smaller circle CPD must be in the line up. Prop. 12. Theorem. If 2 circles, PCF, PDE, have external contact at any point P, the line joining their centers must pass through that point. Democrat, let A be the center of one of the circles. Join AP, and produce it to meet the second circle again in A. I say the center of the second circle is in the line PE. If not, let it be elsewhere, as at B. Join AB, intersecting the circles in C and D, and join BP. Now since A is the center of the circle PCF, AP is equal to AC, and since B is the center of the circle PDE, BP is equal to BD. Hence the sum of the lines AP, BP is equal to the sum of the lines AC, DB, but AB is greater than the sum of AC and DB, therefore AB is greater than the sum of AP, PB, that is, one side of a triangle greater than the sum of the other two, which IXX is impossible. Hence the center of the second circle must be in the line PE. Let it be G, and we see that the line through the centers passes through the point P. Or thus, since BP is a line drawn from a point without the circle PCF to its circumference, and when produced does not pass through the center, the circle whose center is B and radius BP must cut the circle PCF in P8, COR3, but it touches it, HIP, also in P, which is impossible. Hence the center of the second circle must be in the line PE. Observation propositions 11, 12, may both be included in one enunciation as follows: if two circles touch each other at any point, the centers and that point are collinear. And this latter proposition is a limiting case of the theorem given in proposition 3, COR4, that the line joining the centers of two intersecting circles bisects the common chord perpendicularly. Suppose the circle whose center is O and one of the points of intersection A to remain fixed, while the second circle turns round that point in such a manner that the second point of intersection B becomes ultimately consecutive to A, then, since the line OO always bisects AB, we see that when B ultimately becomes consecutive to A, the line OO passes through A. In consequence of the motion, the common chord will become in the limit a tangent to each circle, as in the second diagram Cum-Raus, Geometry Plane, page 57. COR1 if two circles touch each other, their point of contact is the union of two points of intersection. Hence a contact counts for two intersections. COR2 if two circles touch each other at any point, they cannot have any other common point. 4. Since two circles cannot have more than 2 points common x, and that the point of contact is equivalent to 2 common points, circles that touch cannot have any other point common. The following is a formal proof of this proposition. Let O be the centers of the two circles, A the point of contact, and let O lie between O and A. Take any other point B in the circumference of O, join OB, then 7. OB is greater than OA, therefore the point C is outside the circumference of the smaller circle. Hence B cannot be common to both circles. In like manner, they cannot have any other common point but A prop. 13 Theorem. Two circles cannot have double contact, that it, cannot touch each other in 2 points. Democrat 1. If possible, let two circles touch each other at 2 points A and B. Now since the two circles touch each other in A, the line joining their centers passes through A11. In like manner, it passes through B. Hence the centers and the points A, B are in one right line, therefore AB is a diameter of each circle. Hence, if AB be bisected in E must be the center of each circle, that is, the circles are concentric, which V is impossible. 2. If two circles touched each other externally in 2 distinct points, then 12 the line joining the centers should pass through each point, which is impossible. Or thus, draw a line bisecting AB at right angles. Then this line COR1 must pass through the center of each circle, and therefore 11-12 must pass through each point of contact, which is impossible. Hence two circles cannot have double contact. This proposition is an immediate inference from the theorem 12, COR1, that a point of contact counts for 2 intersections, for then 2 contacts would be equivalent to 4 intersections, but there cannot be more than 2 intersections x. It also follows from prop 12, COR2, that if two circles touch each other in a point A, they cannot have any other point common, hence they cannot touch again in B exercises. 1. If a variable circle touch two fixed circles externally, the difference of the distances of its center from the centers of the fixed circles is equal to the difference or the sum of their radii, according as the contacts are of the same or of opposite species, DEF 4. 2. If a variable circle be touched by one of two fixed circles internally, and touch the other fixed circle either externally or internally, the sum of the distances of its center from the centers of the fixed circles is equal to the sum or the difference of their radii, according as the contact with the second circle is of the first or second kind. 3. If through the point of contact of two touching circles any secant be drawn cutting the circles again in 2 points, the radii drawn to these points are parallel. 4. If two diameters of two touching circles be parallel, the lines from the point of contact to the extremities of one diameter pass through the extremities of the other. Prop. 14 Theorem. In equal circles 1. Equal chords, AB, CD, are equally distant from the center 2. Chords which are equally distant from the center are equal. Democrat 1. Let O be the center, draw the perpendiculars OE, of. Join AO, CO. Then because AB is a chord in a circle, and OE is drawn from the center cutting it at right angles, it bisects it 3, therefore AE is the half of AB. In like manner, CF is the half of CD, but AB is equal to CD, hip. Therefore AE is equal to CFI, axiom 7. And because E is a right angle, AO2 is equal to AE2 plus EO2. In like manner, CO2 is equal to CF2 plus FO2, but AO2 is equal to CO2. Therefore AE2 plus EO2 is equal to CF2 plus FO2, and AE2 has been proved equal to CF2. Hence EO2 is equal to FO2, therefore EO is equal to FO. Hence AB, CDR, DEF6, equally distant from the center 2. Let EO be equal to FO, it is required to prove AB equal to CD. The same construction being made, we have, as before, AE2 plus EO2 equal to CF2 plus FO2, but EO2 is equal to FO2, hip. Hence AE2 is equal to CF2, and AE is equal to CF, but AB is double of AE, and CD double of CF. Therefore AB is equal to CD. Exercise. If a chord of given length slide round a fixed circle 1. The locus of its middle point is a circle, 2. The locus of any point fixed in the chord is a circle. Prop. 15 Theorem. The diameter, AB, is the greatest chord in a circle, and of the others, the chord, CD, which is nearer to the center is greater than, F, one more remote, and the greater is nearer to the center than the less. Democrat 1. Join OC, OD, OE, and draw the perpendiculars OG, O, then because O is the center, OA is equal to OCI, DEFXXXII, and OB is equal to OD. Hence AB is equal to the sum of OC and OD, but the sum of OC, OD is greater than CDIXX. Therefore AB is greater than CD. 2. Because the chord CD is nearer to the center than F, OG is less than O, and since the triangles OGC, OH are right-angled, we have OC2 equals OG2 plus GC2, and OE2 equals O2 plus He2, therefore OG2 plus GC2 equals O2 plus He2, but OG2 is less than O2, therefore GC2 is greater than He2, and GC is greater than He, but CD and F are the doubles of GC and He. Hence CD is greater than F. 3. Let CD be greater than F, it is required to prove that OG is less than O. As before, we have OG2 plus GC2 equal to O2 plus He2, but CG2 is greater than A2, therefore OG2 is less than O2. Hence OG is less than O. Exercises. 1. The shortest chord which can be drawn through a given point within a circle is the perpendicular to the diameter which passes through that point. 2. Through a given point, within or without a given circle, draw a chord of length equal to that of a given chord. 3. Through one of the points of intersection of two circles draw a secant one. the sum of whose segments intercepted by the circles shall be a maximum, 2. Which shall be of any length less than that of the maximum. For 3 circles touch each other externally at A, B, C, the chords of AC of 2 of them are produced to meet the third again in the points D and E. Prove that D is a diameter of the third circle, and parallel to the line joining the centers of the others. Prop. 16 Theorem. 1. The perpendicular, by, to the diameter, of a circle at its extremity, B, touches the circle at that point. 2. Any other line, BH, through the same point cuts the circle. Democrat 1. Take any point I, and join it to the center C. Then because the angle CBI is a right angle, CI2 is equal to CB2 plus by 2I slay I, therefore CI2 is greater than CB2. Hence CI is greater than CB, and the point I note on I, DEFXXXII is without the circle. In like manner, every other point in BI, except B, is without the circle. Hence, since BI meets the circle at B, but does not cut it, it must touch it. 2. To prove that BH, which is not perpendicular to AB, cuts the circle. Draw CG perpendicular to HB. Now BC2 is equal to CG2 plus GB2. Therefore BC2 is greater than CG2, and BC is greater than CG. Hence note on I, DEFXXXII the point G must be within the circle, and consequently the line BG produced must meet the circle again, and must therefore cut it. This proposition may be proved as follows: at every point on a circle the tangent is perpendicular to the radius. Let P and Q be 2 consecutive points on the circumference. Join CP, CQ, PQ, produce PQ both ways. Now since P and Q are consecutive points, PQ is a tangent, DEF3. Again, the sum of the 3 angles of the triangle CPQ is equal to 2 right angles, but the angle C is infinitely small, and the others are equal. Hence each of them is a right angle. Therefore the tangent is perpendicular to the diameter. Or thus, a tangent is a limiting position of a secant, namely, when the secant moves out until the 2 points of intersection with the circle become consecutive, but the line through the center which bisects the part of the secant within the circle 3 is perpendicular to it. Hence, in the limit the tangent is perpendicular to the line from the center to the point of contact. Or again, the angle CPR is always equal to CQS, hence, when P and Q come together each is a right angle, and the tangent is perpendicular to the radius. Exercises. 1. If 2 circles be concentric, all chords of the greater which touch the lesser are equal. 2. Draw a parallel to a given line to touch a given circle. 3. Draw a perpendicular to a given line to touch a given circle. 4. Describe a circle having its center at a given point 1. And touching a given line, 2. And touching a given circle. How many solutions of this case? 5. Describe a circle of given radius that shall touch 2 given lines. How many solutions? 6. Find the locus of the centers of a system of circles touching 2 given lines. 7. Describe a circle of given radius that shall touch a given circle and a given line, or that shall touch 2 given circles. Prop. 17 Problem. From a given point, P, without a given circle, BCD, to draw a tangent to the circle. Solution: let O, figure 1, be the center of the given circle. Join OP, cutting the circumference in C. With O as center, and OP as radius, describe the circle APE. Erect CA at right angles to OP. Join OA, intersecting the circle BCD in B. Join BP, it will be the tangent required. Democrat: since O is the center of the 2 circles, we have OA equal to OP, and OC equal to OB. Hence the 2 triangles AOC, POB have the sides OA, OC in one respectively equal to the sides OP, OB in the other, and the contained angle common to both. Hence I for the angle OCA is equal to OBP, but OCA is a right angle, constant, therefore OBP is a right angle, and 16. PB touches the circle at BCOR if AC, figure 2, be produced to E, OE joined, cutting the circle BCD in D, and the line DP drawn, DP will be another tangent from P exercises. 1. The two tangents PB, PD, figure 2, are equal to one another, because the square of each is equal to the square of OP minus the square of the radius. 2. If two circles be concentric, all tangents to the inner from points on the outer are equal. 3. If a quadrilateral be circumscribed to a circle, the sum of one pair of opposite sides is equal to the sum of the other pair. 4. If a parallelogram be circumscribed to a circle, it must be a lozenge, and its diagonals intersect in the center. 5. If BD be joined, intersecting OP in F, OP is perpendicular to BD. 6. The locus of the intersection of two equal tangents to two circles is a right line, called the radical axis of the two circles. 7. Find a point such that tangents from it to three given circles shall be equal. This point is called the radical center of the three circles. 8. The rectangle of dot OP is equal to the square of the radius. Def. 2 points, such as F and P, the rectangle of whose distances of OP from the center is equal to the square of the radius, are called inverse points with respect to the circle. 9. The intercept made on a variable tangent by two fixed tangents subtends a constant angle at the center. 10. Draw a common tangent to two circles. Hence, show how to draw a line cutting two circles, so that the intercepted chords shall be of given lengths. Prop. 18. Theorem. If a line, CD, touch a circle, the line, OC, from the center to the point of contact is perpendicular to it. Democrat. If not, suppose another line OG drawn from the center to be perpendicular to CD. Let OG cut the circle in F. Then because the angle OGC is right, hip, the angle OCG I17 must be acute. Therefore I19. OC is greater than OG, but OC is equal to of IDEFXXXII, therefore of is greater than OG, that is, a part greater than the whole, which is impossible. Hence OC must be perpendicular to CD. Or thus, since the perpendicular must be the shortest line from O to CD, and OC is evidently the shortest line, therefore OC must be perpendicular to CD. Prop. 19. Theorem. If a line, AB, be a tangent to a circle, the line, AC, drawn at right angles to it from the point of contact passes through the center. If the center be not in AC, let O be the center join AO. Then because AB touches the circle, and OA is drawn from the center to the point of contact, OA is at right angles to AB 18, therefore the angle OAB is right, and the angle CAB is right, hip, therefore OAB is equal to CAB, a part equal to the whole, which is impossible. Hence the center must be in the line ACCOR. If a number of circles touch the same line at the same point, the locus of their centers is the perpendicular to the line at the point. Observation. Proposition 16, 18, 19, are so related that any two can be inferred from the third by the rule of identity. Hence it would, in strict logic, be sufficient to prove any one of the three, and the others would follow. Again, these three theorems are limiting cases of proposition I, COR1, and parts 1, 2, of proposition 3, namely, when the points in which the chord cuts the circle become consecutive. Prop. XX theorem. The angle, AOB, at the center, O, of a circle is double the angle, ACB, at the circumference standing on the same arc. Democrat. Join Co, and produce it to E. Then because OA is equal to OC, the angle ACO is equal to OAC, but the angle AOE is equal to the sum of the two angles OAC, ACO. Hence the angle AOE is double the angle ACO. In like manner the angle EOB is double the angle OCB. Hence, by adding in figs alpha, beta, and subtracting in gamma, the angle AOB is double of the angle ACB. COR if AOB be a straight line, ACB will be a right angle, that is, the angle in a semicircle is a right angle, compare XXXI. Prop. XXI theorem. The angles, ACB, ADB, in the same segment of a circle are equal. Democrat let O be the center, join OA, OB. Then the angle AOB is double of the angle ACB XX, and also double of the angle ADB. Therefore the angle ACB is equal to the angle ADB. The following is the proof of the second part, that is, when the arc of is not greater than a semicircle, without using angles greater than two right angles, let O be the center, join CO, and produce it to meet the circle again in E joined A. Now since O is the center, the segment ACE is greater than a semicircle, hence, by the first case, fig alpha, the angle ACE is equal to ID. In like manner the angle ECB is equal to EDB. Hence the whole angle ACB is equal to the whole angle ADB. COR1 if two triangles ACB, ADB on the same base of, and on the same side of it, have equal vertical angles, the 4 points A, C, D, B are concyclic. COR2 if A, B be two fixed points, and if C varies its position in such a way that the angle ACB retains the same value throughout, the locus of C is a circle. In other words, given the base of a triangle and the vertical angle, the locus of the vertex is a circle. Exercises. 1. Given the base of a triangle and the vertical angle, find the locus, 1, of the intersection of its perpendiculars, 2, of the intersection of the internal bisectors of its base angles, 3, of the intersection of the external bisectors of the base angles, 4, of the intersection of the external bisector of one base angle and the internal bisector of the other. 2. If the sum of the squares of two lines be given, their sum is a maximum when the lines are equal. 3. Of all triangles having the same base and vertical angle, the sum of the sides of an isosceles triangle is a maximum. 4. Of all triangles inscribed in a circle, the equilateral triangle has the maximum perimeter. 5. Of all concyclic figures having a given number of sides, the area is a maximum when the sides are equal. Prop. XXII theorem. The sum of the opposite angles of a quadrilateral, ABCD, inscribed in a circle is two right angles. Democrat join AC, BD. The angle ABD is equal to ACD, being in the same segment ABCD XXI, and the angle DBC is equal to DAC, because they are in the same segment DABC. Hence the whole angle ABC is equal to the sum of the two angles ACD, DAC. To each add the angle CDA, and we have the sum of the two angles ABC, CDA equal to the sum of the three angles ACD, DAC, CDA of the triangle ACD, but the sum of the three angles of a triangle is equal to two right angles IXXXII. Therefore the sum of ABC, CDA is two right angles. Or thus, let O be the center of the circle. Join OA, OC, see figure 2. Now the angle AOC is double of CDAXX, and the angle COA is double of ABC. Hence the sum of the angles IDEF9, note AOC, COA is double of the sum of the angles CDA, ABC, but the sum of two angles AOC, COA is four right angles. Therefore the sum of the angles CDA, ABC is two right angles. Or again, Let O be the center, figure 2. Join OA, OBOC, OD. Then the four triangles AOB, BOC, COD, DOA are each isosceles. Hence the angle OAB is equal to the angle OBA, and the angle OD equal to the angle ODA, therefore the angle BAD is equal to the sum of the angles OBA, ODA. In like manner the angle BCD is equal to the sum of the angles OBC, ODC. Hence the sum of the two angles BAD, BCD is equal to the sum of the two angles ABC, ADC, and hence each sum is two right angles. COR if a parallelogram be inscribed in a circle it is a rectangle. Exercises. 1. If the opposite angles of a quadrilateral be supplemental, it is cyclic. 2. If a figure of 6 sides be inscribed in a circle, the sum of any 3 alternate angles is 4 right angles. 3. A line which makes equal angles with one pair of opposite sides of a cyclic quadrilateral, makes equal angles with the remaining pair and with the diagonals. 4. If two opposite sides of a cyclic quadrilateral be produced to meet, and a perpendicular be let fall on the bisector of the angle between them from the point of intersection of the diagonals, this perpendicular will bisect the angle between the diagonals. 5. If two pairs of opposite sides of a cyclic hexagon be respectively parallel to each other, the remaining pair of sides are also parallel. 6. If two circles intersect in the points A, B, and any two lines ACD, BFE, be drawn through A and B, cutting one of the circles in the points C, E, and the other in the points D, F, the line CE is parallel to DF. 7. If equilateral triangles be described on the sides of any triangle, the lines joining the vertices of the original triangle to the opposite vertices of the equilateral triangles are concurrent. 8. In the same case prove that the centers of the circles described about the equilateral triangles form another equilateral triangle. 9. If a quadrilateral be described about a circle, the angles at the center subtended by the opposite sides are supplemental. 10. The perpendiculars of a triangle are concurrent. 11. If a variable tangent meets two parallel tangents it subtends a right angle at the center. 12. The feet of the perpendiculars let fall on the sides of a triangle from any point in the circumference of the circumscribed circle are collinear, Simpson. DEF. The line of collinearity is called Simpson's line. 13. If a hexagon be circumscribed about a circle, the sum of the angles subtended at the center by any 3 alternate sides is equal to 2 right angles. Prop. XXIII theorem. Two similar segments of circles which do not coincide cannot be constructed on the same chord, AB, and on the same side of that chord. Democrat. If possible, let ACB, ADB, be two similar segments constructed on the same side of AB. Take any point D in the inner one. Join AD, and produce it to meet the outer one in C. Join BC, BD. Then since the segments are similar, the angle ADB is equal to ACB, DEFX, which is impossible. I16. Hence two similar segments not coinciding cannot be described on the same chord and on the same side of it. Prop. XXIV theorem. Similar segments of circles, AEB, CFD, on equal chords, AB, CD, are equal to one another. Democrat. Since the lines are equal, if AB be applied to CD, so that the point A will coincide with C, and the line AB with CD, the point B shall coincide with D, and because the segments are similar, they must coincide XXIII. Hence they are equal. This demonstration may be stated as follows: since the chords are equal, they are congruent, and therefore the segments, being similar, must be congruent. Prop. XXV problem. An arc, ABC, of a circle being given, it is required to describe the whole circle. Solution: take any 3 points A, B, C in the arc, join AB, BC. Bisect AB and D, and BC in E erect DF, F at right angles to AB, BC, then F, the point of intersection, will be the center of the circle. Democrat because DF bisects the chord AB and is perpendicular to it, it passes through the center I, COR1. In like manner F passes through the center. Hence the point F must be the center, and the circle described from F as center, with Phi as radius, will be the circle required. Prop. XXVI theorem. The four propositions XXVI, XXIX are so like in their enunciations that students frequently substitute one for another. The following scheme will assist in remembering them in proposition XXVI. Are given angles equals, to prove arcs equals, XXVII. Arcs equals, angles equals, XXVIII. Chords equals, arcs equals, XXIX. Arcs equals, chords equals, so that proposition XXVII is the converse of XXVI, and XXIX of XXVIII. In equal circles, ACB, DFE, equal angles at the centers, AOB, DHE, or at the circumference, ACB, DFE, stand upon equal arcs. Democrat 1. Suppose the angles at the centers to be given equal. Now because the circles are equal their radii are equal, DEFI. Therefore the two triangles AOB, DHE have the sides AO, OB in one respectively equal to the sides DH, he in the other, and the angle AOB equal to DHE, hip. Therefore I for the base of is equal to D. Again, since the angles ACB, DFE are XX the halves of the equal angles AOB, DHE, they are equal I axiom 7. Therefore, DEFX, the segments ACB, DFE are similar, and their chords AB, D have been proved equal, therefore XXIV the segments are equal. And taking these equals from the whole circles, which are equal, hip, the remaining segments AGB, DKE are equal. Hence the arcs AGB, DKE are equal. 2. The demonstration of this case is included in the foregoing. COR1 if the opposite angles of a cyclic quadrilateral be equal, one of its diagonals must be a diameter of the circumscribed circle. COR2 parallel chords in a circle intercept equal arcs. COR3 if two chords intersect at any point within a circle, the sum of the opposite arcs which they intercept is equal to the arc which parallel chords intersecting on the circumference intercept. 2. If they intersect without the circle, the difference of the arcs they intercept is equal to the arc which parallel chords intersecting on the circumference intercept. COR4 if two chords intersect at right angles, the sum of the opposite arcs which they intercept on the circle is a semicircle. Prop. XXVII theorem. In equal circles, ACB, DFE, angles at the centers, AOB, DHE, or at the circumference, ACB, DFE, which stand on equal arcs, AB, D, are equal. Democrat if possible let one of them, such as AOB, be greater than the other, DHE, and suppose a part such as AOL to be equal to DHE. Then since the circles are equal, and the angles AOL, DHE at the centers are equal, hip, the arc AL is equal to DXXVI, but AB is equal to D, hip. Hence AL is equal to AB that is, a part equal to the whole, which is absurd. Therefore the angle AOB is equal to DHE. 2. The angles at the circumference, being the halves of the central angles, are therefore equal. Prop. XXVII theorem. In equal circles, ACB, DFE, equal chords, AB, D, divide the circumference into arcs, which are equal each to each that is, the lesser to the lesser, and the greater to the greater. Democrat. If the equal chords be diameters, the proposition is evident. If not, let O, H be the centers. Join AO, OB, DH, he, then because the circles are equal their radii are equal, DEFI. Hence the two triangles AOB, DHE have the sides AO, OB in one respectively equal to the sides DH, he in the other, and the base of is equal to D, hip. Therefore I8 the angle AOB is equal to DHE. Hence the arc AGB is equal to DKEXXVI, and since the whole circumference AGBC is equal to the whole circumference DKEF, the remaining arc ACB is equal to the remaining arc DFE. Exercises. 1. The line joining the feet of perpendiculars from any point in the circumference of a circle, on two diameters given in position, is given in magnitude. 2. If a line of given length slide between two lines given in position, the locus of the intersection of perpendiculars to the given lines at its extremities is a circle. This is the converse of 1. Prop. XXIX theorem. In equal circles, ACB, DFE, equal arcs, AGB, DCK, are subtended by equal chords. Democrat. Let O, H be the centers, see last figure. Join AO, OB, DH, he, then because the circles are equal, the angles AOB, DHE at the centers, which stand on the equal arcs AGB, DKE, are equal XXVII. Again, because the triangles AOB, DHE have the two sides AO, OB in one respectively equal to the two sides DH, he in the other, and the angle AOB equal to the angle DHE, the base above one is equal to the base D of the other. Observation. Since the two circles in the four last propositions are equal, they are congruent figures, and the truth of the propositions is evident by superposition. Prop. XXX problem. To bisect a given arc ACB. Solution. Draw the chord AB, bisect it in D, erect DC at right angles to AB, meeting the arc in C, then the arc is bisected in C. Democrat. Join AC, BC. Then the triangles ADC, BDC have the side AD equal to DB, constant, and DC common to both, and the angle ADC equal to the angle BDC, each being right. Hence the base AC is equal to the base BC. Therefore XXVII the arc AC is equal to the arc BC. Hence the arc AB is bisected in C. Exercises. 1. ABCD is a semicircle whose diameter is AD, the chord BC produced meets AD produced in E. Prove that if CE is equal to the radius, the arc AB is equal to 3 times CD. 2. The internal and the external bisectors of the vertical angle of a triangle inscribed in a circle meet the circumference again in points equidistant from the extremities of the base. 3. If from A, one of the points of intersection of two given circles, two chords ACD, AC be drawn, cutting the circles in the points C, D, C, D, the triangles BCD, BC, formed by joining these to the second point B of intersection of the circles, are equiangular. 4. If the vertical angle ACB of a triangle inscribed in a circle be bisected by a line CD, which meets the circle again in D, and from D perpendiculars to DF be drawn to the sides, one of which must be produced, prove that EA is equal to BF, and hence show that CE is equal to half the sum of AC, BC. Prop. XXXI theorem. In a circle, 1. The angle in a semicircle is a right angle. 2. The angle in a segment greater than a semicircle is an acute angle. 3. The angle in a segment less than a semicircle is an obtuse angle. Democrat. 1. Let AB be the diameter, see any point in the semicircle. Join AC, CB. The angle ACB is a right angle. 4. Let O be the center. Join OC, and produce AC to F. Then because AO is equal to OC, the angle ACO is equal to the angle OAC. In like manner, the angle OCB is equal to CBO. Hence the angle ACB is equal to the sum of the two angles BAC, CBA, but IXXXII the angle FCB is equal to the sum of the two interior angles BAC, CBA of the triangle ABC. Hence the angle ACB is equal to its adjacent angle FCB, and therefore it is a right angle IDEF 13. 2. Let the arc ACE be greater than a semicircle. Join CE. Then the angle ACE is evidently less than ACB, but ACB is right, therefore ACE is acute. 3. Let the arc ACD be less than a semicircle, then evidently, from 1, the angle ACD is obtuse. COR1 If a parallelogram be inscribed in a circle, its diagonals intersect at the center of the circle. COR2 Find the center of a circle by means of a carpenter's square. COR3 From a point outside a circle draw two tangents to the circle. Prop. XXXII theorem. If a line, F, be a tangent to a circle, and from the point of contact, A, a chord, AC, be drawn cutting the circle, the angles made by this line with the tangent are respectively equal to the angles in the alternate segments of the circle. Democrat, 1. If the chord passes through the center, the proposition is evident, for the angles are right angles, but if not, from the point of contact A draw AB at right angles to the tangent. Join BC. Then because F is a tangent to the circle, and AB is drawn from the point of contact perpendicular to F, AB passes through the center 19. Therefore the angle ACB is right XXXI. Hence the sum of the two remaining angles ABC, CAB is one right angle, but the angle BAF is right, constant, therefore the sum of the angles ABC, BAC is equal to BAF. Reject BAC, which is common, and we get the angle ABC equal to the angle FAC. 2. Take any point D in the arc AC. It is required to prove that the angle CAE is equal to CDA. Since the quadrilateral ABCD is cyclic, the sum of the opposite angles ABC, CDA is two right angles XXII, and therefore equal to the sum of the angles FAC, CAE, but the angles ABC, FAC are equal, 1. Reject them, and we get the angle CDA equal to CAE. Or thus, take any point G in the semicircle AGB. Join AG, GB, GC. Then the angle AGB equals FAB, each being right, and CGB equals CAB XXI. Therefore the remaining angle AGC equals FAC. Again, join BD, CD. The angle BDA equals BA, each being right, and CDB equals CAB XXI. Hence the angle CDA equals CAE Lardner. Or by the method of limits, see Townsend's Modern Geometry, Volume I, page 14. The angle BAC is equal to BDC XXI. Now let the point B move until it becomes consecutive to A, then AB will be a tangent, and BD will coincide with AD, and the angle BDC with ADC. Hence, if AX be a tangent at A, AC any chord, the angle which the tangent makes with the chord is equal to the angle in the alternate segment. Exercises. 1. If two circles touch, any line drawn through the point of contact will cut off similar segments. 2. If two circles touch, and any two lines be drawn through the point of contact, cutting both circles again, the chord connecting their points of intersection with one circle is parallel to the chord connecting their points of intersection with the other circle. 3. ACB is an arc of a circle, CE a tangent at C, meeting the chord AB produced in E, and AD a perpendicular to AB in D. Prove, if to be bisected in C, that the arc AC equals 2CB. 4. If two circles touch at a point A, and ABC be a chord through A, meeting the circles in B and C, prove that the tangents at B and C are parallel to each other, and that when one circle is within the other, the tangent at B meets the outer circle in 2 points equidistant from C5. If two circles touch externally, their common tangent at either side subtends a right angle at the point of contact, and its square is equal to the rectangle contained by their diameters. Prop. XXXIII problem. On a given right line, AB, to describe a segment of a circle which shall contain an angle equal to a given rectilineal angle, x. Solution: if x be a right angle, describe a semicircle on the given line, and the thing required is done, for the angle in a semicircle is a right angle. If not, make with the given line of the angle BA equal to x, erect AC at right angles to AE, and BC at right angles to AB. On AC as diameter describe a circle, it will be the circle required. Democrat: the circle on AC as diameter passes through B, since the angle ABC is right XXXI and touches AE, since the angle CAE is right 16. Therefore the angle BA XXXII is equal to the angle in the alternate segment, but the angle BA is equal to the angle X, constant. Therefore the angle X is equal to the angle in the segment described on AB. Exercises. 1. Construct a triangle, being given base, vertical angle, and any of the following data. 1. Perpendicular. 2. The sum or difference of the sides. 3. Sum or difference of the squares of the sides. 4. Side of the inscribed square on the base. 5. The median that bisects the base. 2. If lines be drawn from a fixed point to all the points of the circumference of a given circle, the locus of all their points of bisection is a circle. 3. Given the base and vertical angle of a triangle, find the locus of the middle point of the line joining the vertices of equilateral triangles described on the sides. 4. In the same case, find the loci of the angular points of a square described on one of the sides. Prop. Third problem. To cut off from a given circle, ABC, a segment which shall contain an angle equal to a given angle, x. Solution: take any point A in the circumference. Draw the tangent AD, and make the angle DAC equal to the given angle XAC will cut off the required segment. Democrat: take any point B in the alternate segment. Join BA, BC. Then the angle DAC is equal to ABC XXXII, but DAC is equal to x, constant. Therefore the angle ABC is equal to x prop. XXXV theorem. If two chords, AB, CD, of a circle intersect in a point, E, within the circle, the rectangles, AE.EB, CE.ED, contained by the segments are equal. Democrat 1. If the point of intersection be the center, each rectangle is equal to the square of the radius. Hence they are equal. 2. Let one of the chords AB pass through the center O, and cut the other chord CD, which does not pass through the center, at right angles. Join OC. Now because AB passes through the center, and cuts the other chord CD, which does not pass through the center at right angles, it bisects it. 3. Again, because AB is divided equally in O and unequally in E, the rectangle AE.EB, together with OE2, is equal to OB2, that is, to OC2 2V, but OC2 is equal to OE2 plus EC2 islai. Therefore reject OE2, which is common, and we have AE.EB equals EC2, but CE2 is equal to the rectangle CE.ED, since CE is equal to ED. Therefore the rectangle AE.EB is equal to the rectangle CE.ED. 3. Let AB pass through the center, and cut CD, which does not pass through the center obliquely. Let O be the center draw a perpendicular to CDI11. Join OC, OD. Then, since CD is cut at right angles by OV, which passes through the center, it is bisected in F3, and divided unequally in E. Hence CE.ed plus Φ2 equals FD2 2V, and of 2 equals of 2. Hence, adding, since Φ2 plus of 2 equals OE2 I/I, and FD2 plus of 2 equals OD2, we get again, since OB is bisected in O and divided unequally in E, AE.EB plus OE2 equals OB2 2V. Therefore CE.ed plus OE2 equals AE.EB plus OE2. Hence CE.ed equals AE.EB. 4. Let neither chord pass through the center. Through the point E, where they intersect, draw the diameter FG. Then by 3, the rectangle FE.EG is equal to the rectangle AE.EB, and also to the rectangle CE.ed. Hence the rectangle AE.EB is equal to the rectangle CE.ed. COR1 If a chord of a circle be divided in any point within the circle, the rectangle contained by its segments is equal to the difference between the square of the radius and the square of the line drawn from the center to the point of section. COR2 If the rectangle contained by the segments of one of two intersecting lines be equal to the rectangle contained by the segments of the other, the four extremities are concyclic. COR3 If two triangles be equiangular, the rectangle contained by the non-corresponding sides about any two equal angles are equal. Let ABO, DCO be the equiangular triangles, and let them be placed so that the equal angles at O may be vertically opposite, and that the non-corresponding sides AO, CO may be in one line, then the non-corresponding sides BO, OD shall be in one line. Now, since the angle ABD is equal to ACD, the points A, B, C, D are concyclic XXI, COR1. Hence the rectangle AO.OC is equal to the rectangle BO.OD/XXXV. Exercises. 1. In any triangle, the rectangle contained by two sides is equal to the rectangle contained by the perpendicular on the third side and the diameter of the circumscribed circle. DEF The supplement of an arc is the difference between it and a semicircle. 2. The rectangle contained by the chord of an arc and the chord of its supplement is equal to the rectangle contained by the radius and the chord of twice the supplement. 3. If the base of a triangle be given, and the sum of the sides, the rectangle contained by the perpendiculars from the extremities of the base on the external bisector of the vertical angle is given. 4. If the base and the difference of the sides be given, the rectangle contained by the perpendiculars from the extremities of the base on the internal bisector is given. 5. Through one of the points of intersection of two circles draw a secant, so that the rectangle contained by the intercepted chords may be given, or a maximum. 6. If the sum of two arcs, AC, CB of a circle be less than a semicircle, the rectangle AC.CB contained by their chords is equal to the rectangle contained by the radius, and the excess of the chord of the supplement of their difference above the chord of the supplement of their sum Catalan. Democrat draw the diameter which is perpendicular to AB, and draw the chord CF, BG parallel to DA. Now it is evident that the difference between the arcs AC, CB is equal to 2 CD, and therefore equals CD plus F. Hence the arc CBF is the supplement of the difference, and CF is the chord of that supplement. Again, since the angle ABG is right, the arc ABG is a semicircle. Hence BG is the supplement of the sum of the arcs AC, CB, therefore the line BG is the chord of the supplement of the sum. Now, EX1, the rectangle AC.CB is equal to the rectangle contained by the diameter and CI, and therefore equal to the rectangle contained by the radius and 2 CI, but the difference between CF and BG is evidently equal to 2 CI. Hence the rectangle AC.CB is equal to the rectangle contained by the radius and the difference between the chords CF, BG7. If we join AF, BF we find, as before, the rectangle AF.FB equal to the rectangle contained by the radius and 2 phi, that is, equal to the rectangle contained by the radius and the sum of CF and BG. Hence if the sum of two arcs of a circle be greater than a semicircle, the rectangle contained by their chords is equal to the rectangle contained by the radius, and the sum of the chords of the supplements of their sum and their difference. 8. Through a given point draw a transversal cutting two lines given in position, so that the rectangle contained by the segments intercepted between it and the line may be given. Prop. 30 Theorem. If from any point, P, without a circle two lines be drawn to it, one of which, PT, is a tangent, and the other, PA, a secant, the rectangle, AP, BP, contained by the segments of the secant is equal to the square of the tangent. Democrat 1. Let PA pass through the center O join OT. Then because AB is bisected in O and divided externally in P, the rectangle AP.BP plus OB2 is equal to OP226. But since PT is a tangent, and OT drawn from the center to the point of contact, the angle OTP is right 18. Hence OT2 plus PT2 is equal to OP2. Therefore AP.BP plus OB2 equals OT2 plus PT2, but OB2 equals OT2. Hence the rectangle AP.BP equals PT2. 2. If AB does not pass through the center O, let fall the perpendicular OC on AB. Join OT, OB, OP. Then because OC, a line through the center, cuts AB, which does not pass through the center at right angles, it bisects it 3. Hence, since AB is bisected in C and divided externally in P, the rectangle AP.BP plus CB2 equals CP226, and OC2 equals OC2. Hence, adding, since CB2 plus OC2 equals OB2 islai, and CP2 plus OC2 equals OP2, we get rectangle AP.BP plus OB2 equals OP2, but OT2 plus PT2 equals OP2 islai. Therefore AP.BP plus OB2 equals OT2 plus PT2, and rejecting the equals OB2 and OT2, we have the rectangle. The two propositions XXXV, 30, may be included in one enunciation, as follows: the rectangle AP.BP contained by the segments of any chord of a given circle passing through a fixed point P, either within or without the circle, is constant. For let O be the center, join OA, OB, OP. Then OAB is an isosceles triangle, and OP is a line drawn from its vertex to a point P in the base, or base produced. Then the rectangle AP.BP is equal to the difference of the squares of OB and OP, and is therefore constant. COR1 if two lines of CD produced meet in P, and if the rectangle AP.BP equals CP.DP, the points A, B, C, D are concyclic, compare XXXV, COR2. COR2 tangents to two circles from any point in their common chord are equal, compare 17, EX6. COR3 the common chords of any three intersecting circles are concurrent, compare 17, EX7. Exercise. If from the vertex A of AABC, AD be drawn, meeting CB produced in D, and making the angle BAD equals ACB, prove dB.dc equals D2. Prop. XXXVII theorem. If the rectangle, AP.BP, contained by the segments of a secant, drawn from any point, P, without a circle, be equal to the square of a line, PT, drawn from the same point to meet the circle, the line which meets the circle is a tangent. Democrat from P draw PQ touching the circle 17. Let O be the center join OP,
OC, OT. Now the rectangle AP.BP is equal to the square on PT, HIP, and equal to the square on PQ30. Hence PT2 is equal to PQ2, and therefore PT is equal to PQ. Again, the triangles OTP, OQP have the side OT equal OC, TP equal QP, and the base OP common, hence I8 the angle OTP is equal to OQP, but OQP is a right angle, since PQ is a tangent 18, hence OTP is right, and therefore 16. PT is a tangent. Exercises. 1. Describe a circle passing through two given points, and fulfilling either of the following conditions: 1. Touching a given line, 2. Touching a given circle. 2. Describe a circle through a given point, and touching two given lines, or touching a given file and a given circle. 3. Describe a circle passing through a given point, having its center on a given line and touching a given circle. 4. Describe a circle through two given points, and intercepting a given arc on a given circle. 5a, b, c, d are four collinear points, and F is a common tangent to the circles described upon a b, c, d as diameters. Prove that the triangles AEB, CFD are equiangular. 6. The diameter of the circle inscribed in a right-angled triangle is equal to half the sum of the diameters of the circles touching the hypotenuse, the perpendicular from the right angle of the hypotenuse, and the circle described about the right-angled triangle. Questions for examination on Book 3. 1. What is the subject matter of Book 3? 2. Define equal circles. 3. What is the difference between a chord and a secant? 4. When does a secant become a tangent? 5. What is the difference between a segment of a circle and a sector? 6. What is meant by an angle in a segment? 7. If an arc of a circle be 1/6 of the whole circumference, what is the magnitude of the angle in it? 8. What are linear segments? 9. What is meant by an angle standing on a segment? 10. What are concyclic points? 11. What is a cyclic quadrilateral? 12. How many intersections can a line and a circle have? 13. What does the line become when the points of intersection become consecutive? 14. How many points of intersection can two circles have? 15. What is the reason that if two circles touch they cannot have any other common point? 16. Give one enunciation that will include propositions 11, 12. Of Book 3. 17. What proposition is this a limiting case of? 18. Explain the extended meaning of the word angle. 19. What is Euclid's limit of an angle? 20. State the relations between propositions 16, 18, 19. 21. What propositions are these limiting cases of? 22. How many common tangents can two circles have? 23. What is the magnitude of the rectangle of the segments of a chord drawn through a point 3.65 meters distant from the center of a circle whose radius is 4.25 meters? 24. The radii of two circles are 4.25 and 1.75 feet respectively, and the distance between their centers 6.5 feet. Find the lengths of their direct and their transverse common tangents. 25. If a point be h feet outside the circumference of a circle whose diameter is 7,920 miles, prove that the length of the tangent drawn from it to the circle is miles. 26. Two parallel chords of a circle are 12 perches and 16 perches respectively, and their distance asunder is 2 perches. Find the length of the diameter. 27. What is the locus of the centers of all circles touching a given circle in a given point? 28. What is the condition that must be fulfilled that 4 points may be concyclic? 29. If the angle in a segment of a circle be a right angle and a half, what part of the whole circumference is it? 30. Mention the converse propositions of Book 3, which are proved directly. 31. What is the locus of the middle points of equal chords in a circle?
32 The radii of two circles are 6 and 8, and the distance between their centers 10, find the length of their common chord. 33 If a figure of any even number of sides be inscribed in a circle, prove that the sum of one set of alternate angles is equal to the sum of the remaining angles. Exercises on Book 3. 1. If two chords of a circle intersect at right angles, the sum of the squares on their segments is equal to the square on the diameter. 2. If a chord of a given circle subtend a right angle at a fixed point, the rectangle of the perpendiculars on it from the fixed point and from the center of the given circle is constant. Also the sum of the squares of perpendiculars on it from two other fixed points, which may be found, is constant. 3. If through either of the points of intersection of two equal circles any line be drawn meeting them again in 2 points, these points are equally distant from the other intersection of the circles. 4. Draw a tangent to a given circle so that the triangle formed by it and two fixed tangents to the circle shall be 1, a maximum, 2, a minimum. 5. If through the points of intersection A, B of two circles any two lines ACD, BEF be drawn parallel to each other, and meeting the circles again in C, D, E, F, then CD equals F. 6. In every triangle the bisector of the greatest angle is the least of the three bisectors of the angles. 7. The circles whose diameters are the four sides of any cyclic quadrilateral intersect again in 4 concyclic points. 8. The four angular points of a cyclic quadrilateral determine 4 triangles whose orthocenters, the intersections of their perpendiculars, form an equal quadrilateral. 9. If through one of the points of intersection of two circles we draw two common chords, the lines joining the extremities of these chords make a given angle with each other. 10. The square on the perpendicular from any point in the circumference of a circle, on the chord of contact of two tangents, is equal to the rectangle of the perpendiculars from the same point on the tangents. 11. Find a point in the circumference of a given circle, the sum of the squares on whose distances from two given points may be a maximum or a minimum. 12. 4 circles are described on the sides of a quadrilateral as diameters. The common chord of any two on adjacent sides is parallel to the common chord of the remaining two. 13. The rectangle contained by the perpendiculars from any point in a circle, on the diagonals of an inscribed quadrilateral, is equal to the rectangle contained by the perpendiculars from the same point on either pair of opposite sides. 14. The rectangle contained by the sides of a triangle is greater than the square on the internal bisector of the vertical angle, by the rectangle contained by the segments of the base. 15. If through one of the points of intersection of two circles, we draw any line ABC, cutting the circles again in B and C, the tangents at B and C intersect at a given angle. 16. If a chord of a given circle pass through a given point, the locus of the intersection of tangents at its extremities is a right line. 17. The rectangle contained by the distances of the point where the internal bisector of the vertical angle meets the base, and the point where the perpendicular from the vertex meets it from the middle point of the base, is equal to the square on half the difference of the sides. 18. State and prove the proposition analogous to 17 for the external bisector of the vertical angle. 19. The square on the external diagonal of a cyclic quadrilateral is equal to the sum of the squares on the tangents from its extremities to the circumscribed circle. 20. If a variable circle touch a given circle and a given line, the chord of contact passes through a given point. 21. If A, B, C be 3 points in the circumference of a circle, and D, E the middle points of the arcs of B, AC, then if the line to intersect the chords of B, AC in the points F, G, AF is equal to AG. 22. Given two circles, O, O, then if any secant cut O in the points B, C, and O in the points B, C, and another secant cuts them in the points D, E, D, E respectively, the four chords BD, CE, BD, CE form a cyclic quadrilateral. 23. If a cyclic quadrilateral be such that a circle can be inscribed in it, the lines joining the points of contact are perpendicular to each other. 24. If through the point of intersection of the diagonals of a cyclic quadrilateral the minimum chord be drawn, that point will bisect the part of the chord between the opposite sides of the quadrilateral. 25. Given the base of a triangle, the vertical angle, and either the internal or the external bisector at the vertical angle, construct it. 26. If through the middle point A of a given arc BAC we draw any chord AD, cutting BC in E, the rectangle AD.AE is constant. 27. The four circles circumscribing the four triangles formed by any four lines pass through a common point. 28. If X, Y, Z be any 3 points on the three sides of a triangle ABC, the three circles about the triangles YAZ, ZBX, XCY pass through a common point. 29. If the position of the common point in the last question be given, the three angles of the triangle XYZ are given, and conversely. 30. Place a given triangle so that its three sides shall pass through three given points. 31. Place a given triangle so that its three vertices shall lie on three given lines. 32. Construct the greatest triangle equiangular to a given one whose sides shall pass through three given points. 33. Construct the least triangle equiangular to a given one whose vertices shall lie on three given lines. 34. Construct the greatest triangle equiangular to a given one whose sides shall touch three given circles. 35. If two sides of a given triangle pass through fixed points, the third touches a fixed circle. 36. If two sides of a given triangle touch fixed circles, the third touches a fixed circle. 37. Construct an equilateral triangle having its vertex at a given point, and the extremities of its base on a given circle. 38. Construct an equilateral triangle having its vertex at a given point, and the extremities of its base on two given circles. 39. Place a given triangle so that its three sides shall touch three given circles. 40. Circumscribe a square about a given quadrilateral. 41. Inscribe a square in a given quadrilateral. 42. Describe circles, 1. Orthogonal, cutting at right angles, to a given circle and passing through two given points, 2. Orthogonal to two others, and passing through a given point, 3. Orthogonal to three others. 43. If from the extremities of a diameter above a semicircle two chords AD, B be drawn, meeting in C, AC.AD plus BC.BE equals of 2. 44. If ABCD be a cyclic quadrilateral, and if we describe any circle passing through the points A and B, another through B and C, a third through C and D, and a fourth through D and A, these circles intersect successively in four other points E, F, G, H, forming another cyclic quadrilateral. 45. If ABC be an equilateral triangle, what is the locus of the point M, if MA equals MB plus MC? 46. In a triangle, given the sum or the difference of two sides and the angle formed by these sides both in magnitude and position, the locus of the center of the circumscribed circle is a right line. 47. Describe a circle, 1. Through two given points which shall bisect the circumference of a given circle, 2. Through one given point which shall bisect the circumference of two given circles. 48. Find the locus of the center of a circle which bisects the circumference of two given circles. 49. Describe a circle which shall bisect the circumference of three given circles. 50. Ob is a diameter of a circle, AC, AD are two chords meeting the tangent at B in the points E, F respectively. Prove that the points C, D, E, F are concyclic. 51. CD is a perpendicular from any point C in a semicircle on the diameter of EFG is a circle touching DB in E, CD in F, and the semicircle in G. Prove, 1, that the points A, F, G are collinear, 2, that AC equals AE. 52. Being given an obtuse angled triangle, draw from the obtuse angle to the opposite side a line whose square shall be equal to the rectangle contained by the segments into which it divides the opposite side. 53. O is a point outside a circle whose center is E. Two perpendicular lines passing through O intercept chords AB, CD on the circle, then AB2 plus CD2 plus 4OE2 equals 8R2. 54. The sum of the squares on the sides of a triangle is equal to twice the sum of the rectangles contained by each perpendicular and the portion of it comprised between the corresponding vertex and the orthocenter, also equal to 12R2 minus the sum of the squares of the distances of the orthocenter from the vertices. 55. If two circles touch in C, and if D be any point outside the circles at which their radii through C subtend equal angles, if DF be tangent from D, DF equals DC2. Book 4. Inscription and circumscription of triangles and of regular polygons in and about circles underscore 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 definitions. If two rectilineal figures be so related that the angular points of one lie on the sides of the other one, the former is said to be inscribed in the latter. 2. The latter is said to be described about the former. 2. A rectilineal figure is said to be inscribed in a circle when its angular points are on the circumference. Reciprocally, a rectilineal figure is said to be circumscribed to a circle when each side touches the circle. 3. A circle is said to be inscribed in a rectilineal figure when it touches each side of the figure. Reciprocally, a circle is said to be circumscribed to a rectilineal figure when it passes through each angular point of the figure. 4. A rectilineal figure which is both equilateral and equiangular is said to be regular. Observation. The following summary of the contents of the fourth book will assist the student in remembering it. 1. It contains 16 propositions, of which 4 relate to triangles, 4 to squares, 4 to pentagons, and 4 miscellaneous propositions. 2 of the 4 propositions occupied with triangles. Alpha, 1 is to inscribe a triangle in a circle. Beta, its reciprocal, to describe a triangle about a circle. Gamma, to inscribe a circle in a triangle. Delta, its reciprocal, to describe a circle about a triangle. 3. If we substitute in alpha, beta, gamma, delta, squares for triangles, and pentagons for triangles, we have the problems for squares and pentagons respectively. 4. Every proposition in the fourth book is a problem. Prop. I problem. In a given circle, ABC, to place a chord equal to a given line, D, not greater than the diameter. Solution. Draw any diameter AC of the circle, then, if AC be equal to D, the thing required is done. If not, from AC cut off the part AE equal to DI3, and with A as center and AE as radius, describe the circle EBF, cutting the circle ABC in the points B, F join AB. Then AB is the chord required. Democrat. Because A is the center of the circle EBF, AB is equal to AEIDEFXXXII, but AE is equal to D, constant, therefore AB is equal to D prop. 2. Problem. In a given circle, ABC, to inscribe a triangle equiangular to a given triangle, def. Solution. Take any point A in the circumference, and at it draw the tangent GH, then make the angle HAC equal to E, and GAB equal to FIXXIII. Join BC. ABC is a triangle fulfilling the required conditions. Democrat. The angle E is equal to HAC, constant, and HAC is equal to the angle ABC in the alternate segment 3XXXII. Hence the angle E is equal to ABC. In like manner the angle F is equal to ACB. Therefore IXXXII the remaining angle D is equal to BAC. Hence the triangle ABC inscribed in the given circle is equiangular to def. Prop. 3 Problem. About a given circle, ABC, to describe a triangle equiangular to a given triangle, def. Solution: produce any side of the given triangle both ways to G and H, and from the center O of the circle draw any radius OA, make the angle AOB equal to GEFIXXIII, and the angle AOC equal to HDF. At the points A, B, C draw the tangents LM, MN, NL to the given circle. LMN is a triangle fulfilling the required conditions. Democrat because AM touches the circle at A, the angle OAM is right. In like manner, the angle MBO is right, but the sum of the four angles of the quadrilateral OAMB is equal to 4 right angles. Therefore the sum of the two remaining angles AOB, AMB is 2 right angles, and I13 the sum of the two angles GEF, FED is 2 right angles. Therefore the sum of AOB, AMB is equal to the sum of GEF, FED, but AOB is equal to GEF, constant. Hence AMB is equal to FED. In like manner, ALC is equal to EDF, therefore IXXXII the remaining angle BNC is equal to DFE. Hence the triangle LMN is equiangular to def. Prop. 4 Problem. To inscribe a circle in a given triangle, ABC. Solution: bisect any two angles A, B of the given triangle by the lines AO, BO, then O, their point of intersection, is the center of the required circle. Democrat from O let fall the perpendiculars OD, OE, of on the sides of the triangle. Now, in the triangles OAE, OF the angle OAE is equal to OF, constant, and the angle AEO equal to AFO, because each is right, and the side OA common. Hence IXXVI the side OE is equal to of. In like manner OD is equal to of, therefore the three lines OD, OE, of are all equal. And the circle described with O as center and OD as radius will pass through the points E, F, and since the angles D, E, F are right, it will 316 touch the three sides of the triangle ABC, and therefore the circle def is inscribed in the triangle ABC. Exercises. 1. If the points O, C be joined, the angle C is bisected. Hence the bisectors of the angles of a triangle are concurrent, compare IXXVI, EX7. 2. If the sides BC, CA, above the triangle ABC be denoted by A, B, C, and half their sum by S, the distances of the vertices A, B, C of the triangle from the points of contact of the inscribed circle are respectively SA, SB, SC3. If the external angles of the triangle ABC be bisected as in the annexed diagram, the three angular points O, 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 of the triangle formed by the three bisectors will be the centers of three circles, each touching one side externally, and the other two produced. These three circles are called the ascribed circles of the triangle ABC. 4. The distances of the vertices A, B, C from the points of contact of the ascribed circle which touches of externally are SB, SA, S5. The center of the inscribed circle, the center of each ascribed circle, and two of the angular points of the triangle, are concyclic. Also any two of the ascribed centers are concyclic with the corresponding two of the angular points of the triangle. 6. Of the 4 points O, 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 any one is the orthocenter of the triangle formed by the remaining three. 7. The three triangles BCO, CAO, ABO are equiangular. 8. The rectangle CO equals AB, AO equals BC, BO equals CA9. Since the whole triangle ABC is made up of the three triangles AOB, BOC, COA, we see that the rectangle contained by the sum of the three sides, and the radius of the inscribed circle, is equal to twice the area of the triangle. Hence, if r denote the radius of the inscribed circle, rs equals area of the triangle. 10 If r denote the radius of the inscribed circle which touches the side externally, it may be shown in like manner that r, sa, equals area of the triangle. 11 rr equals sb.sc12. Square of area equals s.sa.sb.sc13. Square of area equals r.r.r.r. 14 If the triangle ABC be right-angled, having the angle C right, 15. Given the base of a triangle, the vertical angle, and the radius of the inscribed, or any of the inscribed circles, construct it. Prop. V. Problem. To describe a circle about a given triangle, ABC. Solution: bisect any two sides BC, AC in the points D, E erect do, EO at right angles to BC, CA, then O, the point of intersection of the perpendiculars, is the center of the required circle. Democrat: join OA, OB, OC. The triangles BDO, CDO have the side BD equal CD, constant, and do common, and the angle BDO equal to the angle CDO, because each is right. Hence I4. BO is equal to OC. In like manner AO is equal to OC. Therefore the three lines AO, BO, CO are equal, and the circle described with O as center, and OA as radius, will pass through the points A, B, C, and be described about the triangle ABC. COR1 Since the perpendicular from O on AB bisects at 3, 3, we see that the perpendiculars at the middle points of the sides of a triangle are concurrent. DEF The circle ABC is called the circumcircle, its radius the circumradius, and its center the circumcenter of the triangle. Exercises. 1. The three perpendiculars of a triangle, ABC, are concurrent. Democrat: describe a circle about the triangle. Let fall the perpendicular CF. Produce CF to meet the circle in G. Make FO equals FG. Join AG, AO. Produce AO to meet BC in D. Then the triangles GFA, OFA have the sides GF, FA in one equal to the sides of, FA in the other, and the contained angles equal. Hence I4 the angle GAF equal OF, but GAF equals GCB 3XXI, hence OF equals OCD, and FOA equals DOC, hence OFA equals ODC, but OFA is right, hence ODC is right. In like manner, if BO be joined to meet AC in E, B will be perpendicular to AC. Hence the three perpendiculars pass through O, and are concurrent. This proposition may be proved simply as follows: draw parallels to the sides of the original triangle ABC through its vertices, forming a new triangle ABC described about ABC, then the three perpendiculars at the middle points of the sides of ABC are concurrent VCOR1, and these are evidently the perpendiculars from the vertices on the opposite sides of the triangle ABC, compare EX16, Book I. DEF The point O is called the orthocenter of the triangle ABC. 2. The three rectangles OA.op, OB.oc, OC.or are equal. DEF The circle round O as center, the square of whose radius is equal OA.op equals OB.oc equals OC.or, is called the polar circle of the triangle ABC. Observation: if the orthocenter of the triangle ABC be within the triangle, the rectangles OA.op, OB.oc, OC.or are negative, because the lines OA.op and C are measured in opposite directions, and have contrary signs, hence the polar circle is imaginary, but it is real when the point O is without the triangle, that is, when the triangle has an obtuse angle. 3. If the perpendiculars of a triangle be produced to meet the circumscribed circle, the intercepts between the orthocenter and the circle are bisected by the sides of the triangle. For the point of bisection, I, of the line, op, joining the orthocenter, O, to the circumference, P, of any triangle is equally distant from the feet of the perpendiculars, from the middle points of the sides, and from the middle points of the distances of the vertices from the orthocenter. Democrat draw the perpendicular PH, then, since of, PH are perpendiculars on OB, and OP is bisected in I, it is easy to see that IH equals if. Again, since OP, OG are bisected in I, F, if equals PG, that is, if equals the radius. Hence the distance of I from the foot of each perpendicular, and from the middle point of each side, is equals the radius. In like manner, if OC be bisected in K, then AC equals the radius. Hence we have the following theorem: the 9 points made up of the feet of the perpendiculars, the middle points of the sides, and the middle points of the lines from the vertices to the orthocenter, are concyclic. DEF, the circle through these 9 points, is called the 9-point circle of the triangle. 5. The circumcircle of a triangle is the 9-point circle of each of the 4 triangles formed by joining the centers of the inscribed and escribed circles. 6. The distances between the vertices of a triangle and its orthocenter are respectively the doubles of the perpendiculars from the circumcenter on the sides. 7. The radius of the 9-point circle of a triangle is equal to half its circumradius. Prop. 6. Problem. In a given circle, ABCD, to inscribe a square. Solution: draw any 2 diameters AC, BD at right angles to each other. Join AB, BC, CD, da ABCD is a square. Democrat, let O be the center. Then the 4 angles at O, being right angles, are equal. Hence the arcs on which they stand are equal 3xxvi, and hence the 4 chords are equal 3xxix. Therefore the figure ABCD is equilateral. Again, because AC is a diameter, the angle ABC is right 3xxxi. In like manner the remaining angles are right. Hence ABCD is a square. Prop. 7. Problem. About a given circle, ABCD, to describe a square. Solution: through the center O draw any 2 diameters at right angles to each other, and draw at the points A, B, C, D the lines E, F, FG, GH touching the circle. EFGH is a square. Democrat, because AE touches the circle at A, the angle EAO is right 318, and therefore equal to BOC, which is right, constant. Hence AE is parallel to OB. In like manner EB is parallel to AO, and since AO is equal to OB, the figure AOBE is a lozenge, and the angle AOB is right, hence AOBE is a square. In like manner each of the figures BC, CD, DA is a square. Hence the whole figure is a square. COR, the circumscribed square, is double of the inscribed square. Prop. 8. Problem. In a given square, ABCD, to inscribe a circle. Solution: bisect, see last diagram, 2 adjacent sides A, F in the points A, B, and through A, B draw the lines AC, BD, respectively parallel to F, E, then O, the point of intersection of these parallels, is the center of the required circle. Democrat, because AOBE is a parallelogram, its opposite sides are equal, therefore AO is equal to EB, but EB is half the side of the given square, therefore AO is equal to half the side of the given square, and so in like manner is each of the lines OB, OC, OD, therefore the 4 lines OA, OB, OC, OD are all equal, and since they are perpendicular to the sides of the given square, the circle described with O as center, and OA as radius, will be inscribed in the square. Prop. 9 problem. About a given square, ABCD, to describe a circle. Solution: draw the diagonals AC, BD intersecting in O, C diagram to proposition 6. O is the center of the required circle. Democrat: since ABC is an isosceles triangle, and the angle B is right, each of the other angles is half a right angle, therefore BO is half a right angle. In like manner ABO is half a right angle, hence the angle BO equal ABO, therefore I6. AO is equal to OB. In like manner OB is equal to OC, and OC to OD. Hence the circle described, with O as center and OA as radius, will pass through the points B, C, D, and be described about the square. Prop. X problem. To construct an isosceles triangle having each base angle double the vertical angle. Solution: take any line of B, divide it in C, so that the rectangle of BC shall be equal to AC 211. With A as center, and AB as radius, describe the circle BDE, and in it place the chord BD equal to ACI. Join AD. ADB is a triangle fulfilling the required conditions. Democrat: join CD. About the triangle ACD, describe the circle CDEV. Then, because the rectangle of BC is equal to AC2, constant, and that AC is equal to BD, constant, therefore the rectangle of BC is equal to BD2. Hence 3xxxii. BD touches the circle ACD. Hence the angle BDC is equal to the angle A in the alternate segment 3xxxii. To each add CDA, and we have the angle BDA equal to the sum of the angles CDA and A, but the exterior angle BCD of the triangle ACD is equal to the sum of the angles CDA and A. Hence the angle BDA is equal to BCD, but since AB is equal to AD, the angle BDA is equal to ABD, therefore the angle CBD is equal to BCD. Hence I6. BD is equal to CD, but BD is equal to AC, constant, therefore AC is equal to CD, and therefore IV the angle CDA is equal to A, but BDA has been proved to be equal to the sum of CDA and A. Hence BDA is double of A. Hence each of the base angles of the triangle ABD is double of the vertical angle. Exercises. 1. Prove that ACD is an isosceles triangle whose vertical angle is equal to 3 times each of the base angles. 2. Prove that BD is the side of a regular decagon inscribed in the circle BDE. 3. If DB, D, F be consecutive sides of a regular decagon inscribed in a circle, prove BFBD equals radius of circle. 4. If E be the second point of intersection of the circle ACD with BDE, D is equal to DB, and if AE, B, CE, D be joined, each of the triangles ACE, 8 is congruent with ABD. 5. AC is the side of a regular pentagon inscribed in the circle ACD, and EB the side of a regular pentagon inscribed in the circle BDE. 6. Since ACE is an isosceles triangle, EB2EA2 equals AB.BC, that is equals BD2, therefore EB2BD2 equals EA2, that is, the square of the side of a pentagon inscribed in a circle exceeds the square of the side of the decagon inscribed in the same circle by the square of the radius. Prop. 11. Problem. To inscribe a regular pentagon in a given circle, ABCDE. Solution: construct an isosceles triangle X, having each base angle double the vertical angle, and inscribe in the given circle a triangle ABD equiangular to it. Bisect the angles DAB, ABD by the lines AC, B. Join EA, ED, DC, CB, then the figure ABCDE is a regular pentagon. Democrat: because each of the base angles BAD, ABD is double of the angle ADB, and the lines AC, B bisect them, the 5 angles BAC, CAD,
ADB, DBE, EBA are all equal, therefore the arcs on which they stand are equal, and therefore the 5 chords, AB, BC, CD, D, EA are equal. Hence the figure ABCDE is equilateral. Again, because the arcs AB, D are equal, adding the arc BCD to both, the arc ABCD is equal to the arc BCDE, and therefore 3xxVII the angles AED, BE, which stand on them, are equal. In the same manner it can be proved that all the angles are equal, therefore the figure ABCDE is equiangular. Hence it is a regular pentagon. Exercises. 1. The figure formed by the 5 diagonals of a regular pentagon is another regular pentagon. 2. If the alternate sides of a regular pentagon be produced to meet, the 5 points of meeting form another regular pentagon. 3. Every 2 consecutive diagonals of a regular pentagon divide each other in extreme and mean ratio. 4. Being given a side of a regular pentagon, construct it. 5. Divide a right angle into 5 equal parts. Prop. 12. Problem. To describe a regular pentagon about a given circle, ABCDE. Solution. Let the 5 points A, B, C, D, E on the circle be the vertices of any inscribed regular pentagon. At these points draw tangents FG, GH, Hi, IJ, JF. The figure FG is a circumscribed regular pentagon. Democrat. Let O be the center of the circle. Join OE, OA, OB. Now, because the angles A, E of the quadrilateral AOEF are right angles 318, the sum of the 2 remaining angles AOE, AFE is 2 right angles. In like manner the sum of the angles AOB, AGB is 2 right angles, therefore the sum of AOE, AFE is equal to the sum of AOB, AGB, but the angles AOE, AOB are equal, because they stand on equal arcs AE, of 3xxVII. Hence the angle AFE is equal to AGB. In like manner the remaining angles of the figure FG are equal. Therefore it is equiangular. Again, join of, OG. Now the triangles EOF, AOF have the sides AF, Phi equal 317, EX1 and FO common, and the base AO equal to the base EO. Hence the angle AFO is equal to EFOI8. Therefore the angle AFO is half the angle AFE. In like manner AGO is half the angle AGB, but AFE has been proved equal to AGB, hence AFO is equal to AGO, and FAO is equal to GAO, each being right, and AO common to the 2 triangles FAO, GAO, hence IXXVI the side AF is equal to AG, therefore GF is double AF. In like manner JF is double F, but AF is equal to F, hence GF is equal to JF. In like manner the remaining sides are equal, therefore the figure FG is equilateral, and it has been proved equiangular. Hence it is a regular pentagon. This proposition is a particular case of the following general theorem, of which the proof is the same as the foregoing. If tangents be drawn to a circle, at the angular points of an inscribed polygon of any number of sides, they will form a regular polygon of the same number of sides circumscribed to the circle. Prop. 13. Problem. To inscribe a circle in a regular pentagon, ABCDE. Solution. Bisect 2 adjacent angles A, B by the lines AO, BO, then O, the point of intersection of the bisectors, is the center of the required circle. Democrat. Join CO, and let fall perpendiculars from O on the 5 sides of the pentagon. Now the triangles ABO, CBO have the side of equal to BC, hip, and BO common, and the angle ABO equal to CBO, constant. Hence the angle BO is equal to BCOI4, but BO is half BE, constant. Therefore BCO is half BCD, and therefore CO bisects the angle BCD.
In like manner it may be proved that do bisects the angle D, and EO the angle E. Again, the triangles BOF, BOG have the angle F equal to G, each being right, and OBF equal to OBG, because OB bisects the angle ABC, constant, and OB common, hence IXXVI of is equal to OG. In like manner all the perpendiculars from O on the sides of the pentagon are equal, hence the circle whose center is O, and radius of, will touch all the sides of the pentagon, and will therefore be inscribed in it. In the same manner a circle may be inscribed in any regular polygon. Prop. 14 Problem. To describe a circle about a regular pentagon, ABCDE. Solution: bisect two adjacent angles A, B by the lines AO, BO. Then O, the point of intersection of the bisectors, is the center of the required circle. Democrat join OC, OD, OE. Then the triangles ABO, CBO have the side of equal to BC, hip, BO common, and the angle ABO equal to CBO, constant. Hence the angle BO is equal to BCOI4, but the angle BA is equal to BCD, hip, and since BO is half BA, constant, BCO is half BCD. Hence CO bisects the angle BCD. In like manner it may be proved that DO bisects CDE, and EO the angle DIA. Again, because the angle AB is equal to ABC, their halves are equal. Hence OAB is equal to OBA, therefore I6. OA is equal to OB. In like manner the lines OC, OD, OE are equal to one another and to OA. Therefore the circle described with O as center, and OA as radius, will pass through the points B, C, D, E, and be described about the pentagon. In the same manner a circle may be described about any regular polygon. Propositions 13, 14. Are particular cases of the following theorem: a regular polygon of any number of sides has one circle inscribed in it, and another described about it, and both circles are concentric. Prop. 15 Problem. In a given circle, def, to inscribe a regular hexagon. Solution: take any point A in the circumference, and join it to O, the center of the given circle, then with A as center, and AO as radius, describe the circle OBF, intersecting the given circle in the points B, F join OB, of, and produce AO, BO, FO to meet the given circle again in the points D, E, C join AB, BC, CD, D, F, FA, def is the required hexagon. Democrat each of the triangles AOB, AOF is equilateral, see Democrat, II. Hence the angles AOB, AOF are each 1/3 of two right angles, therefore AOF is 1/3 of two right angles. Again, the angles BOC, COD, DO are I15 respectively equal to the angles EOF, FOA, AOB. Therefore the six angles at the center are equal, because each is 1/3 of two right angles. Therefore the six chords are equal 3xxix. Hence the hexagon is equilateral. Again, since the arc AF is equal to ED, to each add the arc ABCD, then the whole arc FAB is equal to ABCDE, therefore the angles DEF, EFA which stand on these arcs are equal 3xxVII. In the same manner it may be shown that the other angles of the hexagon are equal. Hence it is equiangular, and is therefore a regular hexagon inscribed in the circle. COR1 The side of a regular hexagon inscribed in a circle is equal to the radius. COR2 If three alternate angles of a hexagon be joined, they form an inscribed equilateral triangle. Exercises. 1. The area of a regular hexagon inscribed in a circle is equal to twice the area of an equilateral triangle inscribed in the circle, and the square of the side of the triangle is 3 times the square of the side of the hexagon. 2. If the diameter of a circle be produced to C until the produced part is equal to the radius, the two tangents from C and their chord of contact form an equilateral triangle. 3. The area of a regular hexagon inscribed in a circle is half the area of an equilateral triangle, and 3/4 of the area of a regular hexagon circumscribed to the circle. Prop. 16. Problem. To inscribe a regular polygon of 15 sides in a given circle. Solution. Inscribe a regular pentagon ABCDE in the circle 11, and also an equilateral triangle Act 2. Join CG. CG is a side of the required polygon. Democrat. Since ABCDE is a regular pentagon, the arc ABC is THS of the circumference, and since AC is an equilateral triangle, the arc ABG is RD of the circumference. Hence the arc GC, which is the difference between these two arcs, is equal to THS RD, or TH of the entire circumference, and therefore, if chords equal to GCI be placed round the circle, we shall have a regular polygon of 15 sides, or quindecagon, inscribed in it. Scholium. Until the year 1801 no regular polygon could be described by constructions employing the line and circle only, except those discussed in this book, and those obtained from them by the continued bisection of the arcs of which their sides are the chords. But in that year the celebrated Gauss proved that if 2n+1 be a prime number, regular polygons of 2n+1 sides are inscriptable by elementary geometry. For the case n equals 4, which is the only figure of this class except the pentagon for which a construction has been given, see note at the end of this work. Questions for examination on Book 4. 1. What is the subject matter of Book 4? 2. When is one rectilineal figure said to be inscribed in another? 3. When circumscribed? 4. When is a circle said to be inscribed in a rectilineal figure? 5. When circumscribed about it? 6. What is meant by reciprocal propositions? ANS. In reciprocal propositions, to every line in one there corresponds a point in the other, and, conversely, to every point in one there corresponds a line in the other. 7. Give instances of reciprocal propositions in Book 4. 8. What is a regular polygon? 9. What figures can be inscribed in, and circumscribed about, a circle by means of Book 4? 10. What regular polygons has Gauss proved to be inscriptable by the line and circle? 11. What is meant by inscribed circles? 12. How many circles can be described to touch three lines forming a triangle? 13. What is the centroid of a triangle? 14. What is the orthocenter? 15. What is the circumcenter? 16. What is the polar circle? 17. When is the polar circle imaginary? 18. What is the 9-point circle? 19. Why is it so called? 20. Name the special 9 points through which it passes. 21. What three regular figures can be used in filling up the space round a point? ANS equilateral triangles, squares, and hexagons. 22. If the sides of a triangle be 13, 14, 15, what are the values of the radii of its inscribed and inscribed circles? 23. What is the radius of the circumscribed circle? 24. What is the radius of its 9-point circle? 25. What is the distance between the centers of its inscribed and circumscribed circles? 26. If r be the radius of a circle, what is the area of its inscribed equilateral triangle, of its inscribed square, its inscribed pentagon, its inscribed hexagon, its inscribed octagon, its inscribed decagon? 27. With the same hypothesis, find the sides of the same regular figures. Exercises on Book 4. 1. If a circumscribed polygon be regular, the corresponding inscribed polygon is also regular, and conversely. 2. If a circumscribed triangle be isosceles, the corresponding inscribed triangle is isosceles, and conversely. 3. If the two isosceles triangles in EX2 have equal vertical angles, they are both equilateral. 4. Divide an angle of an equilateral triangle into 5 equal parts. 5. Inscribe a circle in a sector of a given circle. 6. The line D is parallel to the base BC of the triangle ABC. Prove that the circles described about the triangles ABC, 8 touch at A7. The diagonals of a cyclic quadrilateral intersect in E. Prove that the tangent at E to the circle about the triangle AB is parallel to CD. 8. Inscribe a regular octagon in a given square. 9. A line of given length slides between two given lines. Find the locus of the intersection of perpendiculars from its extremities to the given lines. 10. If the perpendicular to any side of a triangle at its middle point meet the internal and external bisectors of the opposite angle in the points D and E, prove that D, E are points on the circumscribed circle. 11. Through a given point P draw a chord of a circle so that the intercept F may subtend a given angle x12. In a given circle inscribe a triangle having two sides passing through two given points, and the third parallel to a given line. 13. Given 4 points, no 3 of which are collinear, describe a circle which shall be equidistant from them. 14. In a given circle inscribe a triangle whose 3 sides shall pass through 3 given points. 15. Construct a triangle, being given the radius of the inscribed circle, the vertical angle, and the perpendicular from the vertical angle on the base. The base, the sum or difference of the other sides, and the radius of the inscribed circle, or of one of the inscribed circles. The centers of the inscribed circles. 16. If F be the middle point of the base of a triangle, D the diameter of the circumscribed circle which passes through F, and L the point where a parallel to the base through the vertex meets D, prove dL.Phi is equal to the square of half the sum, and dF.Le equal to the square of half the difference of the two remaining sides. 17. If from any point within a regular polygon of n sides perpendiculars be let fall on the sides, their sum is equal to n times the radius of the inscribed circle. 18. The sum of the perpendiculars let fall from the angular points of a regular polygon of n sides on any line is equal to n times the perpendicular from the center of the polygon on the same line. 19. If r denotes the radius of the circle circumscribed about a triangle ABC, r the radii of its inscribed and inscribed circles, delta the perpendiculars from its circumcenter on the sides, mu the segments of these perpendiculars between the sides and circumference of the circumscribed circle. We have the relations r plus r equals 4r plus r, 1, mu plus mu equals 2r, 2, delta plus delta equals r plus r, 3, the relation, 3, supposes that the circumcenter is inside the triangle. 20. Through a point D, taken on the side BC of a triangle ABC, is drawn a transversal EDF, and circles described about the triangles DBF, ECD. The locus of their second point of intersection is a circle. 21. In every quadrilateral circumscribed about a circle, the middle points of its diagonals and the center of the circle are collinear. 22. Find on a given line a point P, the sum or difference of whose distances from two given points may be given. 23. Find a point such that, if perpendiculars be let fall from it on 4 given lines, their feet may be collinear. 24. The line joining the orthocenter of a triangle to any point P, in the circumference of its circumscribed circle, is bisected by the line of collinearity of perpendiculars from P on the sides of the triangle. 25. The orthocenters of the 4 triangles formed by any 4 lines are collinear. 26. If a semicircle and its diameter be touched by any circle, either internally or externally, twice the rectangle contained by the radius of the semicircle, and the radius of the tangential circle, is equal to the rectangle contained by the segments of any secant to the semicircle, through the point of contact of the diameter and touching circle. 27 If ρ be the radii of two circles, touching each other at the center of the inscribed circle of a triangle, and each touching the circumscribed circle, prove and state and prove corresponding theorems for the ascribed circles. 28 If from any point in the circumference of the circle, circumscribed about a regular polygon of n sides, lines be drawn to its angular points, the sum of their squares is equal to 2n times the square of the radius. 29 In the same case, if the lines be drawn from any point in the circumference of the inscribed circle, prove that the sum of their squares is equal to n times the sum of the squares of the radii of the inscribed and the circumscribed circles. 30 State the corresponding theorem for the sum of the squares of the lines drawn from any point in the circumference of any concentric circle. 31 If from any point in the circumference of any concentric circle perpendiculars be let fall on all the sides of any regular polygon, the sum of their squares is constant. 32 For the inscribed circle, the constant is equal to times the square of the radius. 33 For the circumscribed circle, the constant is equal to n times the square of the radius of the inscribed circle, together with n times the square of the radius of the circumscribed circle. 34 If the circumference of a circle whose radius is r be divided into 17 equal parts, and AO be the diameter drawn from one of the points of division, A, and if ρ1, ρ2, ρ8 denote the chords from O to the points of division, A1, A2, A8 on one side of AO, then Democrat let the supplemental chords corresponding to ρ1, ρ2, and C, be denoted by R1, R2, and C, then 3xxxv. Ex2, we have ρ1 R1 equals RR2, ρ2 R2 equals RR4, ρ4 R4 equals RR8, ρ8 R8 equals RR1, hence ρ1 ρ2 ρ4 ρ8 equals R4. And it may be proved in the same manner that ρ1 ρ2 ρ3 ρ4 ρ5 ρ6 ρ7 ρ8 equals R8. Therefore ρ3 ρ5 ρ6 ρ7 equals R4. 35 If from the middle point of the line joining any two of four concyclic points a perpendicular be let fall on the line joining the remaining two, the six perpendiculars thus obtained are concurrent. 36 The greater the number of sides of a regular polygon circumscribed about a given circle, the less will be its perimeter. 37 The area of any regular polygon of more than four sides circumscribed about a circle is less than the square of the diameter. 38 Four concyclic points taken 3 by 3 determine four triangles, the centers of whose 9-point circles are concyclic. 39 If two sides of a triangle be given in position, and if their included angle be equal to an angle of an equilateral triangle, the locus of the center of its 9-point circle is a right line. 40 If, in the hypothesis and notation of Ex34, alpha, beta denote any two suffixes whose sum is less than 8, and of which alpha is the greater, for instance, ρ1 ρ4 equals R, ρ3 plus ρ5, 3xxxv, ex7. In the same case, if the suffixes be greater than 8, for instance, ρ8 ρ2 equals R, ρ6 ρ7, 3xxxv, ex6. 41 Two lines are given in position, draw a transversal through a given point, forming with the given lines a triangle of given perimeter. 42 Given the vertical angle and perimeter of a triangle, constructed with either of the following data: 1 the bisector of the vertical angle, 2 the perpendicular from the vertical angle on the base, 3 the radius of the inscribed circle. 43 In a given circle inscribe a triangle so that two sides may pass through two given points, and that the third side may be a maximum or a minimum. 44 If S be the semiperimeter of a triangle, R, 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 the radii of its ascribed circles, 45. The feet of the perpendiculars from the extremities of the base on either bisector of the vertical angle, the middle point of the base, and the foot of the perpendicular from the vertical angle on the base, are concyclic. 46. Given the base of a triangle and the vertical angle, find the locus of the center of the circle passing through the centers of the ascribed circles. 47. The perpendiculars from the centers of the ascribed circles of a triangle on the corresponding sides are concurrent. 48. If AB be the diameter of a circle, and PQ any chord cutting AB in O, and if the lines AP, AQ intersect the perpendicular to AB at O, in D and E respectively, the points A, B, D, E are concyclic. 49. If the sides of a triangle be in arithmetical progression, and if R be the radii of the circumscribed and inscribed circles, then 6RR is equal to the rectangle contained by the greatest and least sides. 50. Inscribe in a given circle a triangle having its three sides parallel to three given lines. 51. If the sides of B, C, and C, of a regular pentagon be bisected in the points A, B, C, D, E, and if the two pairs of alternate sides, BC, AE, AB, D, meet in the points A, E, respectively, prove 52. In a circle, prove that an equilateral inscribed polygon is regular, and also an equilateral circumscribed polygon, if the number of sides be odd. 53. Prove also that an equiangular circumscribed polygon is regular, and an equiangular inscribed polygon, if the number of sides be odd. 54. The sum of the perpendiculars drawn to the sides of an equiangular polygon from any point inside the figure is constant. 55. Express the sides of a triangle in terms of the radii of its ascribed circles. Book V Theory of Proportion ________________________ definitions. Introduction. Every proposition in the theories of ratio and proportion is true for all descriptions of magnitude. Hence it follows that the proper treatment is the algebraic. It is, at all events, the easiest and the most satisfactory. Euclid's proofs of the propositions, in the theory of proportion, possess at present none but a historical interest, as no student reads them now. But although his demonstrations are abandoned, his propositions are quoted by every writer, and his nomenclature is universally adopted. For these reasons it appears to us that the best method is to state Euclid's definitions, explain them, or prove them when necessary, for some are theorems under the guise of definitions, and then supply simple algebraic proofs of his propositions. A less magnitude is said to be a part or submultiple of a greater magnitude, when the less measures the greater, that is, when the less is contained a certain number of times exactly in the greater. 2. A greater magnitude is said to be a multiple of a less when the greater is measured by the less, that is, when the greater contains the less a certain number of times exactly. 3. Ratio is the mutual relation of two magnitudes of the same kind with respect to quantity. 4. Magnitudes are said to have a ratio to one another when the less can be multiplied so as to exceed the greater. These definitions require explanation, especially DEF 3, which has the fault of conveying no precise meaning, being, in fact, unintelligible. The following annotations will make them explicit. 1. If an integer be divided into any number of equal parts, 1, or the sum of any number of these parts, is called a fraction. Thus, if the line AB represent the integer, and if it be divided into 4 equal parts in the points C, D, E, then AC is AD, AE. Thus, a fraction is denoted by two numbers parted by a horizontal line. The lower, called the denominator, denotes the number of equal parts into which the integer is divided, and the upper, called the numerator, denotes the number of these equal parts which are taken. Hence it follows, that if the numerator be less than the denominator, the fraction is less than unity. If the numerator be equal to the denominator, the fraction is equal to unity, and if greater than the denominator, it is greater than unity. It is evident that a fraction is an abstract quantity, that is, that its value is independent of the nature of the integer which is divided. 2. If we divide each of the equal parts AC, CD, D, EB into 2 equal parts, the whole, AB, will be divided into 8 equal parts, and we see that AC equals, AD equals, AE equals, AB equals. Now, we saw in 1, that AE equals of the integer, and we have just shown that it is equal to. Hence equals, but would be got from by multiplying its terms, numerator and denominator, by 2. Hence we infer generally that multiplying the terms of any fraction by 2 does not alter its value. In like manner it may be shown that multiplying the terms of a fraction by any whole number does not alter its value. Hence it follows conversely, that dividing the terms of a fraction by a whole number does not alter the value. Hence we have the following important and fundamental theorem: 2 transformations can be made on any fraction without changing its value, namely, its terms can be either multiplied or divided by any whole number, and in either case the value of the new fraction is equal to the value of the original one. 3. If we take any number, such as 3, and multiply it by any whole number, the product is called a multiple of 3. Thus 6, 9, 12, 15, and c, are multiples of 3, but 10, 13, 17, and c, are not, because the multiplication of 3 by any whole number will not produce them. Conversely, 3 is a submultiple, or measure, or part of 6, 9, 12, 15, and c, because it is contained in each of these without a remainder, but not of 10, 13, 17, and c, because in each case it leaves a remainder. 4. If we consider 2 magnitudes of the same kind, such as 2 lines of CD, and if we suppose that AB is equal to of CD, it is evident, if AB be divided into 3 equal parts, and CD into 4 equal parts, that one of the parts into which AB is divided is equal to one of the parts into which CD is divided. And as there are 3 parts in AB, and 4 in CD, we express this relation by saying that AB has to CD the ratio of 3 to 4, and we denote it thus, 3, 4. Hence the ratio 3, 4 expresses the same idea as the fraction. In fact, both are different ways of expressing and writing the same thing. When written 3, 4 it is called a ratio, and when a fraction. In the same manner it can be shown that every ratio whose terms are commensurable can be converted into a fraction, and, conversely, every fraction can be turned into a ratio. From this explanation we see that the ratio of any 2 commensurable magnitudes is the same as the ratio of the numerical quantities which denote these magnitudes. Thus, the ratio of 2 commensurable lines is the ratio of the numbers which express their lengths, measured with the same unit. And this may be extended to the case where the lines are incommensurable. Thus, if A be the side and B the diagonal of a square, the ratio of A, B is when 2 quantities are incommensurable, such as the diagonal and the side of a square, although their ratio is not equal to that of any 2 commensurable numbers, yet a series of pairs of fractions can be found whose difference is continually diminishing, and which ultimately becomes indefinitely small, such that the ratio of the incommensurable quantities is greater than 1, and less than the other fraction of each pair. These fractions are called convergents. By their means we can approximate as nearly as we please to the exact value of the ratio. In the case of the diagonal and the side of a square, the following are the pairs of convergence and the ratio is intermediate to each pair. It is evident we may continue the series as far as we please. Now if we denote the first of any of the foregoing pairs of fractions by, the second will be, and in general, in the case of 2 incommensurable quantities, 2 fractions, and can always be found, where n can be made as large as we please, one of which is less and the other greater than the true value of the ratio. For let A and B be the incommensurable quantities, then, evidently, we cannot find two multiples Na, Mb, such that Na equals Mb. In this case, take any multiple of A, such as Na, then this quantity must lie between some two consecutive multiples of B, such as Mb, and M plus 1, B, therefore is greater than unity, and less than unity. Hence lies between and. Now, since the difference between and namely, becomes small as n increases, we see that the difference between the ratio of two incommensurable quantities and that of two commensurable numbers m and n can be made as small as we please. Hence, ultimately, the ratio of incommensurable quantities may be regarded as the limit of the ratio of commensurable quantities. 5. The two terms of a ratio are called the antecedent and the consequent. These correspond to the numerator and the denominator of a fraction. Hence we have the following definition: a ratio is the fraction got by making the antecedent the numerator and the consequent the denominator. 6. The reciprocal of a ratio is the ratio obtained by interchanging the antecedent and the consequent. Thus, 4:3 is the reciprocal of the ratio 3:4. Hence we have the following theorem: the product of a ratio and its reciprocal is unity. 7. If we multiply any two numbers, as 5 and 7, by any number such as 4, the products 20, 28 are called equimultiples of 5 and 7. In like manner, 10 and 15 are equimultiples of 2 and 3, and 18 and 30 of 3 and 5, and cv. The first of four magnitudes has to the second the same ratio which the third has to the fourth, when any equimultiples whatsoever of the first and third being taken, and any equimultiples whatsoever of the second and fourth, if, according as the multiple of the first is greater than, equal to, or less than the multiple of the second, the multiple of the third is greater than, equal to, or less than the multiple of the fourth. 6 magnitudes which have the same ratio are called proportionals. When four magnitudes are proportionals, it is usually expressed by saying, the first is to the second as the third is to the fourth eighth. Analogy or proportion is the similitude of ratios. We have given the foregoing definitions in the order of Euclid, as given by Simpson, Lardner, and others, 2 except that 8 is put before 7, because it relates, as v and 6, to the equality of ratios, whereas 7 is a test of their inequality. But it is evidently an inverted order, 4, 6. 8 are definitions of proportion, and v is only a test of proportion, and is not a definition but a theorem, and one which, instead of being taken for granted, requires proof. The following explanations will give the student clear conceptions of their meaning. 1. If we take two ratios, such as 6, 9 and 10, 15, which are each equal to the same thing, in this example each is equal to, they are equal to one another, axiom I. Then we may write it thus. This would be the most intelligible way, but it is not the usual one, which is as follows: 6, 9, 10, 15. In this form it is called a proportion. Hence a proportion consists of two ratios which are asserted by it to be equal. Its four terms consist of two antecedents and two consequents. The first and third terms are the antecedents, and the second and fourth the consequents. Also the first and last terms are called the extremes, and the two middle terms the means. 2. Since a proportion consists of two equal ratios, and each ratio can be written as a fraction, whenever we have a proportion such as we can write it in the form of two equal fractions. Thus, conversely, an equation between two fractions can be put into a proportion. By means of these simple principles all the various properties of proportion can be proved in the most direct and easy manner. 3. If we take the proportion a, b, c, d, and multiply the first and third terms, each by m, and second and fourth, each by n, we get the four multiples, ma, nb, mc, nd, and we want to prove that if ma is greater than nb, mc is greater than nd, if equal, equal, and if less, less. Democrat since a, b, c, d, we have equals. Hence, multiplying each by we get equals. Now, it is evident that if is greater than unity, is greater than unity, but if is greater than unity, ma is greater than nb, and if is greater than unity, mc is greater than nd. In like manner, if ma be equal to nb, mc is equal to nd, and if less, less. The foregoing is an easy proof of the converse of the theorem which is contained in Euclid's celebrated fifth definition. Next, to prove Euclid's theorem that if, according as the multiple of the first of four magnitudes is greater than, equal to, or less than the multiple of the second, the multiple of the third is greater than, equal to, or less than the multiple of the fourth, the ratio of the first to the second is equal to the ratio of the third to the fourth. Democrat let a, b, c, d be the four magnitudes. First suppose that a and b are commensurable, then it is evident that we can take multiples na, mb, such that na equals mb. Hence, by hypothesis, nc equals md. Thus, therefore equals. Next, suppose a and b are incommensurable. Then, as in a recent note, we can find two numbers m and n, such that is greater than unity, but less than unity. Hence lies between and. Now, since by hypothesis, when is greater than unity, is greater than unity, and when is less than unity, is less than unity. Hence, since lies between and, lies between the same quantities. Therefore the difference between and is less than, and since n may be as large as we please, the difference is nothing, therefore 7. When of the multiples of four magnitudes, taken as in DEFV, the multiple of the first is greater than that of the second, but the multiple of the third not greater than that of the fourth, the first has to the second a greater ratio than the third has to the fourth. This, instead of being a definition, is a theorem. We have altered the last clause from that given in Simpson's Euclid, which runs thus: the first is said to have to the second a greater ratio than the third has to the fourth. This is misleading, as it implies that it is, by convention, that the first ratio is greater than the second, whereas, in fact, such is not the case, for it follows from the hypothesis that the first ratio is greater than the second, and if it did not, it could not be made so by definition. We have made a similar change in the enunciation of the fifth definition. Let a, b, c, d be the four magnitudes, and m and n the multiples taken. It is required to prove that if ma be greater than nb, but mc not greater than nd, that the ratio a, b is greater than the ratio c, d. Democrat since ma is greater than nb, but mc not greater than nd, it is evident that is greater than, therefore is greater than, that is, the ratio a, b is greater than the ratio c, d. 9. Proportion consists of three terms at least. This has the same fault as some of the others: it is not a definition, but an inference. It occurs when the means in a proportion are equal, so that, in fact, there are four terms. As an illustration, let us take the numbers 4, 6, 9. Here the ratio of 4, 6 is, and the ratio of 6, 9 is, so that 4, 6, 9 are continued proportionals, but, in reality, there are four terms, for the full proportion is 4, 6, 6, 9. X. When three magnitudes are continual proportionals, the first is said to have to the third the duplicate ratio of that which it has to the second. 11. When four magnitudes are continual proportionals, the first is said to have to the fourth the triplicate ratio of that which it has to the second. 12. When there is any number of magnitudes of the same kind greater than 2, the first is said to have to the last the ratio compounded of the ratios of the first to the second, of the second to the third, of the third to the fourth, and c. We have placed these definitions in a group, but their order is inverted, and, as we shall see, DEF 12 is a theorem, and X and 11 are only inferences from it. 1. If we have two ratios, such as 5, 7 and 3, 4, and if we convert each ratio into a fraction, and multiply these fractions together, we get a result which is called the ratio compounded of the two ratios, viz. In this example it is, or 15, 28. It is evident we get the same result if we multiply the two antecedents together for a new antecedent, and the two consequents for a new consequent. Hence we have the following definition: the ratio compounded of any number of ratios is the ratio of the product of all the antecedents to the product of all the consequents. 2. To prove the theorem contained in DEF 12. Let the magnitudes be A, B, C, D. Then the ratio of first, second equals, second, third equals, third, fourth equals. Hence the ratio compounded of the ratio of first, second, of second, third, of third, fourth 3. If three magnitudes be proportional, the ratio of the first, third is equal to the square of the ratio of the first, second. For the ratio of the first, third is compounded of the ratio of the first, second, and of the ratio of the second, third, and since these ratios are equal, the ratio compounded of them will be equal to the square of one of them. Or thus, let the proportionals be A, B, C, that is, let A, B, B, C, hence we have n multiplying each by, we get or A, C, A2, B2 that is, first, third, square of first, square of second. Now, the ratio of first, third is, by DEFX, the duplicate ratio of first, second. Hence the duplicate ratio of two magnitudes means the square of their ratio, or, what is the same thing, the ratio of their squares, see Book 6xx. For if four magnitudes be continual proportionals, the ratio of first, fourth is equal to the cube of the ratio of first, second. This may be proved exactly like 3. Hence we see that what Euclid calls triplicate ratio of two magnitudes is the ratio of their cubes, or the cube of their ratio. We also see that there is no necessity to introduce extraneous magnitudes for the purpose of defining duplicate and triplicate ratios, as Euclid does. In fact, the definitions by squares and cubes are more explicit. 13. In proportionals, the antecedent terms are called homologous to one another, as also the consequents to one another. If one proportion be given, from it an indefinite number of other proportions can be inferred, and a great part of the theory of proportion consists in proving the truth of these derived proportions. Geometers make use of certain technical terms to denote the most important of these processes. We shall indicate these terms by including them in parentheses in connection with the propositions to which they refer. They are useful as indicating, by one word, the whole enunciation of a theorem. Every proposition in the fifth book is a theorem. Prop. I theorem. If any number of magnitudes of the same kind, A, B, C, and C, be equimultiples of as many others, A, B, C, and C, then the sum of the first magnitudes, A plus B plus C, and C, shall be the same multiple of the sum of the second, which any magnitude of the first system is of the corresponding magnitude of the second system. Democrat, let M denote the multiple which the magnitudes of the first system are of those of the second system. Then we have A equals mod, hip, B equals MB, C equals MC. And C, and C. Hence, by addition, Prop. 2 theorem. If two magnitudes of the same kind, A, B, be the same multiples of another, C, which two corresponding magnitudes, A, B, are of another, C, then the sum of the two first is the same multiple of their submultiple which the sum of their corresponding magnitudes is of their submultiple. Democrat let M and N be the multiples which A and B are of C. Then we have therefore hence A plus B is the same multiple of C that A plus B is of C. This proposition is evidently true for any number of multiples. Prop. 3 theorem. If two magnitudes, A, B, be equimultiples of two others, A, B, then any equimultiples of the first magnitudes, A, B, will be also equimultiples of the second magnitudes, A, B. Democrat let M denote the multiples which A, B are of A, B, then we have hence, multiplying each equation by N, we get hence, NA, NB are equimultiples of A, B. Prop. 4 theorem. If four magnitudes be proportional, and if any equimultiples of the first and third be taken, and any other equimultiples of the second and fourth, then the multiple of the first, the multiple of the second, the multiple of the third, the multiple of the fourth. Let A, B, C, D, then mod, NB, MC, and D. Democrat we have A, B, C, D, hip, therefore equals. Hence, multiplying each fraction by, we get equals, therefore mod, NB, MC, and D. Prop. V theorem. If two magnitudes of the same kind, A, B, be the same multiples of another, C, which two corresponding magnitudes, A, B, are of another, C, then the difference of the two first is the same multiple of their submultiple, C, which the difference of their corresponding magnitudes is of their submultiple, C, compare proposition 2. Democrat let M and N be the multiples which A and B are of C. Then we have A equals MC, and A equals MC, B equals NC, and B equals NC. Therefore, AB equals MN, C, and AB equals MN, C. Hence AB is the same multiple of C that AB is of C. COR if AB equals C, AB equals C, for if AB equals C, MN equals 1. Prop. 6 theorem. If a magnitude, A, be the same multiple of another, B, which a magnitude, A, taken from the first is of a magnitude, B, taken from the second, the remainder is the same multiple of the remainder that the whole is of the whole, compare proposition I. Democrat let M denote the multiples which the magnitudes A are of B, B, then we have A equals MB, A equals MB. Hence, A equals M, BB. PROPA theorem, Simpson. If two ratios be equal, then according as the antecedent of the first ratio is greater than, equal to, or less than its consequent, the antecedent of the second ratio is greater than, equal to, or less than its consequent. Democrat let A, B, C, D, then equals, and if A be greater than B, is greater than unity, therefore is greater than unity, and C is greater than D. In like manner, if A be equal to B, C is equal to D, and if less, less. PROPB theorem, Simpson. If two ratios are equal their reciprocals are equal, invert endo. Let A, B, C, D, then B, A, D, C. Democrat since A, B, C, D, then equals, therefore 1 divided by equals 1 divided by, or equals hence B, A, D, C. PROPC theorem, Simpson. If the first of four magnitudes be the same multiple of the second which the third is of the fourth, the first is to the second as the third is to the fourth. Let A equals MB, C equals MD, then A, B, C, D. Democrat. Since A equals MB, we have equals M. In like manner, equals M, therefore equals. Hence A, B, C, D. PROPD theorem, Simpson. If the first be to the second as to the third is to the fourth, and if the first be a multiple or submultiple of the second, the third is the same multiple or submultiple of the fourth. 1. Let A, B, C, D, and let A be a multiple of B, then C is the same multiple of D. Democrat. Let A equals MB, then equals M, but equals, therefore equals M, and C equals MD too. Let A equals, then equals, therefore equals, hence C equals. Prop. 7 Theorem. 1. Equal magnitudes have equal ratios to the same magnitude. 2. The same magnitude has equal ratios to equal magnitudes. Let A and B be equal magnitudes, and C any other magnitude. Then 1. A, C, B, C, 2 C, A, C, B. Democrat. Since A equals B, dividing each by C, we have therefore A, C, B, C again. Since A equals B, dividing C by each, we have therefore C, A, C, B. Observation 2 follows at once from 1 by proposition B. Prop. 8 Theorem. 1 of two unequal magnitudes, the greater has a greater ratio to any third magnitude than the less has. 2. Any third magnitude has a greater ratio to the less of two unequal magnitudes than it has to the greater. 1. Let A be greater than B, and let C be any other magnitude of the same kind, then the ratio A, C is greater than the ratio B, C. Democrat. Since A is greater than B, dividing each by C, therefore the ratio A, C is greater than the ratio B, C2. To prove that the ratio C, B is greater than the ratio C, A. Democrat. Since B is less than A, the quotient which is the result of dividing any magnitude by B is greater than the quotient which is got by dividing the same magnitude by A, therefore is greater than. Hence the ratio C, B is greater than the ratio C, A. Prop. 9 Theorem. Magnitudes which have equal ratios to the same magnitude are equal to one another. 2. Magnitudes to which the same magnitude has equal ratios are equal to one another. 1. If A, C, B, C, to prove A equals B. Democrat. Since A, C, B, C, equals. Hence, multiplying each by C, we get A equals B2. If C, A, C, B, to prove A equals B. Democrat. Since C, A, C, B, by inversion, A, C, B, C, therefore A equals B1. Prop. X Theorem. Of two unequal magnitudes, that which has the greater ratio to any third is the greater of the two, and that to which any third has the greater ratio is the less of the two. 1. If the ratio A, C be greater than the ratio B, C, to prove A greater than B. Democrat. Since the ratio A, C is greater than the ratio B, C, hence, multiplying each by C, we get A greater than B2. If the ratio C, B is greater than the ratio C, A, to prove B is less than A. Democrat. Since the ratio C, B is greater than the ratio C, A, hence 1 divided by is less than 1 divided by, that is less than. Hence, multiplying each by C, we get Prop. 11 Theorem. Ratios that are equal to the same ratio are equal to one another. Let A, B, E, F, and C, D, E, F, to prove A, B, C, D. Democrat. Since A, B, E, F, equals. In like manner, equals. Hence equals I, axiom I, N A, B, C, D prop. 12 theorem. If any number of ratios be equal to one another, any one of these equal ratios is equal to the ratio of the sum of all the antecedents to the sum of all the consequents. Let the ratios A, B, C, D, E, F, be all equal to one another. It is required to prove that any of these ratios is equal to the ratio A plus C plus E, B plus D plus F. Democrat by hypotheses. Since these fractions are all equal, let their common value be R, then we have equals R, equals R, equals R, therefore A equals BR, C equals DR, E equals FR, therefore A plus C plus E equals B plus D plus F, R. Hence equals R, therefore equals, and A plus C plus E, B plus D plus F COR with the same hypotheses. If L, M, and B any three multipliers, A, B, La plus MC plus NE, LB plus MD plus NF. Prop. 13 theorem. If two ratios are equal, and if one of them be greater than any third ratio, then the other is also greater than that third ratio. If A, B, C, D, but the ratio of C, D greater than the ratio of E, F, then the ratio of A, B is greater than the ratio of E, F. Democrat since the ratio of C, D is greater than the ratio of E, F, again, since A, B, C, D, equals, therefore is greater than, or the ratio of A, B is greater than the ratio of E, F prop. 14 theorem. If two ratios be equal, then, according as the antecedent of the first ratio is greater than, equal to, or less than the antecedent of the second, the consequent of the first is greater than, equal to, or less than the consequent of the second. Let A, B, C, D, then if A be greater than C, B is greater than D, if equal, equal, if less, less. Democrat since A, B, C, D we have equals, and multiplying each by we get times equals times, or equals, therefore A, C, B, D. Hence, proposition A, if A be greater than C, B is greater than D, if equal, equal, and if less, less. Prop. 15 theorem. Magnitudes have the same ratio which all equimultiples of them have. Let A, B be two magnitudes, then the ratio A, B is equal to the ratio ma, MB. Democrat the ratio A, B equals, and the ratio of ma, MB equals, but since the value of a fraction is not altered by multiplying its numerator and denominator by the same number, equals, therefore A, B, ma, MB prop. 16 theorem. If four magnitudes of the same kind be proportionals, they are also proportionals by alternation, alternando. Let A, B, C, D, then A, C, B, D. Democrat since A, B, C, D, and multiplying each by, we get equals, or equals, therefore A, C, B, D prop. 17 theorem. If four magnitudes be proportional, the difference between the first and second, the difference between the third and fourth, the fourth, dividendo. Let A, B, C, D, then A, B, B, C, D, D, Democrat since A, B, C, D, equals, therefore 1 equals 1, or equals, therefore A, B, B, C, D, D prop. 18 theorem. If four magnitudes be proportionals, the sum of the first and second, the sum of the third and fourth, the fourth, componendo. Let A, B, C, D, then A plus B, B, C plus D, D. Democrat since A, B, C, D, equals, therefore plus 1 equals plus 1, or equals, therefore A plus B, B, C plus D, D prop. 19 Theorem. If a whole magnitude be to another whole at a magnitude taken from the first it to a magnitude taken from the second, the first remainder, the second remainder, the first whole, the second whole. Let A, B, C, D, C and D being less than A and B, then A C, B D, A, B democrat since A, B, C, D, then A, C, B, D alternando, and C, A, D, B invert endo, therefore equals, and 1 equals 1, or equals. Hence AC, BD, A, BPROPE theorem, Simpson. If four magnitudes be proportional, the first, its excess above the second, the third, its excess above the fourth, convert endo. Let A, B, C, D, then A, B, C, C D democrat since A, B, C, D, equals, therefore equals democrat of 17, therefore divided by, or equals, therefore A, B, C, C D. Prop. XX theorem. If there be two sets of three magnitudes, which taken 2 by 2 in direct order have equal ratios, then if the first of either set be greater than the third, the first of the other set is greater than the third, if equal, equal, and if less, less. Let A, B, C, A, B, C be the two sets of magnitudes, and let the ratio A, B equals A, B, and B, C equals B, C, then, if A be greater than, equal to, or less than C, A will be greater than, equal to, or less than C. Democrat since A, B, we have equals, in like manner, equals, hence times equals times, or equals. Therefore if A be greater than C, A is greater than C, if equal, equal, and if less, less. Prop. XXI theorem. If there be two sets of three magnitudes, which taken 2 by 2 in transverse order have equal ratios, then, if the first of either set be greater than the third, the first of the other set is greater than the third, if equal, equal, and if less, less. Let A, B, C, A, B, C be the two sets of magnitudes, and let the ratio A, B equals B, C, and B, C equals A, B. Then, if A be greater than, equal to, or less than C, A will be greater than, equal to, or less than C. Democrat since A, B, C, we have equals. In like manner, equals. Hence, multiplying equals. Therefore, if A be greater than C, A is greater than C, if equal, equal, if less, less. Prop. XXII theorem. If there be two sets of magnitudes, which, taken 2 by 2 in direct order, have equal ratios, then the first, the last of the first set, the first, the last of the second set, x equally, or x equo. Let A, B, C, A, B, C be the two sets of magnitudes, and if A, B, and B, C, B, C, then A, C, Democrat since A, B, we have equals in like manner, equals. Hence, multiplying, equals. Therefore A, C, and similarly for any number of magnitudes in each set. COR1 if the ratio B, C be equal to the ratio A, B, then A, B, C will be in continued proportion, and so will A, B, C. Hence DEF 12. Annotation 3, but equals. XXII therefore equals. Hence, if A, B, A, B, A2, B2, A2, B2 or if four magnitudes be proportional, their squares are proportional. COR2 if four magnitudes be proportional, their cubes are proportional. Prop. XXIII theorem. If there be two sets of magnitudes, which, taken 2 by 2 in transverse order, have equal ratios, then the first, the last of the first set, the first, the last of the second set, ex equo perturbato. Let A, B, C, A, B, C be the two sets of magnitudes, and let the ratio A, B equals B, C, and B, C equals A, B, then A, C, C. Democrat since A, B, B, C, we have equals. In like manner, equals. Hence, multiplying, equals, therefore A, C, and similarly for any number of magnitudes in each set. This proposition and the preceding one may be included in one enunciation, thus, ratios compounded of equal ratios are equal. Prop. XXIV theorem. If two magnitudes of the same kind, A, B, have to a third magnitude, C, ratios equal to those which two other magnitudes, A, B, have to a third, C, then the sum, A plus B, of the first two has the same ratio to their third, C, which the sum, A plus B, of the other two magnitudes has to their third, C. Democrat since A, C, we have equals. In like manner, equals, therefore, adding, equals. Hence A plus B, C, A plus B, C. Prop. XXV theorem. If four magnitudes of the same kind be proportionals, the sum of the greatest and least is greater than the sum of the other two. Let A, B, C, D, then, if A be the greatest, D will be the least 14 and A. It is required to prove that A plus D is greater than B plus C. Democrat since A, B, C, D, A, C, B, D alternando, therefore A, AC, B, B D E dot, but A is greater than B, hip, therefore AC is greater than B D 14. Hence A plus D is greater than B plus C. Questions for examination on Book V1. What is the subject matter of this book? 2. When is one magnitude said to be a multiple of another? 3. What is a submultiple or measure? 4. What are equimultiples? 5. What is the ratio of two commensurable magnitudes? 6. What is meant by the ratio of incommensurable magnitudes? 7. Give an illustration of the ratio of incommensurables. 8. What are the terms of a ratio called? 9. What is a ratio of greater inequality? 10. What is a ratio of lesser inequality? 11. What is the product of two ratios called? ANS. The ratio compounded of these ratios. 12. What is duplicate ratio? 13. What is Euclid's definition of duplicate ratio? 14. Give another definition. 15. Define triplicate ratio. 16. What is proportion? ANS equality of ratios. 17. Give Euclid's definition of proportion. 18. How many ratios in a proportion? 19. What are the Latin terms in use to denote some of the propositions of Book V? 20. When is a line divided harmonically? 21. When a line is divided harmonically, what are corresponding pairs of points called? ANS harmonic conjugates. 22. What are reciprocal ratios? 23. Give one enunciation that will include propositions XXII, XXIII. Of Book V. Exercises on Book V. DEFI. A ratio whose antecedent is greater than its consequent is called a ratio of greater inequality, and a ratio whose antecedent is less than its consequent, a ratio of lesser inequality. DEF to a right line is said to be cut harmonically when it is divided internally and externally in any ratios that are equal in magnitude. 1. A ratio of greater inequality is increased by diminishing its terms by the same quantity, and diminished by increasing its terms by the same quantity. 2. A ratio of lesser inequality is diminished by diminishing its terms by the same quantity, and increased by increasing its terms by the same quantity. 3. If four magnitudes be proportionals, the sum of the first and second is to their difference as the sum of the third and fourth is to their difference, componendo et dividendo. 4. If two sets of four magnitudes be proportionals, and if we multiply corresponding terms together, the products are proportionals. 5. If two sets of four magnitudes be proportionals, and if we divide corresponding terms, the quotients are proportionals. 6. If four magnitudes be proportionals, their squares, cubes, and c, are proportionals. 7. If two proportions have three terms of one respectively equal to three corresponding terms of the other, the remaining term of the first is equal to the remaining term of the second. 8. If three magnitudes be continual proportionals, the first is to the third as the square of the difference between the first and second is to the square of the difference between the second and third. 9. If a line of B, cut harmonically in C and D, be bisected in O, prove OC, OB, OD are continual proportionals. 10. In the same case, if O be the middle point of CD, prove OO2 equals OB2 plus OD2. 11. And AB, AC plus AD, equals 2AC.AD, or plus equals. 12. And CD, AD plus BD, equals 2AD.BD, or plus equals. 13. And AB.CD equals 2AD.CB. Book 6. Application of the theory of proportion underscore 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 definitions. Similar rectilineal figures are those whose several angles are equal, each to each, and whose sides about the equal angles are proportional. Similar figures agree in shape, if they agree also in size, they are congruent. 1. When the shape of a figure is given, it is said to be given in species. Thus a triangle whose angles are given is given in species. Hence similar figures are of the same species. 2. When the size of a figure is given, it is said to be given in magnitude, for instance, a square whose side is of given length. 3. When the place which a figure occupies is known, it is said to be given in position. 2. A right line is said to be cut at a point in extreme and mean ratio when the whole line is to the greater segment as the greater segment is to the less. 3. If three quantities of the same kind be in continued proportion, the middle term is called a mean proportional between the other two. Magnitudes in continued proportion are also said to be in geometrical progression. 4. If four quantities of the same kind be in continued proportion, the two middle terms are called two mean proportionals between the other two. V. The altitude of any figure is the length of the perpendicular from its highest point to its base. 6. Two corresponding angles of two figures have the sides about them reciprocally proportional, when a side of the first is to a side of the second as the remaining side of the second is to the remaining side of the first. This is evidently equivalent to saying that a side of the first is to a side of the second in the reciprocal ratio of the remaining side of the first to the remaining side of the second. Prop. I theorem. Triangles, ABC, ACD, and parallelograms, EC, CF, which have the same altitude are to one another as their bases, BC, CD. Democrat produce BD both ways, and cut off any number of parts BG, GH, and C, each equal to CB, and any number DK, KL, each equal to CD. Join AG, AK, AL. Now, since the several bases CB, BG, GH are all equal, the triangles ACB, ABG, AC are also all equal I/38. Therefore the triangle ACH is the same multiple of ACB that the base CH is of the base CB. In like manner, the triangle ACL is the same multiple of ACD that the base CL is of the base CD, and it is evident that I/38 if the base HC be greater than CL, the triangle HAC is greater than CAL, if equal, equal, and if less, less. Now we have four magnitudes, the base BC is the first, the base CD the second, the triangle ABC the third, and the triangle ACD the fourth. We have taken equimultiples of the first and third, namely, the base CH, and the triangle ACH, also equimultiples of the second and fourth, namely, the base CL, and the triangle ACL, and we have proved that according as the multiple of the first is greater than, equal to, or less than the multiple of the second, the multiple of the third is greater than, equal to, or less than the multiple of the fourth. Hence VDEFV the base BC, CD, the triangle ABC, ACD. 2. The parallelogram EC is double of the triangle ABC I/30, and the parallelogram CF is double of the triangle ACD. Hence V15. EC, CF, the triangle ABC, ACD, but ABC, ACD, BC, CD, part I. Therefore V11. EC, CF, the base BC, CD. Or thus, let A denote the areas of the triangles ABC, ACD, respectively, and P their common altitude, then 2I, COR1, A equals P dot BC, A equals P dot CD. Hence equals, or A, BC, CD. In extending this proof to parallelograms we have only to use P instead of P prop. 2. Theorem. If a line, D, be parallel to a side, BC, of a triangle, ABC, it divides the remaining sides, measured from the opposite angle, A, proportionally, and, conversely, if two sides of a triangle, measured from an angle, be cut proportionally, the line joining the points of section is parallel to the third side. 1. It is required to prove that AD, DB, AE, EC Democrat join B, CD. The triangles BDE, said are on the same base D, and between the same parallels BC, D. Hence IXXXVII they are equal, and therefore V7 the triangle AD, BDE, AD, CDE, but AD, BDE, AD, DBI, and AD, CDE, AE, ECI. Hence AD, DB, AE, EC2. If AD, DB, AE, EC, it is required to prove that D is parallel to BC. Democrat let the same construction be made, then AD, DB, the triangle AD, BDEI, and AE, EC, the triangle AD, CDEI, but AD, DB, AE, EC, HIP. Hence AD, BDE, AD, CDE. Therefore V9 the triangle BDE is equal to CDE, and they are on the same base D, and on the same side of it, hence they are between the same parallels I/36. Therefore D is parallel to BC. Observation. The line D may cut the sides of AC produced through B, C, or through the angle A, but evidently a separate figure for each of these cases is unnecessary. Exercise. If two lines be cut by three or more parallels, the intercepts on one are proportional to the corresponding intercepts on the other. Prop. 3. Theorem. If a line, AD, bisect any angle, A, of a triangle, ABC, it divides the opposite side, BC, into segments proportional to the adjacent sides. Conversely, if the segments, BD, DC, into which a line, AD, drawn from any angle, A, of a triangle divides the opposite side B proportional to the adjacent sides, that line bisects the angle, A. Democrat 1. Through C draw CE parallel to AD, to meet BA produced in A. Because BA meets the parallels AD, EC, the angle BAD IXXIX is equal to AEC, and because AC meets the parallels AD, EC, the angle DAC is equal to ACE, but the angle BAD is equal to DAC, HIP, therefore the angle ACE is equal to AEC, therefore AE is equal to ACI6. Again, because AD is parallel to EC, one of the sides of the triangle BEC, BD, DC, BA, AE2, but AE has been proved equal to AC. Therefore BD, DC, BA, AC2. If BD, DC, BA, AC, the angle BAC is bisected. Democrat let the same construction be made. Because AD is parallel to EC, BA, AE, BD, DC2, but BD, DC, BA, AC, HIP. Therefore V11. BA, AE, BA, AC, and hence V9. AE is equal to AC, therefore the angle AEC is equal to ACE, but AEC is equal to BAD IXXIX, and ACE to DAC, hence BAD is equal to DAC, and the line AD bisects the angle BAC. Exercises. 1. If the line AD bisect the external vertical angle CAE, BA, AC, BD, DC, and conversely. Democrat cut off AE equals AC join ED. Then the triangles ACD, AED are evidently congruent, therefore the angle EDB is bisected, hence 3. BA, AE, BD, DA, or BA, AC, BD, DC. 2. Exercise 1 has been proved by quoting proposition 3. Prove it independently, and prove 3. As an inference from it. 3. The internal and the external bisectors of the vertical angle of a triangle divide the base harmonically, see definition, p. 191. 4. Any line intersecting the legs of any angle is cut harmonically by the internal and external bisectors of the angle. 5. Any line intersecting the legs of a right angle is cut harmonically by any two lines through its vertex which make equal angles with either of its sides. 6. If the base of a triangle be given in magnitude and position, and the ratio of the sides, the locus of the vertex is a circle which divides the base harmonically in the ratio of the sides. 7. If A, B, C denote the sides of a triangle ABC, and D, D the points where the internal and external bisectors of a meet BC, prove 8. In the same case, if E, F, F be points similarly determined on the side CA, AB, respectively, prove plus plus equals 0, and plus plus equals 0. Prop. 4 theorem. The sides about the equal angles of equiangular triangles, BAC, CDE, are proportional, and those which are opposite to the equal angles are homologous. Democrat let the sides BC, CE, which are opposite to the equal angles A and D, be conceived to be placed so as to form one continuous line, the triangles being on the same side, and so that the equal angles BCA, said may not have a common vertex. Now, the sum of the angles ABC, BCA is less than 2 right angles, but BCA is equal to BED, HIP. Therefore the sum of the angles AB, BED is less than 2 right angles, hence axiom 12 the lines AB, ED will meet if produced. Let them meet in F. Again, because the angle BCA is equal to BEF, the line CAIXXVIII is parallel to F. In like manner, BF is parallel to CD, therefore the figure ACDF is a parallelogram, hence AC is equal to DF, and CD is equal to AF. Now, because AC is parallel to Φ, BA, AF, BC, CE2, but AF is equal to CD, therefore BA, CD, BC, CE, hence V16, AB, BC, DC, CE. Again, because CD is parallel to BF, BC, CE, FD, D, but FD is equal to AC, therefore BC, CE, AC, D, hence V16. BC, AC, CE, D. Therefore we have proved that AB, BC, DC, CE, and that BC, CA, CE, ed. Hence, X equally, AB, AC, DC, D. Therefore the sides about the equal angles are proportional. This proposition may also be proved very simply by superposition. Thus, see figure, Prop2. Let the two triangles be ABC, AD, let the second triangle AD be conceived to be placed on ABC, so that its two sides AD, AE may fall on the sides of AC, then, since the angle AD is equal to ABC, the side D is parallel to BC. Hence 2. AD, DB, AE, EC, hence AD, AB, AE, AC, and V16. AD, AE, AB, AC. Therefore the sides about the equal angles BAC, DE are proportional, and similarly for the others. It can be proved by this proposition that two lines which meet at infinity are parallel. 4. Let I denote the point at infinity through which the two given lines pass, and draw any two parallels intersecting them in the points A, B, then the triangles IB, AIB are equiangular, therefore AI, AB, AI, AB, but the first term of the proportion is equal to the third, therefore V14 the second term of is equal to the fourth AB, and, being parallel to it, the lines AA, BBIXXXIII are parallel. Exercises. 1. If two circles intercept equal chords of AB on any secant, the tangents at AT to the circles at the points of intersection are to one another as the radii of the circles. 2. If two circles intercept on any secant chords that have a given ratio, the tangents to the circles at the points of intersection have a given ratio, namely, the ratio compounded of the direct ratio of the radii and the inverse ratio of the chords. 3. Being given a circle and a line, prove that a point may be found, such that the rectangle of the perpendiculars let fall on the line from the points of intersection of the circle with any chord through the point shall be given. 4. AB is the diameter of a semicircle ADB, CD a perpendicular to AB, draw through AA chord AF of the semicircle meeting CD in E, so that the ratio CE, F may be given. Prop. V. Theorem. If two triangles, ABC, DEF, have their sides proportional, BA, AC, ED, DF, AC, CB, DF, Φ, they are equiangular, and those angles are equal which are subtended by the homologous sides. Democrat at the points D, E make the angles EDG, DEG equal to the angles A, B of the triangle ABC. Then IXXXII the triangles ABC, DEG are equiangular. Therefore BA, AC, ED, DG4, but BA, AC, ED, DF, HIP. Therefore DG is equal to DF. In like manner it may be proved that EG is equal to F. Hence the triangles EDF, EDG have the sides ED, DF in one equal to the sides ED, DG in the other, and the base F equal to the base EG. Hence I8 they are equiangular, but the triangle DEG is equiangular to ABC. Therefore the triangle DEF is equiangular to ABC. Observation in 6. DEFI2 conditions are laid down as necessary for the similitude of rectilineal figures. 1. The equality of angles, 2. The proportionality of sides. Now, from propositions 4 and v, we see that if two triangles possess either condition, they also possess the other. Triangles are unique in this respect. In all other rectilineal figures one of the conditions may exist without the other. Thus, two quadrilaterals may have their sides proportional without having equal angles, or vice versa. Prop. 6 theorem. If two triangles, ABC, def, have one angle, A, in one equal to one angle, D, in the other, and the sides about these angles proportional, BA, AC, ed, DF, the triangles are equiangular, and have those angles equal which are opposite to the homologous sides. Democrat make the same construction as in the last proposition, then the triangles ABC, DEG are equiangular. Therefore BA, AC, ed, DG4, but BA, AC, ed, DF, hip. Therefore DG is equal to DF. Again, because the angle EDG is equal to BAC, constant, and BAC equal to EDF, hip, the angle EDG is equal to EDF, and it has been proved that DG is equal to DF, and is common, hence the triangles EDG and EDF are equiangular, but EDG is equiangular to BAC. Therefore EDF is equiangular to BAC. It is easy to see, as in the case of proposition 4, that an immediate proof of this proposition can also be got from proposition 2. COR1 if the ratio of two sides of a triangle be given, and the angle between them, the triangle is given in species. Prop. 7 theorem. If two triangles, ABC, def, have one angle, A, one equal to one angle, D, in the other, the sides about two other angles, B, E, proportional, AB, BC, D, F, and the remaining angles, C, F, of the same species, i.e. either both acute or both not acute, the triangles are similar. Democrat if the angles B and E are not equal, one must be greater than the other. Suppose ABC to be the greater, and that the part ABG is equal to DEF, then the triangles ABG, DEF have two angles in one equal to two angles in the other, and are IXXXII equiangular. Therefore AB, BG, D, F4, but AB, BC, D, F, hip. Therefore BG is equal to BC. Hence the angles BCG, BGC must be each acute I17, therefore AGB must be obtuse, hence DFE, which is equal to it, is obtuse, and it has been proved that ACB is acute, therefore the angles ACB, DFE are of different species, but, hip, they are of the same species, which is absurd. Hence the angles B and E are not unequal, that is, they are equal. Therefore the triangles are equiangular. COR1 if two triangles ABC, DEF have two sides in one proportional to two sides in the other, AB, BC, D, F, and the angles A, D opposite one pair of homologous sides equal, the angles C, F opposite the other are either equal or supplemental. This proposition is nearly identical with 7. COR2 if either of the angles C, F be right, the other must be right. Prop. 8 theorem. The triangles, ACD, BCD, into which a right-angled triangle, ACB, is divided, by the perpendicular, CD, from the right angle, C, on the hypotenuse, are similar to the whole and to one another. Democrat since the two triangles ADC, ACB have the angle A common, and the angles ADC, ACB equal, each being right, they are IXXXII equiangular, henceforth they are similar. In like manner it may be proved that BDC is similar to ABC. Hence ADC, CDB are each similar to ACD, and therefore they are similar to one another. COR1 The perpendicular CD is a mean proportional between the segments AD, DB of the hypotenuse. 4. Since the triangles ADC, CDB are equiangular, we have AD, DC, DC, DB, hence DC is a mean proportional between AD, DB, DEF3. COR2BC is a mean proportional between AB, BD, and AC between AB, AD. COR3 The segments AD, DB are in the duplicate of AC, CB, or in other words, AD, DB, AC2, CB2, COR4BA, AD in the duplicate ratios of BA, AC, and AB, BD in the duplicate ratio of AB, BC. Prop. 9 Problem. From a given right line, AB, to cut off any part required, i.e. to cut off any required submultiple. Solution Let it be required, for instance, to cut off the fourth part. Draw AF, making any angle with AB, and in AF take any point C, and cut off, I3, the part CD, D, F each equal to AC. Join BF, and draw CG parallel to BF. AG is the fourth part of AB. Democrat since CG is parallel to the side BF of the triangle ABF, AC, AF, AG, AB2, but AC is the fourth part of AF, constant. Hence AG is the fourth part of AB, D. In the same manner, any other required submultiple may be cut off. Proposition X, Book I, is a particular case of this proposition. Prop. X problem. To divide a given undivided line, AB, similarly to a given divided line, CD. Solution Draw AG, making any angle with AB, and cut off the parts A, high, IG respectively equal to the part CE, F, FD of the given divided line CD. Join BG, and draw HK, IL, each parallel to BG. AB will be divided similarly to CD. Democrat through H. Draw HN parallel to AB, cutting IL in M. Now in the triangle ALI, HK is parallel to IL. Hence 2. AK, KL, A, high, that is, CE, F, constant. Again, in the triangle HNG, MI is parallel to NG. Therefore 2. MN, high, IG, but I-thirsive. Is equal to KL, MN is equal to LB, high is equal to F, and IG is equal to FD, constant. Therefore KL, LB, F, FD. Hence the line AB is divided similarly to the line CD. Exercises. 1. To divide a given line AB internally or externally in the ratio of two given lines, M, and solution through A and B. Draw any two parallels AC and BD in opposite directions. Cut off AC equals M, and BD equals N, and join CD. The joining line will divide AB internally at E in the ratio of M, and 2. If BD be drawn in the same direction with AC, as denoted by the dotted line, then CD will cut AB externally at E in the ratio of M, and CO are the 2 points E divide AB harmonically. This problem is manifestly equivalent to the following given the sum or difference of two lines and their ratio, to find the lines. 3. Any line AE, through the middle point B of the base DD of a triangle DCD, is cut harmonically by the sides of the triangle and a parallel to the base through the vertex. 4. Given the sum of the squares on two lines and their ratio, find the lines. 5. Given the difference of the squares on two lines and their ratio, find the lines. 6. Given the base and ratio of the sides of a triangle, construct it when any of the following data is given: 1. The area, 2. The difference on the squares of the sides, 3. The sum of the squares on the sides, 4. The vertical angle, 5. The difference of the base angles. Prop. 11. Problem. To find a third proportional to two given lines, x, y. Solution: draw any two lines AC, AE making an angle. Cut off of equal x, BC equal y, and AD equal y. Join BD, and draw CE parallel to BD, then D is the third proportional required. Democrat: in the triangle CAE, BD is parallel to CE, therefore AB, BC, AD, D2, but AB is equal to x, and BC, AD each equal to y. Therefore x, y, y, D. Hence D is a third proportional to x and y. Another solution can be inferred from proposition 8. For if AD, DC in that proposition be respectively equal to x and y, then DB will be the third proportional. Or again, if in the diagram, proposition 8, AD equals x, and AC equals y, AB will be the third proportional. Hence may be inferred a method of continuing the proportion to any number of terms. Exercises. 1. If AO omega be a triangle, having the side A omega greater than AO, then if we cut off AB equals AO, draw BB parallel to AO, cut off BC equals BB, and C, the series of lines AB, BC, CD, and C, are in continual proportion. 2. Of BC, AB, A omega. This is evident by drawing through B a parallel to A omega. Prop. 12. Problem. To find a fourth proportional to three given lines, x, y, z. Solution: draw any two lines AC, AE, making an angle, then cut off of equal x, BC equal y, AD equal z. Join BD, and draw CE parallel to BD. D will be the fourth proportional required. Democrat: since BD is parallel to CE, we have 2. AB, BC, AD, D, therefore x, y, z, D. Hence D is a fourth proportional to x, y, z. Or thus, take two lines AD, BC intersecting in O, make OA equals x, OB equals y, OC equals z, and describe a circle through the points A, B, C. For V cutting AD in DOD will be the fourth proportional required. The demonstration is evident from the similarity of the triangles AOB and COD. Prop. 13. Problem. To find a mean proportional between two given lines. X, Y. Solution: take on any line AC parts of BC respectively equal to x, y. On AC describe a semicircle ADC. Erect BD at right angles to AC, meeting the semicircle in DBD will be the mean proportional required. Democrat: join AD, DC. Since ADC is a semicircle, the angle ADC is right 3xxxi. Hence, since ADC is a right-angled triangle, and BD a perpendicular from the right angle on the hypotenuse, BD is a mean proportional 8. COR1 between AB, BC, that is, BD is a mean proportional between x and y. Exercises. 1. Another solution may be inferred from proposition 8, COR2. 2. If through any point within a circle the chord be drawn, which is bisected in that point, its half is a mean proportional between the segments of any other chord passing through the same point. 3. The tangent to a circle from any external point is a mean proportional between the segments of any secant passing through the same point. 4. If through the middle point C of any arc of a circle any secant be drawn cutting the chord of the arc in D, and the circle again in E, the chord of half the arc is a mean proportional between CD and CE. 5. If a circle be described touching another circle internally and two parallel chords, the perpendicular from the center of the former on the diameter of the latter, which bisects the chords, is a mean proportional between the two extremes of the three segments into which the diameter is divided by the chords. 6. If a circle be described touching a semicircle and its diameter, the diameter of the circle is a harmonic mean between the segments into which the diameter of the semicircle is divided at the point of contact. 7. State and prove the proposition corresponding to EX5, for external contact of the circles. Prop. 14 Theorem. 1. Equiangular parallelograms, AB, CD, which are equal in area have the sides about the equal angles reciprocally proportional AC, CE, GC, CB. 2. Equiangular parallelograms which have the sides about the equal angles reciprocally proportional are equal in area. Democrat, let AC, CE be so placed as to form one right line, and that the equal angles ACB, ECG may be vertically opposite. Now, since the angle ACB is equal to ECG, to each add BCE, and we have the sum of the angles ACB, BCE equal to the sum of the angles ECG, BCE, but the sum of ACB, BCE is I13 two right angles. Therefore the sum of ECG, BCE is two right angles. Hence I14. BC, CG form one right line. Complete the parallelogram B. Again, since the parallelograms AB, CD are equal, HIP, AB, CF, CD, CFV7, but AB, CF, AC, CEI, and CD, CF, GC, CBI, therefore AC, CE, GC, CB, that is, the sides about the equal angles are reciprocally proportional. 2. Let AC, CE, GC, CB, to prove the parallelograms of CD are equal. Democrat, let the same construction be made. We have AB, CF, AC, CEI, and CD, CF, GC, CBI, but AC, CE, GC, CB, HIP. Therefore AB, CF, CD, CF. Hence AB equals CDV9, that is, the parallelograms are equal. Or thus, join he, B, HD, BD. The HC equals twice the HBE, and the CD equals twice the BDE. Therefore the HBE equals BDE, and I36. HD is parallel to B. Hence 2. May be proved by reversing this demonstration. Another demonstration of this proposition may be got by producing the lines HA and DG to meet in I. Then I slide the points I, C, F are collinear, and the proposition is evident. Prop. 15 Theorem. 1. Two triangles equal in area, ACB, DCE, which have one angle, C, in one equal to one angle, C, in the other, have the sides about these angles reciprocally proportional. 2. Two triangles, which have one angle in one equal to one angle in the other, and the sides about these angles reciprocally proportional, are equal in area. Democrat 1. Let the equal angles be so placed as to be vertically opposite, and that AC, CD may form one right line, then it may be demonstrated, as in the last proposition, that BC, CE form one right line. Join BD. Now since the triangles ACB, DCE are equal, ACB, BCD, DCE, BCDV7, but ACB, BCD, AC, CDI, and DCE, BCD, EC, CBI. Therefore AC, CD, EC, CB, that is, the sides about the equal angles are reciprocally proportional. 2. If AC, CD, EC, CB, to prove the triangle ACB equal to DCE. Democrat, let the same construction be made, then we have AC, CD, triangle ACB, BCDI, and EC, CB, triangle DCE, BCDI, but AC, CD, EC, CB, HIP. Therefore the triangle, hence the triangle ACB equals DCEV9. That is, the triangles are equal. This proposition might have been appended as a COR to the preceding, since the triangles are the halves of equiangular parallelograms, or it may be proved by joining AE, and showing that it is parallel to BD prop. 16 Theorem 1. If four right lines, AB, CD, E, F, be proportional, the rectangle, AB.F, contained by the extremes is equal to the rectangle, CD.E, contained by the means. 2. If the rectangle contained by the extremes of four right lines be equal to the rectangle contained by the means, the four lines are proportional. Democrat 1. Erect A, CI at right angles to AB and CD, and equal to F and E respectively, and complete the rectangles. Then because AB, CD, E, F, HIP, and that E is equal to CI, and F to A, constant, we have AB, CD, CI, A. Hence the parallelograms AG, CK are equiangular, and have the sides about their equal angles reciprocally proportional. Therefore they are 14 equal, but since A is equal to F, AG is equal to the rectangle AB.F. In like manner, CK is equal to the rectangle CD.E. Hence AB.F equals CD.E, that is, the rectangle contained by the extremes is equal to the rectangle contained by the means. 2. If AB.F equals CD.E, to prove AB, CD, E, F the same construction being made, because AB.F equals CD.E, and that F is equal to A, and E to CI, we have the parallelogram AG equals CK, and since these parallelograms are equiangular, the sides about their equal angles are reciprocally proportional. Therefore or thus, place the four lines in a concurrent position so that the extremes may form one continuous line, and the means another. Let the four lines so placed be AO, BO, OD, OC join AB, CD. Then because AO, OB, OD, OC, and the angle AOB equals DOC, the triangles AOB, COD are equiangular. Hence the 4 points A, B, C, D are concyclic. Therefore 3xxxv. AO.OC equals BO.OD. Prop. 17 Theorem 1. If three right lines, A, B, C, be proportional, the rectangle, A.C, contained by the extremes is equal to the square, B2, of the mean. 2. If the rectangle contained by the extremes of three right lines be equal to the square of the mean, the three lines are proportional. Democrat 1. Assume a line D equals B, then because A, B, B, C, we have A, B, D, C therefore 16. AC equals BD, but BD equals B2. Therefore AC equals B2, that is, the rectangle contained by the extremes is equal to the square of the mean. 2. The same construction being made, since AC equals B2, we have A.C equals B.D, therefore A, B, D, C, but D equals B. Hence A, B, B, C, that is, the three lines are proportionals. This proposition may be inferred as a COR to the last, which is one of the fundamental propositions in mathematics. Exercises. 1. If a line CD bisect the vertical angle C of any triangle ACB, its square added to the rectangle AD.DB contained by the segments of the base is equal to the rectangle contained by the sides. Democrat describe a circle about the triangle, and produce CD to meet it in E, then it is easy to see that the triangles ACD, ECB are equiangular. Henceforth, AC, CD, CE, CB, therefore AC.CB equals CE.CD equals CD2 plus CD.DE equals CD2 plus AD.DB 3xxxv. 2. If the lines CD bisect the external vertical angle of any triangle ACB, its square subtracted from the rectangle AD.DB is equal to AC.CB. 3. The rectangle contained by the diameter of the circumscribed circle, and the radius of the inscribed circle of any triangle, is equal to the rectangle contained by the segments of any chord of the circumscribed circle passing through the center of the inscribed. Democrat, let O be the center of the inscribed circle. Join OB, see foregoing figure, let fall the perpendicular OG, draw the diameter F of the circumscribed circle. Now the angle AB equals ECB 3xxvii, and ABO equals OBC, therefore EBO equals sum of OCB, OBC equals EOB. Hence EB equals EO. Again, the triangles EBF, OGC are equiangular, because EFB, ECB are equal, and EBF, OGC are each right. Therefore, F, EB, OC, OG, therefore F.OG equals EB.OC equals EO.OC. 4. EX may third be extended to each of the ascribed circles of the triangle ACB. 5. The rectangle contained by two sides of a triangle is equal to the rectangle contained by the perpendicular and the diameter of the circumscribed circle. 4. Let CE be the diameter. Join AE. Then the triangles ACE, DCB are equiangular, hence AC, CE, CD, CB, therefore AC.CB equals CD.CE. 6. If a circle passing through one of the angles A of a parallelogram ABCD intersect the two sides of AD again in the points E, G, and the diagonal AC again in F, then AB.AE plus AD.AG equals AC.AF. Democrat, join F, FG, and make the angle ABH equals AFE. Then the triangles ABH, AFE are equiangular. Therefore AB, AF, AE. Hence AB.AE equals AF.A. Again, it is easy to see that the triangles BCH, FAG are equiangular, therefore BC, CH, AF, AG, hence BC.AG equals AF.CH, or AD.AG equals AF.CH, but we have proved AB.AE equals AF.A. Hence AD.AG plus AB.AE equals AF.AC. 7. If the DF be parallels to the sides of a triangle ABC from any point D in the base, then AB.AE plus AC.AF equals AD2 plus BD.DC. This is an easy deduction from 6. 8. If through a point O within a triangle ABC parallels F, GH, IC to the sides be drawn, the sum of the rectangles of their segments is equal to the rectangle contained by the segments of any chord of the circumscribing circle passing through O. Democrat, AO.AL equals AB.AK plus AC.AE. 6. But AO2 equals AG.AK plus AH.AE go.O. 7. Hence AO.OL equals BG.AK plus CH.AE plus go.O, or AO.OL equals EO.A plus IO.OK plus go.O. 9. The rectangle contained by the side of an inscribed square standing on the base of a triangle, and the sum of the base and altitude, is equal to twice the area of the triangle. 10. The rectangle contained by the side of an ascribed square standing on the base of a triangle, and the difference between the base and altitude, is equal to twice the area of the triangle. 11. If from any point P in the circumference of a circle a perpendicular be drawn to any chord, its square is equal to the rectangle contained by the perpendiculars from the extremities of the chord on the tangent at P12.
If O be the point of intersection of the diagonals of a cyclic quadrilateral ABCD, the four rectangles of dot BC, BD.CD, CD.D, D.AB, are proportional to the four lines BO, CO, DO, AO. 13. The sum of the rectangles of the opposite sides of a cyclic quadrilateral ABCD is equal to the rectangle contained by its diagonals. Democrat make the angle DO equals CAB, then the triangles DO, CAB are equiangular, therefore AD, DO, AC, CB, therefore AD.BC equals AC.DO. Again, the triangles DAC, OAB are equiangular, and CD, AC, BO, AB, therefore AC.CD equals AC.BO. Hence AD.BC plus AB.CD equals AC.BD.33. This proposition is known as Ptolemy's theorem. 14. If the quadrilateral ABCD is not cyclic, prove that the three rectangles AB.CD, BC.AD, AC.BD are proportional to the three sides of a triangle which has an angle equal to the sum of a pair of opposite angles of the quadrilateral. 15. Prove by using theorem 11 that if perpendiculars be let fall on the sides and diagonals of a cyclic quadrilateral, from any point in the circumference of the circumscribed circle, the rectangle contained by the perpendiculars on the diagonals is equal to the rectangle contained by the perpendiculars on either pair of opposite sides. 16. If AB be the diameter of a semicircle, and PA, PB chords from any point P in the circumference, and if a perpendicular to AB from any point C meet PA, PB in D and E, and the semicircle in F, CF is a mean proportional between CD and CE. Prop. 18. Problem. On a given right line, AB, to construct a rectilineal figure similar to a given one, DIFC, and similarly placed as regards any side, CD, of the latter. DEF. Similar figures are said to be similarly described upon given right lines, when these lines are homologous sides of the figures. Solution. Join CE, CF, and construct a triangle ABH on AB equiangular to CDE, and similarly placed as regards CD, that is, make the angle ABH equal to CDE, and BA equal to DCE. In like manner construct the triangle high equiangular to ECF, and similarly placed, and lastly, the triangle IAJ equiangular and similarly placed with FCG. Then ABH is the figure required. Democrat. From the construction it is evident that the figures are equiangular, and it is only required to prove that the sides about the equal angles are proportional. Now because the triangle ABH is equiangular to CDE, AB, BH, CD, D4, hence the sides about the equal angles B and D are proportional. Again, from the same triangles we have BH, HA, D, EC, and from the triangles IHA, FEC, HA, HI, EC, F, therefore, X equally, BH, HI, D, F, that is, the sides about the equal angles B, DEF are proportional, and so in like manner are the sides about the other equal angles. Hence, DEFI, the figures are similar. Observation. In the foregoing construction, the line AB is homologous to CD, and it is evident that we may take AB to be homologous to any other side of the given figure DIFC. Again, in each case, if the figure ABH be turned round the line AB until it falls on the other side, it will still be similar to the figure DIFC. Hence on a given line AB there can be constructed two figures each similar to a given figure DIFC, and having the given line AB homologous to any given side CD of the given figure. The first of the figures thus constructed is said to be directly similar, and the second inversely similar to the given figure. These technical terms are due to Hamilton, see Elements of Quaternions, page 112. COR1. Twice as many polygons may be constructed on AB similar to a given polygon DIFC as that figure has sides.
COR2 if the figure ABHIJ be applied to DIFC so that the point A will coincide with C, and that the line AB may be placed along CD, then the points H, I, J will be respectively on the line CE, CF, CG, also the sides BH, Hi, IJ of the one polygon will be respectively parallel to their homologous sides DE, F, FG of the other. COR3 if lines drawn from any point O in the plane of a figure to all its angular points be divided in the same ratio, the lines joining the points of division will form a new figure similar to, and having every side parallel to, the homologous side of the original. Prop. 19 Theorem. Similar triangles, ABC, DEF, have their areas to one another in the duplicate ratio of their homologous sides. Democrat take BG a third proportional to BC, F11. Join AG. Then because the triangles ABC, DEF are similar, AB, BC, DE, F, hence, alternately, AB, DE, BC, F, but BC, F, F, BG, constant, therefore V11. AB, DE, F, BG, hence the sides of the triangles ABG, DEF about the equal angles B, E are reciprocally proportional, therefore the triangles are equal. Again, since the lines BC, F, BG are continual proportionals, BC, BG in the duplicate ratio of BC, FVDEFX, but BC, BG, triangle ABC, ABG. Therefore ABC, ABG in the duplicate ratio of BC, F, but it has been proved that the triangle ABG is equal to DEF. Therefore the triangle ABC is to the triangle DEF in the duplicate ratio of BC, F. This is the first proposition in Euclid in which the technical term duplicate ratio occurs. My experience with pupils is, that they find it very difficult to understand either Euclid's proof or his definition. On this account I submit the following alternative proof, which, however, makes use of a new definition of the duplicate ratio of two lines, viz. The ratio of the squares, see annotations on VDEFX, described on these lines. On AB and DE describe squares, and through C and F draw lines parallel to AB and DE, and complete the rectangles AI, DN. Now, the triangles JAC, ODF are evidently equiangular. Hence JA, AC, OD, DF4, but AC, AB, DF, DE4. Hence JA, AB, OD, DE, X equally, but AB equals AG, and DE equals DL, therefore JA, AG, OD, DL. Again, JA, AG, AI, square II, and OD, DL, DN, square DMI. Hence AI, DN, DM, therefore AI, DN, DMV16, hence ABC, DEF, UB2, DE2. Exercises. 1. If one of two similar triangles has its sides 50% or longer than the homologous sides of the other, what is the ratio of their areas? 2. When the inscribed and circumscribed regular polygons of any common number of sides to a circle have more than 4 sides, the difference of their areas is less than the square of the side of the inscribed polygon. Prop. XX theorem. Similar polygons may be divided, 1. Into the same number of similar triangles, 2. The corresponding triangles have the same ratio to one another which the polygons have, 3. The polygons are to each other in the duplicate ratio of their homologous sides. Democrat let ABHIJ, DIFC be the polygons, and let the sides AB, CD be homologous. Join AI, CE, CF1. The triangles into which the polygons are divided are similar. 4. Since the polygons are similar, they are equiangular, and have the sides about their equal angles proportional DEFI, hence the angle B is equal to D, and AB, BH, CD, D. Therefore 6 the triangle ABH is equiangular to CDE, hence the angle BHA is equal to DEC, but B is equal to DEF, HIP, therefore the angle AHI is equal to SEF. Again, because the polygons are similar, IH, HB, Phe, ED, and since the triangles ABH, CDE are similar, HB, HA, ED, EC, hence, X equally, IH, HA, Phe, EC, and the angle IHA has been proved to be equal to the angle FEC, therefore the triangles IHA, FEC are equiangular. In the same manner it can be proved that the remaining triangles are equiangular. 2. Since the triangle ABH is similar to CDE, we have 19. In like manner, AHI, SEF in the duplicate ratio of A, CE, hence ABH, CDE equals AHI, SEF V11. Similarly, AHI, SEF equals AIJ, CFG. In these equal ratios, the triangles ABH, AHI, AIJ are the antecedents, and the triangles CDE, SEF, CFG the consequents, and V12 any one of these equal ratios is equal to the ratio of the sum of all the antecedents to the sum of all the consequents, therefore the triangle ABH, the triangle CDE, the polygon ABHJ, the polygon CDFG. 3. The triangle ABH, CDE in the duplicate ratio of AB, CD19. Hence, 2, the polygon ABHJ, the polygon CDFG in the duplicate ratio of AB, CD. COR1 the perimeters of similar polygons are to one another in the ratio of their homologous sides. COR2 as squares are similar polygons, therefore the duplicate ratio of two lines is equal to the ratio of the squares described on them, compare annotations, VDEFX. COR3 similar portions of similar figures bear the same ratio to each other as the wholes of the figures. COR4 similar portions of the perimeters of similar figures are to each other in the ratio of the whole perimeters. Exercises. DEFI homologous points in the planes of two similar figures are such, that lines drawn from them to the angular points of the two figures are proportional to the homologous sides of the two figures. 1. If two figures be similar, to each point in the plane of one there will be a corresponding point in the plane of the other. Democrat let ABCD be the two figures, P a point in the plane of ABCD. Join AP, BP and construct a triangle APB on AB, similar to APB, then it is easy to see that lines from P to the angular points of ABCD are proportional to the lines from P to the angular points of ABCD. 2. If two figures be directly similar, and in the same plane, there is in the plane a special point which, regarded as belonging to either figure, is its own homologous point with respect to the other. 4. Let AB be two homologous sides of the figures, see their point of intersection. Through the two triads of points A, C, B, C describe two circles intersecting again in the point O will be the point required. For it is evident that the triangles OAB are similar and that either may be turned round the point O, so that the two bases, AB, will be parallel. DEF2 the point O is called the center of similitude of the figures. It is also called their double point. 3. Two regular polygons of n sides each have n centers of similitude. 4. If any number of similar triangles have their corresponding vertices lying on three given lines, they have a common center of similitude. 5. If two figures be directly similar, and have a pair of homologous sides parallel, every pair of homologous sides will be parallel. DEF3 two figures, such as those in 5, are said to be homothetic. 6. If two figures be homothetic, the lines joining corresponding angular points are concurrent, and the point of concurrence is the center of similitude of the figures. 7. If two polygons be directly similar, either may be turned round their center of similitude until they become homothetic, and this may be done in two different ways. 8. Two circles are similar figures. Democrat, let O be their centers, let the angle AOB be indefinitely small, so that the arc AB may be regarded as a right line, make the angle AOB equal to AOB, then the triangles AOB are similar. Again, make the angle BOC indefinitely small, and make BOC equal to it, the triangles BOC, BOC are similar. Proceeding in this way, we see that the circles can be divided into the same number of similar elementary triangles. Hence the circles are similar figures. 9 sectors of circles having equal central angles are similar figures. 10. As any 2 points of 2 circles may be regarded as homologous, 2 circles have in consequence an infinite number of centers of similitude, their locus is the circle, whose diameter is the line joining the 2 points for which the 2 circles are homothetic. 11. The areas of circles are to one another as the squares of their diameters. For they are to one another as the similar elementary triangles into which they are divided, and these are as the squares of the radii. 12. The circumferences of circles are as their diameters, cor1. 13. The circumference of sectors having equal central angles are proportional to their radii. Hence if A denote the arcs of 2 sectors, which subtend equal angles at the centers, and if R be their radii, equals. 14. The area of a circle is equal to half the rectangle contained by the circumference and the radius. This is evident by dividing the circle into elementary triangles, as in EX8. 15. The area of a sector of a circle is equal to half the rectangle contained by the arc of the sector and the radius of the circle. Prop. XXI theorem. Rectilineal figures, A, B, which are similar to the same figure, C, are similar to one another. Democrat, since the figures A and C are similar, they are equiangular, and have the sides about their equal angles proportional. In like manner B and C are equiangular, and have the sides about their equal angles proportional. Hence A and B are equiangular, and have the sides about their equal angles proportional. Therefore they are similar. COR two similar rectilineal figures which are homothetic to a third are homothetic to one another. Exercise. If 3 similar rectilineal figures be homothetic, 2 by 2, their 3 centers of similitudes are collinear. Prop. XXII theorem. If 4 lines, AB, CD, F, GH, be proportional, and any pair of similar rectilineal figures, ABK, CDL, be similarly described on the first and second, and also any pair, EI, GJ, on the third and fourth, these figures are proportional. Conversely, if any rectilineal figure described on the first of 4 right lines, the similar and similarly described figure described on the second, any rectilineal figure on the third, the similar and similarly described figure on the fourth, the 4 lines are proportional. Democrat 1 ABK, CDL, up to, CD2, XX, and EI, GJ, F2, GH2XX. But since AB, CD, F, GH, up to, CD2, F2, GH2 VXXII, COR1, therefore ABK, CDL, EI, GJ. If ABK, CDL, EI, GJ, AB, CD, F, GH. 3 Democrat 2 ABK, CDL, up to, CD2XX, and EI, GJ, F2, GH2XX, therefore up to, CD2, F2, GH2. hence AB, CD, F, GH. The enunciation of this proposition is wrongly stated in Simpson's Euclid, and in those that copy it. As given in those works, the four figures should be similar. Prop. XXIII theorem. Equiangular parallelograms, AD, CG, are to each other as the rectangles contained by their sides about a pair of equal angles. Democrat let the two sides of BC about the equal angles ABD, CBG, be placed so as to form one right line, then it is evident, as in Prop 14, that GB, BD form one right line. Complete the parallelogram BF. Now, denoting the parallelograms of BF, CG by X, Y, Z, respectively, we have X, Y, AB, BCI, Y, Z, BD, BGI. Hence XY, YZ, AB.BD, BC.BG, or X, Z, AB.BD, BC.BG. Observations: since AB.BD, BC.BG is compounded of the two ratios of BC and BD, BGVDEF of compound ratio, the enunciation is the same as if we said, in the ratio compounded of the ratios of the sides, which is Euclid's, but it is more easily understood as we have put it. Exercises. 1. Triangles which have one angle of one equal or supplemental to one angle of the other, are to one another in the ratio of the rectangles of the sides about those angles. 2. Two quadrilaterals whose diagonals intersect at equal angles are to one another in the ratio of the rectangles of the diagonals. Prop. XXIV theorem. In any parallelogram, AC, every two parallelograms, AF, FC, which are about a diagonal are similar to the whole and to one another. Democrat: since the parallelograms AC, AF have a common angle, they are equiangular ithirsive, and all that is required to be proved is, that the sides about the equal angles are proportional. Now, since the lines F, BC are parallel, the triangles AEF, ABC are equiangular, therefore for AE, F, AB, BC, and the other sides of the parallelograms are equal to AE, F, AB, BC, hence the sides about the equal angles are proportional, therefore the parallelograms AF, AC are similar. In the same manner the parallelograms AF, FC are similar. So are the parallelograms AF, FC, AC are, 2 by 2, homothetic. Prop. XXV problem. To describe a rectilineal figure equal to a given one, A, and similar to another given one, BCD. Solution: on any side BC of the figure BCD describe the rectangle B equal to BCD IXLV, and on CE describe the rectangle F equal to A between BC, CF find a mean proportional GH, and on it describe the figure GHI similar to BCD 18, so that BC and GH may be homologous sides. GHI is the figure required. Democrat: the three lines BC, GH, CF are in continued proportion, therefore BC, CF in the duplicate ratio of BC, GHVDEFX, and since the figures BCD, GHI are similar, BCD, GHI in the duplicate ratio of BC, GHXX, also BC, CF, rectangle B, rectangle F. Hence rectangle B, F, figure BCD, GHI, but the rectangle B is equal to the figure BCD, therefore the rectangle F is equal to the figure GHI, but F is equal to A, constant. Therefore the figure GHI is equal to A, and it is similar to BCD. Hence it is the figure required. Or thus, describe the squares EFJK, LMNO equal to the figures BCD and A respectively 214, then find GH a fourth proportional to F, LM, and BC 12. On GH describe the rectilineal figure GHI similar to the figure BCD 18, so that BC and GH may be homologous sides. GHI is the figure required. Democrat because F, LM, BC, GH, constant, the figure EFJK, LMNO, BCD, GHIXXII, but EFJK is equal to BCD, constant, therefore LMNO is equal to GHI, but LMNO is equal to A, constant. Therefore GHI is equal to A, and it is similar to BCD. Prop. XXVI theorem. If two similar and similarly situated parallelograms, AEFG, ABCD, have a common angle, they are about the same diagonal. Democrat draw the diagonals, see figure, PROPXXIV. AF, AC. Then because the parallelograms AEFG, ABCD are similar figures, they can be divided into the same number of similar triangles XX. Hence the triangle FAG is similar to CAD, and therefore the angle FAG is equal to the angle CAD. Hence the line AC must pass through the point F, and therefore the parallelograms are about the same diagonal. Observation proposition XXVI, being the converse of XXIV, has evidently been misplaced. The following would be a simpler enunciation: if two homothetic parallelograms have a common angle, they are about the same diagonal. Prop. XXVII problem. To inscribe in a given triangle, ABC, the maximum parallelogram having a common angle, B, with the triangle. Solution: bisect the side AC opposite to the angle B, at P, through P draw PE, PF parallel to the other sides of the triangle. BP is the parallelogram required. Democrat take any other point D in AC, draw DG, DH parallel to the sides, and CK parallel to AB, produce EP, GD to meet CK in K and J, and produce HD to meet PK in I. Now, since AC is bisected in P, EK is also bisected in P, hence I30 the parallelogram EO is equal to OK, therefore EO is greater than DK, but DK is equal to FD I slien, hence EO is greater than FD. To each add BO, and we have the parallelogram BP greater than BD. Hence BP is the maximum parallelogram which can be inscribed in the given triangle. COR1 the maximum parallelogram exceeds any other parallelogram about the same angle in the triangle, by the area of the similar parallelogram whose diagonal is the line between the middle point P of the opposite side and the point D, which is the corner of the other inscribed parallelogram. COR2 the parallelograms inscribed in a triangle, and having one angle common with it, are proportional to the rectangles contained by the segments of the sides of the triangle, made by the opposite corners of the parallelograms. COR3 the parallelogram AC, GH, AC2, AD.DC. Prop. XXVII problem. To inscribe in a given triangle, ABC, a parallelogram equal to a given rectilineal figure, X, not greater than the maximum inscribed parallelogram, and having an angle, B, common with the triangle. Solution: bisect the side AC opposite to B, at P draw PF, PE parallel to the sides of BC, then XXVII. BP is the maximum parallelogram that can be inscribed in the triangle ABC, and if X be equal to it, the problem is solved. If not, produce EP, and draw CJ parallel to PF, then describe the parallelogram KLMNXXV equal to the difference between the figure PJCF and X, and similar to PJCF, and so that the sides PJ and KL will be homologous, then cut off pi equal to KL, draw IH parallel to AB, cutting AC in D, and draw DG parallel to BC. BD is the parallelogram required. Democrat, since the parallelograms PC, PD are about the same diagonal, they are similar XXIV, but PC is similar to KPT, constant, therefore PD is similar to KN, and, constant, their homologous sides, pi and KL, are equal, hence XX. PD is equal to Kn. Now, PD is the difference between F and GHXXVII. COR1, and Kn is, constant, the difference between PC and X, therefore the difference between PC and X is equal to the difference between F and GH, but F is equal to PC. Hence GH is equal to X prop. XXIX problem. To ascribe to a given triangle, ABC, a parallelogram equal to a given rectilineal figure, X, and having an angle common with an external angle, B, of the triangle. Solution: the construction is the same as the last, except that, instead of making the parallelogram Kn equal to the excess of the parallelogram PC over the rectilineal figure X, we make it equal to their sum, and then make pi equal to KL, draw IH parallel to AB, and the rest of the construction as before. Democrat: now it can be proved, as in 2.6, that the parallelogram BD is equal to the gnomon OHJ, that is, equal to the difference between the parallelograms PD and PC, or the difference, constant, between Kn and PC, that is, constant, equal to X, and BD is ascribed to the triangle ABC, and has an angle common with the external angle B. Hence the thing required is done. Observation: the enunciations of the three foregoing propositions have been altered, in order to express them in modern technical language. Some writers recommend the student to omit them. We think differently. In the form we have given them, they are freed from their usual repulsive appearance. The constructions and demonstrations are Euclid's, but slightly modified. Prop. XXX theorem. To divide a given line, AB, in extreme and mean ratio. Solution: divide AB in C, so that the rectangle AB.BC may be equal to the square on AC 211. Then C is the point required. Democrat: because the rectangle AB.BC is equal to the square on AC AB, AC, BC 17. Hence AB is cut in extreme and mean ratio in CDEF2. Exercises. 1. If the three sides of a right-angled triangle be in continued proportion, the hypotenuse is divided in extreme and mean ratio by the perpendicular from the right angle on the hypotenuse. 2. In the same case, the greater segment of the hypotenuse is equal to the least side of the triangle. 3. The square on the diameter of the circle described about the triangle formed by the points F, H, D, see figure 211, is equal to 6 times the square on the line FD. Prop. XXXI theorem. If any similar rectilineal figure be similarly described on the three sides of a right-angled triangle, ABC, the figure on the hypotenuse is equal to the sum of those described on the two other sides. Democrat: draw the perpendicular CDI12. Then, because ABC is a right-angled triangle, and CD is drawn from the right angle perpendicular to the hypotenuse, BD, AD in the duplicate ratio of BA, AC8. COR4. Again, because the figures described on BA, AC are similar, they are in the duplicate ratio of BA, ACXX. Hence V11. BA, AD, figure described on BA, figure described on AC. In like manner, AB, BD, figure described on AB, figure described on BC. Hence VXXIV. AB, sum of AD and BD, figure described on the line AB, sum of the figures described on the lines AC, BC, but AB is equal to the sum of AD and BD. Therefore VA, the figure described on the line AB, is equal to the sum of the similar figures described on the lines AC and BC. Or thus, let us denote the sides by A, B, C, and the figures by alpha, beta, gamma. Then because the figures are similar, we have XX alpha, gamma, A2, C2 therefore equals. In like manner, equals, therefore equals, but A2 plus B2 equals C2 islai. Therefore alpha plus beta equals gamma, that is, the sum of the figures on the sides is equal to the figure on the hypotenuse. Exercise. If semicircles be described on supplemental chords of a semicircle, the sum of the areas of the two crescents thus formed is equal to the area of the triangle whose sides are the supplemental chords and the diameter. Prop. XXXII theorem. If two triangles, ABC, CDE, which have two sides of one proportional to two sides of the other, AB, BC, CD, D, and the contained angles, B, D, equal, be joined at an angle, C, so as to have their homologous sides parallel, the remaining sides are in the same right line. Democrat, because the triangles ABC, CDE have the angles B and D equal, and the sides about these angles proportional, viz., AB, BC, CD, D, they are equiangular 6, therefore the angle BAC is equal to DCE. To each add ACD, and we have the sum of the angles BAC, ACD equal to the sum of DCE and ACD, but the sum of BAC, ACD is IXXIX, two right angles, therefore the sum of DCE and ACD is two right angles. Hence I14. AC, CE are in the same right line. Prop. XXXIII, theorem. In equal circles, angles, BAC, EPF, at the centers or, BAC, EDF, at the circumference have the same ratio to one another as the arcs, BC, F, on which they stand, and so also have the sectors, BAC, EPF. Democrat 1. Take any number of arcs CG, GH in the first circle, each equal to BC. Join OG, O, and in the second circle take any number of arcs phi, IJ, each equal to F. Join IP, JP. Then because the arcs BC, CG, GH are all equal, the angles BAC, COG, GO, are all equal 3xxVII. Therefore the arc BH and the angle BO are equimultiples of the arc BC and the angle BAC. In like manner it may be proved that the arc EJ and the angle EPJ are equimultiples of the arc F and the angle EPF. Again, since the circles are equal, it is evident that the angle BO is greater than, equal to, or less than the angle EPJ, according as the arc BH is greater than, equal to, or less than the arc EJ. Now we have four magnitudes, namely, the arc BC, the arc F, the angle BAC, and the angle EPF, and we have taken equimultiples of the first and third, namely, the arc BH, the angle BO, and other equimultiples of the second and fourth, namely, the arc EJ and the angle EPJ, and we have proved that, according as the multiple of the first is greater than, equal to, or less than the multiple of the second, the multiple of the third is greater than, equal to, or less than the multiple of the fourth. Hence VDEFV. BC, F, the angle BAC, EPF. Again, since the angle BAC is half the angle BAC 3xx, and EDF is half the angle EPF, BAC, EDF, BAC, EPF V15, but BAC, EPF, BC, F. Hence BAC, EDF, BC, FV11. To the sector BAC, sector EPF, BC, F. Democrat, the same construction being made, since the arc BC is equal to CG, the angle BOC is equal to COG. Hence the sectors BOC, COG are congruent, see observation, proposition XXIX, Book 3, therefore they are equal. In like manner the sectors COG, GO are equal. Hence there are as many equal sectors as there are equal arcs, therefore the arc BH and the sector BO are equimultiples of the arc BC and the sector BOC. In the same manner it may be proved that the arc EJ and the sector EPJ are equimultiples of the arc F and the sector EPF, and it is evident, by superposition, that if the arc BH is greater than, equal to, or less than the arc EJ, the sector BO is greater than, equal to, or less than the sector EPJ. Hence VDEFV the arc BC, F, sector BOC, sector EPF. The second part may be proved as follows: sector BOC equals rectangle contained by the arc BC, and the radius of the circle ABC XX. EX14 and sector EPF equals rectangle contained by the arc F and the radius of the circle EDF, and since the circles are equal, their radii are equal. Hence, sector BOC, sector EPF, arc BC, arc F. Questions for examination on Book 6. 1. What is the subject matter of Book 6? ANS application of the theory of proportion. 2. What are similar rectilineal figures? 3. What do similar figures agree in? 4. How many conditions are necessary to define similar triangles? 5. How many to define similar rectilineal figures of more than 3 sides? 6. When is a figure said to be given in species? 7. When in magnitude? 8. When in position? 9. What is a mean proportional between two lines? 10. Define two mean proportionals. 11. What is the altitude of a rectilineal figure? 12. If two triangles have equal altitudes, how do their areas vary? 13. How do these areas vary if they have equal bases but unequal altitudes? 14. If both bases and altitudes differ, how do the areas vary? 15. When are two lines divided proportionally? 16. If in two lines divided proportionally a pair of homologous points coincide with their point of intersection, what property holds for the lines joining the other pairs of homologous points? 17. Define reciprocal proportion. 18. If two triangles have equal areas, prove that their perpendiculars are reciprocally proportional to the bases. 19. What is meant by figures inversely similar? 20. If two figures be inversely similar, how can they be changed into figures directly similar? 21. Give an example of two triangles inversely similar. ANS. If two lines passing through any point O outside a circle intersected in pairs of points A, B, B, respectively, the triangles OAB, OAB, are inversely similar. 22. What point is it round which a figure can be turned so as to bring its sides into positions of parallelism with the sides of a similar rectilineal figure? ANS. The center of similitude of the two figures. 23. How many figures similar to a given rectilineal figure of sides can be described on a given line? 24. How many centers of similitude can two regular polygons of n sides each have? ANS n centers, which lie on a circle. 25. What are homothetic figures? 26. How do the areas of similar rectilineal figures vary? 27. What proposition is 19? A special case of? 28. Define Philo's line. 29. How many centers of similitude have two circles? Exercises on Book 6. 1. If in a fixed triangle we draw a variable parallel to the base, the locus of the points of intersection of the diagonals of the trapezium thus cut off from the triangle is the median that bisects the base. 2. Find the locus of the point which divides in a given ratio the several lines drawn from a given point to the circumference of a given circle. 3. Two lines of x, y, are given in position, AB is divided in C in the ratio m, n, and parallels A, BB, CC, are drawn in any direction meeting XY in the points A, B, C, prove 4. 3 concurrent lines from the vertices of a triangle ABC meet the opposite sides in A, B, C, prove 5. If a transversal meet the sides of a triangle ABC in the points A, B, C, prove 6. If on a variable line AC, drawn from a fixed point A to any point B in the circumference of a given circle, a point C be taken such that the rectangle AB.AC is constant, the locus of C is a circle. 7. If D be the middle point of the base BC of a triangle ABC, E the foot of the perpendicular, L the point where the bisector of the angle A meets BC, H the point of contact of the inscribed circle with BC, proved A.HL equals He.HD. 8. In the same case, if K be the point of contact with BC of the inscribed circle, which touches the other sides produced, LH.BK equals BD.LE. 9. If R be the radii of the circumscribed, the inscribed, and the inscribed circles of a plane triangle, D the distances of the center of the circumscribed circle from the centers of the others, then R2 equals D2 plus 2RR equals D2 2RR, and C10. In the same case, 12 R2 equals D2 plus D2 plus D2 plus D2. 11. If P denote the perpendiculars of a triangle, then 1 plus equals 2 plus equals, and C 3 equals, and C 4 equals plus, and C 12. In a given triangle inscribe another of given form, and having one of its angles at a given point in one of the sides of the original triangle. 13. If a triangle of given form moves so that its 3 sides pass through 3 fixed points, the locus of any point in its plane is a circle. 14. The angle A and the area of a triangle ABC are given in magnitude, if the point A be fixed in position, and the point B move along a fixed line or circle, the locus of the point C is a circle. 15. One of the vertices of a triangle of given form remains fixed, the locus of another is a right line or circle, find the locus of the third. 16. Find the area of a triangle, 1, in terms of its medians, 2, in terms of its perpendiculars. 17. If 2 circles touch externally, their common tangent is a mean proportional between their diameters. 18. If there be given 3 parallel lines, and 2 fixed points A, B, then if the lines of connection of A and B to any variable point in one of the parallels intersect the other parallels in the points C and D, E, and F, respectively, CF and A pass each through a fixed point. 19. If a system of circles pass through 2 fixed points, any 2 secants passing through one of the points are cut proportionally by the circles. 20. Find a point O in the plane of a triangle ABC, such that the diameters of the 3 circles, about the triangles OAB, OBC, OCA, may be in the ratios of 3 given lines. 21. ABCD is a cyclic quadrilateral, the lines of AD and the point C, are given in position, find the locus of the point which divides BD in a given ratio. 22. CA, CB are 2 tangents to a circle, B is perpendicular to AD, the diameter through A, prove that CD bisects B. 23. If 3 lines from the vertices of a triangle ABC to any interior point O meet the opposite sides in the points A, B, C, prove 24. If 3 concurrent lines OA, OB, OC be cut by 2 transversals in the 2 systems of points A, B, C, A, B, C, respectively, prove 25. The line joining the middle points of the diagonals of a quadrilateral circumscribed to a circle divides each pair of opposite sides into inversely proportional segments, is divided by each pair of opposite lines into segments which, measured from the center, are proportional to the sides, is divided by both pairs of opposite sides into segments which, measured from either diagonal, have the same ratio to each other. 26 If CD be the internal and external bisectors of the angle C of the triangle ACB, the three rectangles AD.DB, AC.CB, AD.BD are proportional to the squares of AD, AC, AD, and R. 1. In arithmetical progression if the difference of the base angles be equal to a right angle. 2. In geometrical progression if one base angle be right. 3. In harmonical progression if the sum of the base angles be equal to a right angle. 27 If a variable circle touch two fixed circles, the chord of contact passes through a fixed point on the line connecting the centers of the fixed circles. Democrat let O be the centers of the two fixed circles, O the center of the variable circle, A, be the points of contact. Let AB and OO meet in C, and cut the fixed circles again in the points A, B respectively. Join AO, BO. Then AO, BO meet in O311. Now, because the triangles OAA, OAB are isosceles, the angle OBA equals OAB equals OAA. Hence OA is parallel to OB, therefore OC, OA, OB, that is, in a given ratio. Hence C is a given point. 28 If DD be the common tangent to the two circles, DD2 equals AB. 29 If R denote the radius of O and ρ, the radii of O, DD2, AB2, R plus or minus ρ, R plus or minus ρ, R2, the choice of sign depending on the nature of the contacts. This follows from 28. 30 If four circles be tangential to a fifth, and if we denote by 12 the common tangent to the first and second, and C, then 31. The inscribed and escribed circles of any triangle are all touched by its 9-point circle. 32 The four triangles which are determined by 4 points, taken 3 by 3, are such that their 9-point circles have one common point. 33 If A, B, C, D denote the four sides, and D the diagonals of a quadrilateral, prove that the sides of the triangle, formed by joining the feet of the perpendiculars from any of its angular points on the sides of the triangle formed by the three remaining points, are proportional to the three rectangles AC, BD, DD. 34 Prove the converse of Ptolemy's theorem, C17, EX13. 35 Describe a circle which shall, 1. Pass through a given point, and touch two given circles, 2. Touch three given circles. 36 If a variable circle touch two fixed circles, the tangent to it from their center of similitude, through which the chord of contact passes, 27, is of constant length. 37 If the lines AD, BD, see figure, EX27, be produced, they meet in a point on the circumference of O, and the line OP is perpendicular to DD. 38 If A, B be two fixed points on two lines given in position, and A, B two variable points, such that the ratio A, BB is constant, the locus of the point dividing AB in a given ratio is a right line. 39 If a line F divide proportionally two opposite sides of a quadrilateral, and a line GH the other sides, each of these is divided by the other in the same ratio as the sides which determine them. 40 In a given circle inscribe a triangle, such that the triangle whose angular points are the feet of the perpendiculars from the extremities of the base on the bisector of the vertical angle, and the foot of the perpendicular from the vertical angle on the base, may be a maximum. 41 In a circle, the point of intersection of the diagonals of any inscribed quadrilateral coincides with the point of intersection of the diagonals of the circumscribed quadrilateral, whose sides touch the circle at the angular points of the inscribed quadrilateral. 42 through 2 given points describe a circle whose common chord with another given circle may be parallel to a given line, or pass through a given point. 43 being given the center of a circle, describe it so as to cut the legs of a given angle along a chord parallel to a given line. 44 if concurrent lines drawn from the angles of a polygon of an odd number of sides divide the opposite sides each into two segments, the product of one set of alternate segments is equal to the product of the other set. 45 if a triangle be described about a circle, the lines from the points of contact of its sides with the circle to the opposite angular points are concurrent. 46 if a triangle be inscribed in a circle, the tangents to the circle at its three angular points meet the three opposite sides at three collinear points. 47 the external bisectors of the angles of a triangle meet the opposite sides in three collinear points. 48 describe a circle touching a given line at a given point, and cutting a given circle at a given angle. DEF the center of mean position of any number of points A, B, C, D, and C, is a point which may be found as follows: bisect the line joining any 2 points A, B, in G, join G to a third point C, divide GC in H, so that GH equals GC. Join H to a fourth point D, and divide HD in K, so that HK equals HD, and so on. The last point found will be the center of mean position of the given points. 49 the center of mean position of the angular points of a regular polygon is the center of figure of the polygon. 50 the sum of the perpendiculars let fall from any system of points A, B, C, D, and C, whose number is n on any line L, is equal to n times the perpendicular from the center of mean position on L. 51. The sum of the squares of lines drawn from any system of points A, B, C, D, and C, to any point P, exceeds the sum of the squares of lines from the same points to their center of mean position, O, by NOP2. 52 if a point be taken within a triangle, so as to be the center of mean position of the feet of the perpendiculars drawn from it to the sides of the triangle, the sum of the squares of the perpendiculars is a minimum. 53 construct a quadrilateral, being given two opposite angles, the diagonals and the angle between the diagonals. 54 a circle rolls inside another of double its diameter, find the locus of a fixed point in its circumference. 55 2 points, C, D, in the circumference of a given circle are on the same side of a given diameter, find a point P in the circumference at the other side of the given diameter, AB, such that PC, PD may cut AB at equal distances from the center. 56. If the sides of any polygon be cut by a transversal, the product of one set of alternate segments is equal to the product of the remaining set. 57 a transversal being drawn cutting the sides of a triangle, the lines from the angles of the triangle to the middle points of the segments of the transversal intercepted by those angles meet the opposite sides in collinear points. 58 if lines be drawn from any point P to the angles of a triangle, the perpendiculars at P to these lines meet the opposite sides of the triangle in three collinear points. 59 divide a given semicircle into two parts by a perpendicular to the diameter, so that the radii of the circles inscribed in them may have a given ratio. 60 from a point within a triangle perpendiculars are let fall on the sides, find the locus of the point, when the sum of the squares of the lines joining the feet of the perpendiculars is given. 61 if a circle make given intercepts on two fixed lines, the rectangle contained by the perpendiculars from its center on the bisectors of the angle formed by the lines is given. 62 if the base and the difference of the base angles of a triangle be given, the rectangle contained by the perpendiculars from the vertex on two lines through the middle point of the base, parallel to the internal and external bisectors of the vertical angle, is constant. 63 the rectangle contained by the perpendiculars from the extremities of the base of a triangle, on the internal bisector of the vertical angle, is equal to the rectangle contained by the external bisector and the perpendicular from the middle of the base on the internal bisector. 64 State and prove the corresponding theorem for perpendiculars on the external bisector. 65 If R denote the radii of the circles inscribed in the triangles into which a right-angled triangle is divided by the perpendicular from the right angle on the hypotenuse, then, if C be the hypotenuse, and S the semiperimeter, R2 plus R2 equals, SC, 2. 66 If A, B, C, D be four collinear points, find a point O in the same line with them such that OA.OD equals OB.OC. 67 The four sides of a cyclic quadrilateral are given, construct it. 68 Being given two circles, find the locus of a point such that tangents from it to the circles may have a given ratio. 69 If 4 points A, B, C, D be collinear, find the locus of the point P at which AB and CD subtend equal angles. 70 If a circle touch internally two sides, CA, CB, of a triangle and its circumscribed circle, the distance from C to the point of contact on either side is a fourth proportional to the semiperimeter, and CA, CB. 71 State and prove the corresponding theorem for a circle touching the circumscribed circle externally and two sides produced. 72 Pascal's theorem If the opposite sides of an irregular hexagon of def inscribed in a circle be produced till they meet, the 3 points of intersection G, H, I are collinear. Democrat join AD. Describe a circle about the triangle ADI, cutting the lines AF, CD produced, if necessary, in K and L join IC, KL, Li. Now, the angles KLG, FCG are each 3xxi equal to the angle GAD. Hence they are equal. Therefore KL is parallel to CF. Similarly, Li is parallel to CH, and Ki to FH, hence the triangles KLI, FCH are homothetic. Hence the lines joining corresponding vertices are concurrent. Therefore the points I, H, G are collinear. 73 If two sides of a triangle circumscribed to a given circle be given in position, but the third side variable, the circle described about the triangle touches a fixed circle. 74 If two sides of a triangle be given in position, and if the area be given in magnitude, 2 points can be found, at each of which the base subtends a constant angle. 75 If A, B, C, D denote the sides of a cyclic quadrilateral, and S its semiperimeter, prove its area equals. 76 If three concurrent lines from the angles of a triangle ABC meet the opposite side in the points A, B, C, and the points A, B, C be joined, forming a second triangle ABC, 77. In the same case the diameter of the circle circumscribed about the triangle ABC equals AB.BC.CA divided by the area of ABC. 78 If a quadrilateral be inscribed in one circle, and circumscribed to another, the square of its area is equal to the product of its four sides. 79 If on the sides of AC of a triangle ABC we take 2 points D, E, and on their line of connection F, such that prove the triangle BFC equals to ID. 80 If through the middle points of each of the two diagonals of a quadrilateral we draw a parallel to the other, the lines drawn from their points of intersection to the middle points of the sides divide the quadrilateral into 4 equal parts. 81 CE, DF are perpendiculars to the diameter of a semicircle, and two circles are described touching CE, D, and the semicircle, one internally and the other externally. The rectangle contained by the perpendiculars from their centers on AB is equal to CE.df. 82 If lines be drawn from any point in the circumference of a circle to the angular points of any inscribed regular polygon of an odd number of sides, the sums of the alternate lines are equal. 83 If at the extremities of a chord drawn through a given point within a given circle tangents be drawn, the sum of the reciprocals of the perpendiculars from the point upon the tangents is constant. 84 If a cyclic quadrilateral be such that three of its sides pass through three fixed collinear points, the fourth side passes through a fourth fixed point, collinear with the three given ones. 85 If all the sides of a polygon be parallel to given lines, and if the loci of all the angles but one be right lines, the locus of the remaining angle is also a right line. 86 If the vertical angle and the bisector of the vertical angle be given, the sum of the reciprocals of the containing sides is constant. 87 If P denote the areas of two regular polygons of any common number of sides, inscribed and circumscribed to a circle, and pi the areas of the corresponding polygons of double the number of sides, prove pi is a geometric mean between P, and pi a harmonic mean between pi and P. 88 The difference of the areas of the triangles formed by joining the centers of the circles described about the equilateral triangles constructed, 1. Outwards, 2. Inwards on the sides of any triangle, is equal to the area of that triangle. 89 In the same case, the sum of the squares of the sides of the two new triangles is equal to the sum of the squares of the sides of the original triangle. 90 If R denote the radii of the circumscribed and inscribed circles to a regular polygon of any number of sides, R, corresponding radii to a regular polygon of the same area, and double the number of sides, prove 91. If the altitude of a triangle be equal to its base, the sum of the distances of the orthocenter from the base and from the middle point of the base is equal to half the base. 92 In any triangle, the radius of the circumscribed circle is to the radius of the circle which is the locus of the vertex, when the base and the ratio of the sides are given, as the difference of the squares of the sides is to 4 times the area. 93 Given the area of a parallelogram, one of its angles, and the difference between its diagonals, construct the parallelogram. 94 If a variable circle touch two equal circles, one internally and the other externally, and perpendiculars be let fall from its center on the transverse tangents to these circles, the rectangle of the intercepts between the feet of these perpendiculars and the intersection of the tangents is constant. 95 Given the base of a triangle, the vertical angle, and the point in the base whose distance from the vertex is equal half the sum of the sides, construct the triangle. 96 If the middle point of the base BC of an isosceles triangle ABC be the center of a circle touching the equal sides, prove that any variable tangent to the circle will cut the sides in points D, E, such that the rectangle BD.CE will be constant. 97 Inscribe in a given circle a trapezium, the sum of whose opposite parallel sides is given, and whose area is given. 98 Inscribe in a given circle a polygon all whose sides pass through given points. 99 If two circles X, Y be so related that a triangle may be inscribed in X and circumscribed about Y, an infinite number of such triangles can be constructed. 100 In the same case, the circle inscribed in the triangle formed by joining the points of contact on Y touches a given circle. 101 And the circle described about the triangle formed by drawing tangents to X, at the angular points of the inscribed triangle, touches a given circle. 102 Find a point, the sum of whose distances from three given points may be a minimum. 103 A line drawn through the intersection of two tangents to a circle is divided harmonically by the circle and the chord of contact. 104 To construct a quadrilateral similar to a given one whose four sides shall pass through four given points. 105 To construct a quadrilateral, similar to a given one, whose four vertices shall lie on four given lines. 106 Given the base of a triangle, the difference of the base angles, and the rectangle of the sides, construct the triangle.
107 ABCD is a square, the side CD is bisected in E, and the line F drawn, making the angle AEF equals EAB, prove that F divides the side BC in the ratio of 2, 1. 108 If any chord be drawn through a fixed point on a diameter of a circle, and its extremities join to either end of the diameter, the joining lines cut off, on the tangent at the other end, portions whose rectangle is constant. 109 If two circles touch, and through their point of contact two secants be drawn at right angles to each other, cutting the circles respectively in the points A, B, B, then A2 plus BB2 is constant. 110 If two secants at right angles to each other, passing through one of the points of intersection of two circles, cut the circles again, and the line through their centers in the two systems of points A, B, C, A, B, C respectively, then AB, BC, AB, BC. 111 Two circles described to touch an ordinate of a semicircle, the semicircle itself, and the semicircles on the segments of the diameter, are equal to one another. 112 If a chord of a given circle subtend a right angle at a given point, the locus of the intersection of the tangents at its extremities is a circle. 113 The rectangle contained by the segments of the base of a triangle, made by the point of contact of the inscribed circle, is equal to the rectangle contained by the perpendiculars from the extremities of the base on the bisector of the vertical angle. 114 If O be the center of the inscribed circle of the triangle, prove 115. State and prove the corresponding theorems for the centers of the ascribed circles. 116 4 points A, B, C, D are collinear, find a point P at which the segments of B, C, CD subtend equal angles. 117 The product of the bisectors of the three angles of a triangle whose sides are A, B, C, is 118. In the same case the product of the alternate segments of the sides made by the bisectors of the angles is 119. If three of the 6 points in which a circle meets the sides of any triangle be such, that the lines joining them to the opposite vertices are concurrent, the same property is true of the three remaining points. 120 If a triangle ABC be inscribed in another ABC, prove is equal twice the triangle ABC multiplied by the diameter of the circle ABC. 121 Construct a polygon of an odd number of sides, being given that the sides taken in order are divided in given ratios by fixed points. 122 If the external diagonal of a quadrilateral inscribed in a given circle be a chord of another given circle, the locus of its middle point is a circle. 123 If a chord of one circle be a tangent to another, the line connecting the middle point of each arc which it cuts off on the first, to its point of contact with the second, passes through a given point. 124 From a point P in the plane of a given polygon perpendiculars are let fall on its sides, if the area of the polygon formed by joining the feet of the perpendiculars be given, the locus of P is a circle. Book 11. Theory of planes, coplanar lines, and solid angles _____________ definitions. When two or more lines are in one plane they are said to be coplanar. 2. The angle which one plane makes with another is called a dihedral angle. 3. A solid angle is that which is made by more than two plane angles, in different planes, meeting in a point. 4. The point is called the vertex of the solid angle. V. If a solid angle be composed of three plane angles it is called a trihedral angle, if of 4, a tetrahedral angle, and if of more than 4, a polyhedral angle. Prop. I theorem. One part, ab, of a right line cannot be in a plane, x, and another part, bc, not in it. Democrat since ab is in the plane x, it can be produced in it bki post 2,
let it be produced to D. Then, if BC be not in X, let any other plane passing through AD be turned round AD until it passes through the point C. Now, because the points B, C are in this second plane, the line BCI, DEF6 is in it. Therefore the two right lines ABC, ABD lying in one plane have a common segment of, which is impossible. Therefore, and C prop. 2 theorem. Two right lines, AB, CD, which intersect one another in any point, E, are coplanar, and so also are any three right lines, EC, CB, B, which form a triangle. Democrat let any plane pass through EB, and be turned round it until it passes through C. Then because the points E, C are in this plane, the right line EC is in it I, DEF6. For the same reason the line BC is in it. Therefore the lines EC, CB, B are coplanar, but AB and CD are two of these lines. Hence AB and CD are coplanar. Prop. 3 theorem. If two planes, AB, BC, cut one another, their common section, BD, is a right line. Democrat if not from B to D, draw in the plane of the right line bed, and in the plane BC the right line BFD. Then the right line's bed, BFD enclose a space, which I, axiom X is impossible. Therefore the common section BD of the two planes must be a right line. Prop. 4 theorem. If a right line, F, be perpendicular to each of two intersecting lines, AB, CD, it will be perpendicular to any line GH, which is both coplanar and concurrent with them. Democrat through any point G in GH draw a line BC intersecting AB, CD, and so as to be bisected in G, and join any point F in F to B, G, C. Then, because F is perpendicular to the lines EB, EC, we have BF2 equals B2 plus F2, and CF2 equals CE2 plus F2, BF2 plus CF2 equals B2 plus CE2 plus 2F2. Again BF2 plus CF2 equals 2BG2 plus 2GF2 2XEX2, and B2 plus CE2 equals 2BG2 plus 2GE2, 2BG2 plus 2GF2 equals 2BG2 plus 2GE2 plus 2F2, GF2 equals GE2 plus F2. Hence the angle GEF is right, and F is perpendicular to EG. DEF6 a line such as F, which is perpendicular to a system of concurrent and coplanar lines, is said to be perpendicular to the plane of these lines, and is called a normal to it. COR1 the normal is the least line that may be drawn from a given point to a given plane, and of all others that may be drawn to it, the lines of any system making equal angles with the normal are equal to each other. COR2 a perpendicular to each of two intersecting lines is normal to their plane. Prop. V theorem. If three concurrent lines, BC, BD, B, have a common perpendicular, AB, they are coplanar. Democrat for if possible let BC be not coplanar with BD, B, and let the plane of AB, BC intersect the plane of BD, B in the line BF. Then 11.3. BF is a right line, and, since it is coplanar with BD, B, which are each perpendicular to AB, it is 11.4 perpendicular to AB. Therefore the angle ABF is right, and the angle ABC is right, hip. Hence ABC is equal to ABF, which is impossible I, axiom 9. Therefore the lines BC, BD, B are coplanar. Prop. 6 theorem. If two right lines, AB, CD, be normals to the same plane, X, they shall be parallel to one another. Democrat let AB, CD meet the plane X at the points B, D join BD, and in the plane X draw it at right angles to BD, take any point E into. Join B, AE, AD. Then because AB is normal to X, the angle AB is right. Therefore AE2 equals AB2 plus B2 equals AB2 plus BD2 plus D2, because the angle BDE is right. But AB2 plus BD2 equals AD2, because the angle ABD is right. Hence AE2 equals AD2 plus D2. Therefore the angle 8 is right. I/8. And since CD is normal to the plane X, D is perpendicular to CD. Hence D is a common perpendicular to the three concurrent lines CD, AD, BD. Therefore these lines are coplanar 11V. But AB is coplanar with AD, BD 11 too. Therefore the lines AD, BD, CD are coplanar, and since the angles ABD, BDC are right, the line AB is parallel to CDIXXVIII. DEF7 If from every point in a given line normals be drawn to a given plane, the locus of their feet is called the projection of the given line on the plane. Exercises. 1. The projection of any line on a plane is a right line. 2. The projection on either of two intersecting planes of a normal to the other plane is perpendicular to the line of intersection of the planes. Prop. 7. Theorem. Two parallel lines, AB, CD, and any line, F, intersecting them are coplanar. Democrat if possible let the intersecting line be out of the plane, as e.g. F. And in the plane, of the parallels draw I post to the right line EHF. Then we have two right lines e.g. F, EHF, enclosing a space, which I axiom X is impossible. Hence the two parallel right lines and the transversal are coplanar. Or thus, since the points E, F are in the plane of the parallels, the line joining these points is in that plane IDEF6. Prop. 8 Theorem. If one, AB, of two parallel right lines, AB, CD, be normal to a plane, X, the other line, CD, shall be normal to the same plane. Democrat let AB, CD meet the plane X in the points B, D join BD. Then the lines AB, BD, CD are coplanar. Now in the plane X, to which AB is normal, draw D at right angles to BD. Take any point E in D, and join B, AE, AD. Then because AB is normal to the plane X, it is perpendicular to the line B in that plane 11. DEF6. Hence the angle AB is right, therefore AE2 equals AB2 plus B2 equals AB2 plus BD2 plus D2, because BDE is right, constant, equals AD2 plus D2, because ABD is right, hip. Therefore the angle 8 is right. Hence D is at right angles both to AD and BD. Therefore 11.4. D is perpendicular to CD, which is coplanar and concurrent with AD and BD. Again, since AB and CD are parallel, the sum of the angles ABD, BDC is two right angles IXXIX, but ABD is right, hip, therefore BDC is right. Hence CD is perpendicular to the two lines DB, D, and therefore 11.4 it is normal to their plane, that is, it is normal to X prop. 9 Theorem. Two right lines, AB, CD, which are each parallel to a third line, F, are parallel to one another. Democrat if the three lines be coplanar, the proposition is evidently the same as IXXX. If they are not coplanar, from any point G in F draw in the planes of F, AB, F, CD, respectively, the lines GH, GK each perpendicular to FI11. Then because F is perpendicular to each of the lines GH, GK, it is normal to their plane 11.4. And because AB is parallel to F, hip, and F is normal to the plane GHK, AB is normal to the plane GHK 11.8. In like manner CD is normal to the plane HGK. Hence, since AB and CD are normals to the same plane, they are parallel to one another. Prop. X theorem. If two intersecting right lines, AB, BC, be respectively parallel to two other intersecting right lines, D, F, the angle, ABC, between the former is equal to the angle, def, between the latter. Democrat. If both pairs of lines be coplanar, the proposition is the same as IXXIX, EX2. If not, take any points A, C in the lines of BC and cut off ED equals BA, and F equals BCI3. Join AD, B, CF, AC, DF. Then because AB is equal and parallel to DA, AD is equal and parallel to BIXXXIII. In like manner CF is equal and parallel to B. Hence 11.9. AD is equal and parallel to CF. Hence IXXXIII. AC is equal to DF. Therefore the triangles ABC, DEF, have the three sides of one respectively equal to the three sides of the other. Hence I8 the angle ABC is equal to DEF. DEF8 two planes which meet are perpendicular to each other, when the right lines drawn in one of them perpendicular to their common section are normals to the other. DEF9 when two planes which meet are not perpendicular to each other, their inclination is the acute angle contained by two right lines drawn from any point of their common section at right angles to it, one in one plane, and the other in the other. Observation. These definitions tacitly assume the result of props 3 and X of this book. On this account we have departed from the usual custom of placing them at the beginning of the book. We have altered the place of definition 6. For a similar reason. Prop. 11 Problem. To draw a normal to a given plane, BH, from a given point, A, not in it. Solution. In the given plane BH draw any line BC, and from a draw AD perpendicular to BC I12, then if AD be perpendicular to the plane, the thing required is done. If not, from D draw to in the plane BH at right angles to BC I11, and from a draw AF I12 perpendicular to D. AF is normal to the plane BH. Democrat. Draw GH parallel to BC. Then because BC is perpendicular both to ED and DA, it is normal to the plane of ED, DA 11.4, and since GH is parallel to BC, it is normal to the same plane 11.8. Hence AF is perpendicular to GH 11. DEF 6, and AF is perpendicular to DA, constant. Therefore AF is normal to the plane of GH and ED, that is, to the plane BH. Prop. 12 Problem. To draw a normal to a given plane from a given point, A, in the plane. Solution. From any point B not in the plane draw 11.11. BC normal to it. If this line pass through A, it is the normal required. If not, from a draw AD parallel to BC IXXXI. Then because AD and BC are parallel, and BC is normal to the plane, AD is also normal to it 11.8, and it is drawn from the given point. Hence it is the required normal. Prop. 13 Theorem. From the same point, A, there can be but one normal drawn to a given plane, X. Democrat 1. Let A be in the given plane, and if possible let AB, AC be both normals to it, on the same side. Now let the plane of BA, AC cut the given plane X in the line DA. Then because BA is a normal, the angle BA is right. In like manner CAE is right. Hence BA equals CAE, which is impossible. 2. If the point be above the plane, there can be but one normal, for, if there could be two, they would be parallel 11.6 to one another, which is absurd. Therefore from the same point there can be drawn but one normal to a given plane. Prop. 14 Theorem. planes, CD, F, which have a common normal, AB, are parallel to each other. Democrat if the planes be not parallel, they will meet when produced. Let them meet, their common section being the line GH, in which take any point K join AK, BK. Then because AB is normal to the plane CD, it is perpendicular to the line AK, which it meets in that plane 11. DEF 6. Therefore the angle BOC is right. In like manner the angle ABK is right. Hence the plane triangle ABK has two right angles, which is impossible. Therefore the planes CD, F cannot meet, that is, they are parallel. Exercises. 1. The angle between two planes is equal to the angle between two intersecting normals to these planes. 2. If a line be parallel to each of two planes, the sections which any plane passing through it makes with them are parallel. 3. If a line be parallel to each of two intersecting planes, it is parallel to their intersection. 4. If two right lines be parallel, they are parallel to the common section of any two planes passing through them. 5. If the intersections of several planes be parallel, the normals drawn to them from any point are coplanar. Prop. 15 Theorem. Two planes, AC, DF, are parallel, if two intersecting lines, AB, BC, on one of them be respectively parallel to two intersecting lines, D, F, on the other. Democrat from B draw BG perpendicular to the plane DF 1111, and let it meet that plane in G. Through G draw GH parallel to ED, and GK to F. Now, since GH is parallel to ED, constant, and AB to ED, HIP, AB is parallel to GH 11:9. Hence the sum of the angles ABG, BGH is two right angles IXXIX, but BGH is right, constant, therefore ABG is right. In like manner CBG is right. Hence BG is normal to the plane AC 11. DEF 6, and it is normal to DF, constant. Hence the planes AC, DF have a common normal BG, therefore they are parallel to one another. Prop. 16 Theorem. If two parallel planes, AB, CD, be cut by a third plane, F, HG, their common sections, F, GH, with it are parallel. Democrat if the lines F, GH are not parallel, they must meet at some finite distance. Let them meet in K. Now since K is a point in the line F, and F is in the plane AB, K is in the plane AB. In like manner K is a point in the plane CD. Hence the planes AB, CD meet in K, which is impossible, since they are parallel. Therefore the lines F, GH must be parallel. Exercises. 1. Parallel planes intercept equal segments on parallel lines. 2. Parallel lines intersecting the same plane make equal angles with it. 3. A right line intersecting parallel planes makes equal angles with them. Prop. 17 Theorem. If two parallel lines, AB, CD, be cut by three parallel planes, GH, KL, MN, in two triads of points, A, E, B, C, F, D, their segments between those points are proportional. Democrat join AC, BD, AD. Let AD meet the plane KL in X join X, XF. Then because the parallel planes KL, MN are cut by the plane ABD in the lines X, BD, these lines are parallel 11:16. Hence in like manner, therefore V11. Prop. 18 Theorem. If a right line, AB, be normal to a plane, CI, any plane, D, passing through it shall be perpendicular to that plane. Democrat let CE be the common section of the planes D, CI. From any point F in CE draw FG in the plane to parallel to A by XXXI. Then because AB and FG are parallel, but AB is normal, to the plane CI, hence FG is normal to it 11/8. Now since FG is parallel to AB, the angles ABF, BFG are equal to two right angles IXXIX, but ABF is right, hip, therefore BFG is right, that is, FG is perpendicular to CE. Hence every line in the plane DE, drawn perpendicular to the common section of the planes DE, CI, is normal to the plane CI. Therefore 11. DEF8 the planes DE, CI are perpendicular to each other. Prop. 19 Theorem. If two intersecting planes, AB, BC, be each perpendicular to a third plane, ADC, their common section, BD, shall be normal to that plane. Democrat if not, draw from D in the plane of the line DE perpendicular to AD, the common section of the planes AB, ADC, and in the plane BC draw BF perpendicular to the common section DC of the planes BC, ADC. Then because the plane AB is perpendicular to ADC, the line DE in AB is normal to the plane ADC 11. DEF8. In like manner DF is normal to it. Therefore from the point D there are two distinct normals to the plane ADC, which 11/13 is impossible. Hence BD must be normal to the plane ADC. Exercises. 1. If three planes have a common line of intersection, the normals drawn to these planes from any point of that line are coplanar. 2. If two intersecting planes be respectively perpendicular to two intersecting lines, the line of intersection of the former is normal to the plane of the latter. 3. In the last case, show that the dihedral angle between the planes is equal to the rectilineal angle between the normals. Prop. XX Theorem. The sum of any two plane angles, BAD, DAC, of a trihedral angle, A, is greater than the third, BAC. Democrat if the third angle BAC be less than or equal to either of the other angles the proposition is evident. If not, suppose it greater, take any point D in AD, and at the point A in the plane BAC make the angle BA equal BAD IXXIII, and cut off AE equal AD. Through E draw BC, cutting AB, AC in the points B, C join DB, DC. Then the triangles BAD, BA have the two sides BA, AD in one equal respectively to the two sides BA, AE in the other, and the angle BAD equal to BA, therefore the third side BD is equal to B. But the sum of the sides BD, DC is greater than BC, hence DC is greater than EC. Again, because the triangles DAC, EAC have the sides DE, AC respectively equal to the sides EA, AC in the other, but the base DC greater than EC, therefore IXXV the angle DAC is greater than EAC, but the angle DAB is equal to BA, constant. Hence the sum of the angles BAD, DAC is greater than the angle BAC. Prop. XXI Theorem. The sum of all the plane angles, BAC, CAD, and C, forming any solid angle, A, is less than 4 right angles. Democrat suppose for simplicity that the solid angle A is contained by 5 plane angles BAC, CAD, DE, EAF, FAB, and let the planes of these angles be cut by another plane in the lines BC, CD, DE, F, FB, then we have 11XX, ABC plus ABF greater than FBC, ACB plus ACD, BCD, and C. Hence, adding, we get the sum of the base angles of the 5 triangles BAC, CAD, and C, greater than the sum of the interior angles of the pentagon DEF, that is, greater than 6 right angles. But the sum of the base angles of the same triangles, together with the sum of the plane angles BAC, CAD, and C, forming the solid angle A, is equal to twice as many right angles as there are triangles BAC, CAD, and C, that is, equal to 10 right angles. Hence the sum of the angles forming the solid angle is less than 4 right angles. Observation: this prop may not hold if the polygonal base def contain reentrant angles. Exercises on Book 11. 1. Any face angle of a trihedral angle is less than the sum, but greater than the difference, of the supplements of the other two face angles. 2. A solid angle cannot be formed of equal plane angles which are equal to the angles of a regular polygon of n sides, except in the case of n equals 3, 4, or 5. 3. Through one of two non-coplanar lines draw a plane parallel to the other. 4. Draw a common perpendicular to two non-coplanar lines, and show that it is the shortest distance between them. 5. If two of the plane angles of a tetrahedral angle be equal, the planes of these angles are equally inclined to the plane of the third angle, and conversely. If two of the planes of a trihedral angle be equally inclined to the third plane, the angles contained in those planes are equal. 6. The three lines of intersection of three planes are either parallel or concurrent. 7. If a trihedral angle O be formed by three right angles, and A, B, C be points along the edges, the orthocenter of the triangle ABC is the foot of the normal from O on the plane ABC. 8. If through the vertex O of a trihedral angle OABC any line OD be drawn interior to the angle, the sum of the rectilineal angles DOA, DOB, DOC is less than the sum, but greater than half the sum, of the face angles of the trihedral. 9. If on the edges of a trihedral angle OABC three equal lines OA, OB, OC be taken, each of these is greater than the radius of the circle described about the triangle ABC. 10. Given the three angles of a trihedral angle, find, by a plane construction, the angles between the containing planes. 11. If any plane P cut the four sides of a gauche quadrilateral, a quadrilateral whose angular points are not coplanar, ABCD in 4 points, A, B, C, D, then the product of the four ratios is plus unity, and conversely, if the product the points A, B, C, D are coplanar. 12. If in the last exercise the intersecting plane be parallel to any two sides of the quadrilateral, it cuts the two remaining sides proportionally. DEFX. If at the vertex O of a trihedral angle OABC we draw normals OA, OB, OC to the faces OBC, OCA, OAB, respectively, in such a manner that OA will be on the same side of the plane OBC as OA, and C, the trihedral angle OABC is called the supplementary of the trihedral angle OABC. 13. If OABC be the supplementary of OABC, prove that OABC is the supplementary of OABC. 14. If two trihedral angles be supplementary, each dihedral angle of one is the supplement of the corresponding face angle of the other. 15. Through a given point draw a right line which will meet two non-coplanar lines. 16. Draw a right line parallel to a given line, which will meet two non-coplanar lines. 17. Being given an angle AOB, the locus of all the points P of space, such that the sum of the projections of the line up on OA and OB may be constant, is a plane. Appendix. Prism, pyramid, cylinder, sphere, and cone underscore 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 definitions. A polyhedron is a solid figure contained by plane figures. If it be contained by four plane figures it is called a tetrahedron, by 6, a hexahedron, by 8, an octahedron, by 12, a dodecahedron, and if by 20, an icosahedron. 2. If the plane faces of a polyhedron be equal and similar rectilineal figures, it is called a regular polyhedron. 3. A pyramid is a polyhedron of which all the faces but one meet in a point. This point is called the vertex, and the opposite face, the base. For a prism is a polyhedron having a pair of parallel faces which are equal and similar rectilineal figures, and are called its ends. The others, called its side faces, are parallelograms. A prism whose ends are perpendicular to its sides is called a right prism, any other is called an oblique prism. 6. The altitude of a pyramid is the length of the perpendicular drawn from its vertex to its base, and the altitude of a prism is the perpendicular distance between its ends. 7. A parallelopiped is a prism whose bases are parallelograms. A parallelopiped is evidently a hexahedron. 8. A cube is a rectangular parallelopiped, all whose sides are squares. 9. A cylinder is a solid figure formed by the revolution of a rectangle about one of its sides, which remains fixed, and which is called its axis. The circles which terminate a cylinder are called its bases or ends. A cone is the solid figure described by the revolution of a right-angled triangle about one of the legs, which remains fixed, and which is called the axis. The other leg describes the base, which is a circle. 11. A sphere is the solid described by the revolution of a semicircle about a diameter, which remains fixed. The center of the sphere is the center of the generating semicircle. Any line passing through the center of a sphere and terminated both ways by the surface is called a diameter. Prop. I theorem. Right prisms, ABCDE, FGH, ABCDE, FGHIJ, which have bases, ABCDE, ABCDE, that are equal and similar, and which have equal altitudes, are equal. Democrat apply the bases to each other, then, since they are equal and similar figures, they will coincide, that is, the point A with A, B with B, and C. And since AF is equal to AF, and each is normal to its respective base, the point F will coincide with F. In the same manner the points G, H, I, J will coincide respectively with the points G, H, I, J. Hence the prisms are equal in every respect. COR1 right prisms which have equal bases, F, EF, and equal altitudes are equal in volume. Democrat, since the bases are equal, but not similar, we can suppose one of them, F, divided into parts A, B, C, and rearranged so as to make them coincide with the other IXXXV. Note, and since the prism on EF can be subdivided in the same manner by planes perpendicular to the base, the proposition is evident. COR2 the volumes of right prisms, X, Y, having equal bases are proportional to their altitudes. 4. If the altitudes be in the ratio of m, n, x can be divided into m prisms of equal altitudes by planes parallel to the base, then these m prisms will be all equal. In like manner, y can be divided into n equal prisms. Hence x, y, m, and COR3 in right prisms of equal altitudes the volumes are to one another as the areas of their bases. This may be proved by dividing the bases into parts so that the subdivisions will be equal, and then the volumes proportional to the number of subdivisions in their respective bases, that is, to their areas. COR4 the volume of a rectangular parallelopiped is measured by the continued product of its three dimensions. Prop. 2 theorem. Parallelopipeds, ABCD, EFGH, ABCD, MNOP, having a common base, ABCD, and equal altitudes, are equal. 1. Let the edges MN, F be in one right line, then GH, OP must be in one right line. Now F equals MN, because each equal OB, therefore ME equals NF, therefore the prisms AEM, DHP, and BFN, CGO, have their triangular bases AEM, BFN identically equal, and they have equal altitudes, hence they are equal, and supposing them taken away from the entire solid, the remaining parallelepipeds ABCD, EFGH, ABCD, MNOP are equal. 2. Let the edges F, M and be in different lines, then produce on PM to meet the lines F and GH produced in the points J, K, L, I. Then by 1 the parallelepipeds ABCD, EFGH, ABCD, MNOP are each equal to the parallelepiped ABCD, IJKL. Hence they are equal to one another. COR the volume of any parallelepiped is equal to the product of its base and altitude. Prop. 3 theorem. A diagonal plane of a parallelepiped divides it into two prisms of equal volume. 1. When the parallelepiped is rectangular, the proposition is evident. 2. When it is any parallelepiped, ABCD, EFGH, the diagonal plane bisects it. Democrat through the vertices A, E let planes be drawn perpendicular to the edges and cutting them in the points I, J, K, L, M, N, respectively. Then I thirsive we have IL equals BF, because each is equal to AE. Hence IB equals LF. In like manner JC equals MG. Hence the pyramid A, IJCB agrees in everything but position with E, LMGF, hence it is equal to it in volume. To each add the solid ABC, LME, and we have the prism AIJ, LM equal to the prism ABC, EFG. In like manner AJK, EMN equals ACD, EGH, but, 1, the prism AIJ, LM equals AJK, EMN. Hence ABC, EFG equals ACD, EGH. Therefore the diagonal plane bisects the parallelepiped. COR1 the volume of a triangular prism is equal to the product of its base and altitude, because it is half of a parallelepiped, which has a double base and equal altitude. COR2 the volume of any prism is equal to the product of its base and altitude, because it can be divided into triangular prisms. Prop. 4 theorem. If a pyramid, O, ABCDE, be cut by any plane, ABCDE, parallel to the base, the section is similar to the base. Democrat because the plane AOB cuts the parallel planes ABCDE, ABCDE, the sections of are parallel 11/16. In like manner BC, BC are parallel. Hence the angle ABC equals ABC 11x. In like manner the remaining angles of the polygon ABCDE are equal to the corresponding angles of ABCDE. Again, because AB is parallel to AB, the triangles ABO, ABO are equiangular. Hence AB, BO, AB, BO. 6-4. In like manner BO, BC, BO, BC, therefore AB, BC, AB, BC. X equally dot. In like manner BC, CD, BC, CD, and C. Therefore the polygons ABCDE, ABCDE are equiangular, and have the sides about their equal angles proportional. Hence they are similar. COR1 the edges and the altitude of the pyramid are similarly divided by the parallel plane. COR2 the areas of parallel sections are in the duplicate ratio of the distances of their planes from the vertex. COR3 in any two pyramids, sections parallel to their bases, which divide their altitudes in the same ratio, are proportional to their bases. Prop. V theorem. Pyramids, P, ABCD, P, ABC, having equal altitudes, PO, and bases, ABCD, ABC, of equal areas, have equal volumes. Democrat if they be not equal in volume, let ABC be the base of the greater, and let OX be the altitude of a prism, with an equal base, and whose volume is equal to their difference, then let the equal altitudes Po be divided into such a number of equal parts, by planes parallel to the bases of the pyramids, that each part shall be less than ox. Then for cor3 the sections made by these planes will be equal each to each. Now let prisms be constructed on these sections as bases and with the equal parts of the altitudes of the pyramids as altitudes, and let the prisms in P, ABCD be constructed below the sections, and in P, ABC, above. Then it is evident that the sum of the prisms in P, ABCD is less than that pyramid, and the sum of those on the sections of P, ABC greater than P, ABC. Therefore the difference between the pyramids is less than the difference between the sums of the prisms, that is, less than the lower prism in the pyramid P, ABC, but the altitude of this prism is less than ox, constant. Hence the difference between the pyramids is less than the prism whose base is equal to one of the equal bases, and whose altitude is equal to ox, and the difference is equal to this prism, hip, which is impossible. Therefore the volumes of the pyramids are equal. Cor1 the volume of a triangular pyramid E, ABC is 1/3 the volume of the prism ABC, def, having the same base and altitude. 4. Draw the plane EAF, then the pyramids E, AFC, E, AFD are equal, having equal bases AFC, AFD and a common altitude, and the pyramids E, ABC, F, ABC are equal, having a common base and equal altitudes. Hence the pyramid E, ABC is one of 3 equal pyramids into which the prism is divided. Therefore it is 1/3 of the prism. Cor2 the volume of every pyramid is 1/3 of the volume of a prism having an equal base and altitude. Because it may be divided into triangular pyramids by planes through the vertex and the diagonals of the base. Prop. 6 theorem. The volume of a cylinder is equal to the product of the area of its base by its altitude. Democrat let O be the center of its circular base, and take the angle AOB indefinitely small, so that the arc of may be regarded as a right line. Then planes perpendicular to the base, and cutting it in the lines OA, OB, will be faces of a triangular prism, whose base will be the triangle AOB, and whose altitude will be the altitude of the cylinder. The volume of this prism will be equal to the area of the triangle AOB by the height of the cylinder. Hence, dividing the circle into elementary triangles, the cylinder will be equal to the sum of all the prisms, and therefore its volume will be equal to the area of the base multiplied by the altitude. Cor1 if r be the radius, and h the height of the cylinder, Cor2 if ABCD be a rectangle, x a line in its plane parallel to the side of O the middle point of the rectangle, the volume of the solid described by the revolution of ABCD round x is equal to the area of ABCD multiplied by the circumference of the circle described by O. Democrat produce the lines AD, BC to meet x in the points E, F. Then when the rectangle revolves round x, the rectangles ABFE, DCFE will describe cylinders whose bases will be circles having AE, D as radii, and whose common altitude will be AB. Hence the difference between the volumes of these cylinders will be equal to the differences between the areas of the bases multiplied by AB, that is equals pi, AE2 to 2, dot AB. Therefore the volume described by ABCD equals pi dot AB, AE plus D, AE D, but AE plus D equals 2 og, and AE D equals AD. Hence volume described by the rectangle ABCD equals 2 pi dot og dot ab dot AD. Equals rectangle ABCD multiplied by the circumference of the circle described by its middle point O. Observation: the COR is a simple case of Guldenius's celebrated theorem. By its assistance we give in the 2 following corollaries original methods of finding the volumes of the cone and sphere, and it may be applied with equal facility to the solution of several other problems which are usually done by the integral calculus. COR3 The volume of a cone is one-third the volume of a cylinder having the same base and altitude. Democrat, let ABCD be a rectangle whose diagonal is AC. The triangle ABC will describe a cone, and the rectangle a cylinder by revolving round a B. Take 2 points E, F infinitely near each other in AC, and form two rectangles, E, EK, by drawing lines parallel to AD, a B. Now if O be the middle points of these rectangles, it is evident that, when the whole figure revolves round a B, the circumference of the circle described by O will ultimately be twice the circumference of the circle described by O, and since the parallelogram EK is equal to EI/N, the solid described by EK, COR1, will be equal to twice the solid described by E. Hence, if AC be divided into an indefinite number of equal parts, and rectangles corresponding to E, EK be inscribed in the triangles ABC, ADC, the sum of the solids described by the rectangles in the triangle ADC is equal to twice the sum of the solids described by the rectangles in the triangle ABC, that is, the difference between the cylinder and cone is equal to twice the cone. Hence the cylinder is equal to 3 times the cone. Or thus, we may regard the cone and the cylinder as limiting cases of a pyramid and prism having the same base and altitude, and since, VCOR2, the volume of a pyramid is one-third of the volume of a prism, having the same base and altitude, the volume of the cone is one-third of the volume of the cylinder. COR4 if R be the radius of the base of a cone, and h its height, COR5 the volume of a sphere is two-thirds of the volume of a circumscribed cylinder. Democrat, let A be the diameter of the semicircle which describes the sphere, ABCD the rectangle which describes the cylinder. Take 2 points E, F indefinitely near each other in the semicircle. Join F, which will be a tangent, and produce it to meet the diameter PQ perpendicular to AB in N. Let R be the center. Join RE, draw EG, FH, NL parallel to AB, and EI, FK parallel to PQ, and produce to meet LN in M and L, and let O be the middle points of the rectangles E, EK. Now the rectangle NG.GR equals PG.GQ, because each is equal to GE2. Hence NG, GP, GQ, GR, or ME, i.e., RP plus RG, RG. Now, denoting the radii of the circles described by the points O by ρ respectively, we have ultimately ρ equals GR and ρ equals RP plus RG. Hence me, i.e., 2 ρ, but me, i.e., rectangle L, rectangle EK, I/N. EK, EK, 2 ρ, 2 pi ρ dot E equals 2 pi ρ dot EK. Hence the solid described by E equal twice the solid described by EK. Therefore we infer, as in the last COR, that the whole volume of the sphere is equal to twice the difference between the cylinder and sphere. Therefore the sphere is two-thirds of the cylinder. COR6 if R be the radius of a sphere, Prop. 7 theorem. The surface of a sphere is equal to the convex surface of the circumscribed cylinder. Democrat, let A be the diameter of the semicircle which describes the sphere. Take 2 points, E, F, indefinitely near each other in the semicircle. Join F, and produce to meet the tangent CD parallel to AB in N. Draw EI, FK parallel to PQ. Produce EI to meet AB in G. Let O be the center. Join OE. Now we have Phi, Ki, N, in 6-2, but N, in, OE, EG, because the triangles ENI and OEG are similar. Hence Phi, Ki, OE, EG, but OE equals IG. Hence F, IC, IG, EG, and IG, EG, circumference of circle described by the point I, circumference of circle described by the point E. Hence the rectangle contained by F, and circumference of circle described by E is equal to the rectangle contained by AC, and circumference of circle described by I, that is, the portion of the spherical surface described by F is equal to the portion of the cylindrical surface described by AC. Hence it is evident, if planes be drawn perpendicular to the diameter of that, the portions of cylindrical and spherical surface between any two of them are equal. Hence the whole spherical surface is equal to the cylindrical surface described by CD. Or thus, conceive the whole surface of the sphere divided into an indefinitely great number of equal parts, then it is evident that each of these may be regarded as the base of a pyramid having the center of the sphere as a common vertex. Therefore the volume of the sphere is equal to the whole area of the surface multiplied by 1/3 of the radius. Hence if S denote the surface, we have S times equals 6, cor 6, therefore S equals 4 pi r2. That is, the area of the surface of a sphere is equal 4 times the area of one of its great circles. Exercises. 1. The convex surface of a cone is equal to half the rectangle contained by the circumference of the base and the slant height. 2. The convex surface of a right cylinder is equal to the rectangle contained by the circumference of the base and the altitude. 3. If P be a point in the base ABC of a triangular pyramid O, ABC, and if parallels to the edges OA, OB, OC, through P, meet the faces in the points A, B, C, the sum of the ratios 4. The volume of the frustum of a cone, made by a plane parallel to the base, is equal to the sum of the three cones whose bases are the two ends of the frustum, and the circle whose diameter is a mean proportional between the end diameters, and whose common altitude is equal to 1/3 of the altitude of the frustum. 5. If a point P be joined to the angular points A, B, C, D of a tetrahedron, and the joining lines, produced if necessary, meet the opposite faces in A, B, C, D, the sum of the ratios 6. The surface of a sphere is equal to the rectangle by its diameter, and the circumference of a great circle. 7. The surface of a sphere is 2/3 of the whole surface of its circumscribed cylinder. 8. If the four diagonals of a quadrangular prism be concurrent, it is a parallelopiped. 9. If the slant height of a right cone be equal to the diameter of its base, its total surface is to the surface of the inscribed sphere as 9, 4. 10. The middle points of two pairs of opposite edges of a triangular pyramid are coplanar, and form a parallelogram. 11. If the four perpendiculars from the vertices on the opposite faces of a pyramid ABCD be concurrent, then 12. Every section of a sphere by a plane is a circle. 13. The locus of the centers of parallel sections is a diameter of the sphere. 14. If any number of lines in space pass through a fixed point, the feet of the perpendiculars on them from another fixed point are homospheric. 15. Extend the property of EX4 to the pyramid. 16. The volume of the ring described by a circle which revolves round a line in its plane is equal to the area of the circle, multiplied by the circumference of the circle described by its center. 17. Any plane bisecting two opposite edges of a tetrahedron bisects its volume. 18. Planes which bisect the dihedral angles of a tetrahedron meet in a point. 19. Planes which bisect perpendicularly the edges of a tetrahedron meet in a point. 20. The volumes of two triangular pyramids, having a common solid angle, are proportional to the rectangles contained by the edges terminating in that angle. 21. A plane bisecting a dihedral angle of a tetrahedron divides the opposite edge into portions proportional to the areas containing that edge. 22. The volume of a sphere, the volume of the circumscribed cube is pi, 623. If h be the height, and ρ the radius of a segment of a sphere, its volume is h2 plus 3 ρ2. 24. If h be the perpendicular distance between two parallel planes, which cut a sphere in sections whose radii are ρ1, Rho 2, the volume of the frustum is H2 plus 3, Rho 1 2 plus Rho 2 2. 25 If delta be the distance of a point P from the center of a sphere whose radius is r, the sum of the squares of the 6 segments at 3 rectangular chords passing through P is equals 6r2 2 delta 2. 26 The volume of a sphere, the volume of an inscribed cube is pi, 227. If O, ABC be a tetrahedron whose angles AOB, BOC, COA are right, the square of the area of the triangle ABC is equal to the sum of the squares of the 3 other triangular faces. 28 In the same case, if P be the perpendicular from O on the face ABC, 29. If H be the height of an aeronaut, and R the radius of the earth, the extent of surface visible equals 30. If the 4 sides of a gauche quadrilateral touch a sphere, the points of contact are concyclic. Notes. Note a modern theory of parallel lines. In every plane there is one special line called the line at infinity. The point where any other line in the plane cuts the line at infinity is called the point at infinity in that line. All other points in the line are called finite points. 2 lines in the plane which meet the line at infinity in the same point are said to have the same direction, and 2 lines which meet it in different points to have different directions. 2 lines which have the same direction cannot meet in any finite point I axiom X, and are parallel. 2 lines which have different directions must intersect in some finite point, since, if produced, they meet the line at infinity in different points. This is a fundamental conception in geometry, it is self-evident, and may be assumed as an axiom. See Observations on the Axioms, Book I. Hence we may infer the following general proposition: any 2 lines in the same plane must meet in some point in that plane, that is, 1, at infinity, when the lines have the same direction, 2, in some finite point, when they have different directions. See Poncelet, Proprieties Projectives, page 52. Underscore 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 Note B. Legendre's and Hamilton's proofs of Euclid, IXXXII. The discovery of the proposition that the sum of the 3 angles of a triangle is equal to 2 right angles is attributed to Pythagoras. Until modern times no proof of it, independent of the theory of parallels, was known. We shall give here 2 demonstrations, each independent of that theory. These are due to 2 of the greatest mathematicians of modern times: one, the founder of the theory of elliptic functions, the other, the discoverer of the calculus of quaternions. Legendre's proof: let ABC be a triangle, of which the side AC is the greatest. Bisect BC in D, join AD. Then AD is less than AC I 19. EX5. Now, construct a new triangle of C, having the side AC equals 2AD, and AB equals AC. Again, bisect BC in D, and form another triangle of C, having AC equals 2AD, and AB equals AC, and C, 1. The sum of the angles of the triangle ABC equals the sum of the angles of ABC I 16. COR1 equals the sum of the angles of ABC equals the sum of the angles of ABC, and C, 2, the angle BAC is less than half BAC, the angle BAC is less than half BAC, and so on. Hence the angle B, N, A, N, will ultimately become infinitely small. 3. The sum of the base angles of any triangle of the series is equal to the angle of the preceding triangle, see Democrat I 16. Hence, if the annexed diagram represent the triangle of n plus 1, c, n plus 1, the sum of the base angles A and C, n plus 1, is equal to the angle B, n, c, n, and when n is indefinitely large, this angle is an infinitesimal, hence the point B, n plus 1, will ultimately be in the line AC, and the angle of n plus 1, C, n plus 1, will become a straight angle IDEFX, that is, it is equal to two right angles, but the sum of the angles of a n plus 1, C, n plus 1, is equal to the sum of the angles ABC. Hence the sum of the three angles of ABC is equal to two right angles. Hamilton's quaternion proof. Let ABC be the triangle. Produce BA to D, and make AD equal to AC. Produce CB to E, and make B equal to BD. Finally, produce AC to F, and make CF equal to CE. Denote the exterior angles thus formed by A, B, C. Now let the leg AC of the angle A be turned round the point A through the angle A, then the point C will coincide with D. Again, let the leg BD of the angle B be turned round the point B through the angle B, until BD coincides with B, then the point D will coincide with E. Lastly, let CE be turned round C, through the angle C, until CE coincides with CF, and the point E with F. Now, it is evident that by these rotations the point C has been brought successively into the positions D, E, F, hence, by a motion of mere translation along the line FC, the line CA can be brought into its former position. Therefore it follows, since rotation is independent of translation, that the amount of the three rotations is equal to one complete revolution round the point A. Therefore A plus B plus C equals 4 right angles, but A plus A plus B plus B plus C equals 6 right angles I13, hence A plus B plus C equals 2 right angles. Observation. The foregoing demonstration is the most elementary that was ever given of this celebrated proposition. I have reduced it to its simplest form, and without making any use of the language of quaternions. The same method of proof will establish the more general proposition, that the sum of the external angles of any convex rectilineal figure is equal to 4 right angles. Mr. Abbott, FTCD, has informed me that this demonstration was first given by Playfair in 1826, so that Hamilton was anticipated. It has been objected to on the ground that, applied verbatim to a spherical triangle, it would lead to the conclusion that the sum of the angles is 2 right angles, which being wrong, proves that the method is not valid. A slight consideration will show that the cases are different. In the proof given in the text there are 3 motions of rotation, in each of which a point describes an arc of a circle, followed by a motion of translation, in which the same point describes a right line, and returns to its original position. On the surface of a sphere we should have, corresponding to these, 3 motions of rotation, in each of which the point would describe an arc of a circle, followed by a motion of rotation about the center of the sphere, in which the point should describe an arc of a great circle to return to its original position. Hence, the proof for a plane triangle cannot be applied to a spherical triangle. Underscore 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 note C to inscribe a regular polygon of 17 sides in a circle. Analysis. Let A be one of the angular points, AO the diameter, A1, A2, A8 the vertices at one side of AO. Produce OA3 to M, and OA2 to P, making A3M equals OA5, and A2P equals OA8. Again, cut off A6N equals OA7, and A1Q equals OA4. Lastly, cut off OR equals ON, and OS equals OC. Then we have 4. EX40, row 1 row 4 equals R, row 3 plus row 5, equals R.OM, row 2 row 8 equals R, row 6 row 7, equals R.ON, but row 1 row 2 row 4 row 8 equals R44. EX34, therefore OM on equals R2, 1. In like manner, OP.OC equals R2, 2. Again, OM on equals, row 3 plus row 5, row 6 row 7, equals row 3 row 6 plus row 5 row 6 row 3 row 7 row 5 row 7 equals R, row 3 row 8, plus R, row 1 row 6, R, row 2 row 7, R, row 2 row 5, 4. EX40 equals R, OM on up plus OC, equals R, MRPS, MRPS equals R. Again, MR.PS equals, OM on, up OC, equals, row 3 plus row 5 row 6 plus row 7, row 2 plus row 8 row 1 plus row 4, and performing the multiplication and substituting, we get hence, the rectangle and the difference of the lines MR and PS being given, each is given, hence MR is given, but MR equals OM on, therefore OM on is given, and we have proved that the rectangle OM on equals R2, therefore OM and on are each given. In like manner, OP and OC are each given. Again, hence, since OC and on are each given, row 6 and row 7 are each given, therefore we can draw these chords, and we have the arc A6 A7 between their extremities given, that is, the 17th part of the circumference of a circle. Hence the problem is solved. The foregoing analysis is due to Ampere, see Catalan, Theorems et Problems de Geometrie Elementaire. We have abridged and simplified Ampere's solution. Underscore 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 note D to find two mean proportionals between two given lines. The problem to find two mean proportionals is one of the most celebrated in geometry on account of the importance which the ancients attached to it. It cannot be solved by the line and circle, but is very easy by conic sections. The following is a mechanical construction by the ruler and compass. Solution: let the extremes of BC be placed at right angles to each other, complete the rectangle ABCD, and describe a circle about it. Produce a DC, and let a graduated ruler be made to revolve round the point B, and so adjusted that B shall be equal to GF, then AF, CE are two mean proportionals between a BC. Democrat: since B is equal to GF, the rectangle BE.GE equals BF.GF. Therefore DE.CE equals DF.AF, hence DF, AF, CE, and by similar triangles, AB, AF, DF, and CE, CB, DF. Hence AB, AF, CE, and AF, CE, CB. Therefore AB, AF, CE, CB are continual proportions. Hence 6. DEF4. AF, CE are two mean proportionals between AB and BC. The foregoing elegant construction is due to the ancient geometer Philo of Byzantium. If we join DG, it will be perpendicular to F. The line F is called Philo's line. It possesses the remarkable property of being the minimum line through the point B between the fixed lines DF. Newton's construction: let AB and L be the two given lines of which AB is the greater. Bisect AB and C. With A as center and AC as radius, describe a circle, and in it place the chord CD equal to the second line L join BD, and draw by trial through a line meeting BD, CD produced in the points E, F, so that the intercept F will be equal to the radius of the circle. D and Fa are the mean proportionals required. Democrat: join AD. Since the line BF cuts the sides of the ACE, we have AB.CD.F equals CB.D.Fa, but F equals CB, therefore AB.CD equals D.Fa, or equals. Again, since the ACD is isosceles, we have ED.EC equals EA2AC2 equals, Fa plus AC, 2AC2 equals 2 Fa.AC plus Fa2 equals Fa.AB plus Fa2. Hence ed. ed plus cd, equals fa, ab plus fa, or d2 equals fa dot ab, therefore d2 equals fa dot ab, and we have ab dot cd equals d dot fa. Hence ab, d, fa, cd are in continued proportion. Underscore 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 note E on Philo's line. I am indebted to Professor Galbraith for the following proof of the minimum property of Philo's line. It is due to the late Professor McCulloch. Let AC, CB be two given lines, E a fixed point, CD a perpendicular on AB, it is required to prove, if AE is equal to DB, that AB is a minimum. Democrat through E draw M parallel to BC, make N equals M, produce AB until EP equals AB. Through the points N, P draw NT, RP each parallel to AC, and through P draw PQ parallel to BC. It is easy to see from the figure that the parallelogram QR is equal to the parallelogram MF, and is therefore given. Through P draw ST perpendicular to EP. Now, since AE equals DB, BP is equal to DB, therefore PS equals CD. Again, since OP equals AD, PT is equal to CD, therefore PS equals PT. Hence QR is the maximum parallelogram in the triangle SVT. Again, if any other line AB be drawn through E, and produced to P, so that EP equals AP, the point P must fall outside ST, because the parallelogram QR, corresponding to QR, will be equal to MF, and therefore equal to QR. Hence the line EP is greater than EP, or AB is greater than AB. Hence AB is a minimum. Underscore 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 note F on the trisection of an angle. The following mechanical method of trisecting an angle occurred to me several years ago. Apart from the interest belonging to the problem, it is valuable to the student as a geometrical exercise to trisect a given angle ACB. Solution: erect CD perpendicular to CA, bisect the angle BCD by CG, and make the angle ECI equal half a right angle. It is evident that CI will fall between CB and CA. Then, if we use a jointed ruler, that is two equal rulers connected by a pivot, and make CB equal to the length of one of these rulers, and, with C as center and CB as radius, describe the circle BAM, cutting CI in I, at I draw the tangent IG, cutting CG in G. Then, since ICG is half a right angle, and SIG is right, IGC is half a right angle, therefore IC is equal to IG, but IC equals CB, therefore IG equals CB equal length of one of the two equal rulers. Hence, if the rulers be opened out at right angles, and placed so that the pivot will be at I, and one extremity at C, the other extremity at G, it is evident that the point B will be between the two rulers. Then, while the extremity at C remains fixed, let the other be made to traverse the line GF, until the edge of the second ruler passes through B. It is plain that the pivot moves along the circumference of the circle. Let CH, HF, be the positions of the rulers when this happens. Draw the line CH, the angle ACH is 1/3 of ACB. Democrat produce BC to M, join HM, erect bow at right angles to BM. Then, because CH equals HF, the angle HCF equals HFC, and the angle DCE equals ECB, constant. Hence the angle HCD equals HBCIXXXII, and the right angles ACD, CBO are equal, therefore the angle ACH is equal to HBO, that is 3XXXII, equal to HMB, or to half the angle HCB. Hence ACH is 1/3 of ACB. underscore 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 note G on the quadrature of the circle. Modern mathematicians denote the ratio of the circumference of a circle to its diameter by the symbol pi. Hence, if r denote the radius, the circumference will be 2 pi r, and, since the area of a circle 6xx, ex 15 is equal to half the rectangle contained by the circumference and the radius, the area will be pi r2. Hence, if the area be known, the value of pi will be known, and, conversely, if the value of pi be known, the area is known. On this account the determination of the value of pi is called the problem of the quadrature of the circle, and is one of the most celebrated in mathematics. It is now known that the value of pi is incommensurable, that is, that it cannot be expressed as the ratio of any two whole numbers, and therefore that it can be found only approximately, but the approximation can be carried as far as we please, just as in extracting the square root we may proceed to as many decimal places as may be required. The simplest approximate value of pi was found by Archimedes, namely, 22.7. This value is tolerably exact, and is the one used in ordinary calculations, except where great accuracy is required. The next to this in ascending order, viz. 355, 113, found by Vita, is correct to 6 places of decimals. It differs very little from the ratio 3.1416, given in our elementary books. Several expeditious methods, depending on the higher mathematics, are known for calculating the value of pi. The following is an outline of a very simple elementary method for determining this important constant. It depends on a theorem which is at once inferred from 6, ex 87, namely if a denote the reciprocals of the areas of any two polygons of the same number of sides inscribed and circumscribed to a circle, a the corresponding quantities for polygons of twice the number, a is the geometric mean between a, and the arithmetic mean between a and a. Hence, if a and a be known, we can, by the processes of finding arithmetic and geometric means, find a and a. In like manner, from a we can find a related to a, as a r to a. Therefore, proceeding in this manner until we arrive at values n, that will agree in as many decimal places as there are in the degree of accuracy we wish to attain, and since the area of a circle is intermediate between the reciprocals of a, n, and a, n, the area of the circle can be found to any required degree of approximation. If for simplicity we take the radius of the circle to be unity, and commence with the inscribed and circumscribed squares, we have these numbers are found thus: a is the geometric mean between a and a, that is, between 0.5 and 0.25, and a is the arithmetic mean between a and a, or between 0.3535533 and 0.25. Again, a is the geometric mean between a, and a the arithmetic mean between a and a. Proceeding in this manner, we find a, 13, equals 0.31830099, a, 13, equals 0.31830099. Hence the area of a circle radius unity, correct to 7 decimal places, is equal to the reciprocal of 0.31830099, that is, equal to 3.1415926, or the value of pi correct to 7 places of decimals is 3.1415926. The number pi is of such fundamental importance in geometry, that mathematicians have devoted great attention to its calculation. Mr. Shanks, an English computer, carried the calculation to 707 places of decimals. The following are the first 36 figures of his result. The result is here carried far beyond all the requirements of mathematics. 10 decimals are sufficient to give the circumference of the Earth to the fraction of an inch, and 30 decimals would give the circumference of the whole visible universe to a quantity imperceptible with the most powerful microscope. Conclusion. In the foregoing treatise we have given the elementary geometry of the point, the line, and the circle, and figures formed by combinations of these. But it is important to the student to remark, that points and lines, instead of being distinct from, are limiting cases of, circles, and points and planes limiting cases of spheres. Thus, a circle whose radius diminishes to 0 becomes a point. If, on the contrary, the circle be continually enlarged, it may have its curvature so much diminished, that any portion of its circumference may be made to differ in as small a degree as we please from a right line, and become one when the radius becomes infinite. This happens when the center, but not the circumference, goes to infinity. The end. Third edition, revised and enlarged 3/6, cloth. _______ is sequel to the first 6 books of the Elements of Euclid. By John Casey, Doctor of Laws, F.R.S., Fellow of the Royal University of Ireland, Vice President, Royal Irish Academy, and CNC _____________________________________________ Dublin, Hodges, Figgis, and Co. London, Longmans, Green, and Co. Extracts from critical notices. Nature, April 17, 1884. We have noticed, Nature, Volume XXIV, p. 52, Volume XXVI, p. 219, 2 previous editions of this book, and are glad to find that our favorable opinion of it has been so convincingly endorsed by teachers and students in general. The novelty of this edition is a supplement of additional propositions and exercises. This contains an elegant mode of obtaining the circle tangential to 3 given circles by the methods of false positions, constructions for a quadrilateral, and a full account for the first time in a textbook of the Brocard, triplicate ratio, and, what the author proposes to call, the cosine circles. Dr. Casey has collected together very many properties of these circles, and, as usual with him, has added several beautiful results of his own. He has done excellent service in introducing the circles to the notice of English students. We only need say we hope that this edition may meet with as much acceptance as its predecessors. It deserves greater acceptance. The /Mathematical Magazine, Erie, Pennsylvania. Dr. Casey, an eminent professor of the higher mathematics and mathematical physics in the Catholic University of Ireland, has just brought out a second edition of his unique sequel to the first 6 books of Euclid, in which he has contrived to arrange and to pack more geometrical gems than have appeared in any single textbook since the days of the self-taught Thomas Simpson. The principles of modern geometry contained in the work are, in the present state of science, indispensable in pure and applied mathematics, and in mathematical physics, and it is important that the student should become early acquainted with them. 11 of the 16 sections into which the work is divided exhibit most excellent specimens of geometrical reasoning and research. These will be found to furnish very neat models for systematic methods of study. The other 5 sections contain 261 choice problems for solution. Here the earnest student will find all that he needs to bring himself abreast with the amazing developments that are being made almost daily in the vast regions of pure and applied geometry. On pages 152 and 153 there is an elegant solution of the celebrated Malfati's problem. As our space is limited, we earnestly advise every lover of the bright seraphic truth and every friend of the mathematical magazine to procure this invaluable book without delay. The /Schoolmaster. This book contains a large number of elementary geometrical propositions not given in Euclid, which are required by every student of mathematics. Here are such propositions as that the three bisectors of the sides of a triangle are concurrent, needed in determining the position of the center of gravity of a triangle, propositions in the circle needed in practical geometry and mechanics, properties of the centers of similitudes, and the theories of inversion and reciprocation so useful in certain electrical questions. The proofs are always neat, and in many cases exceedingly elegant. The /Educational Times. We have certainly seen nowhere so good an introduction to modern geometry, or so copious a collection of those elementary propositions not given by Euclid, but which are absolutely indispensable for every student who intends to proceed to the study of the higher mathematics. The style and general get-up of the book are, in every way, worthy of the Dublin University Press series, to which it belongs. The /School Guardian. This book is a well-devised and useful work. It consists of propositions supplementary to those of the first 6 books of Euclid, and a series of carefully arranged exercises which follow each section. More than half the book is devoted to the 6th book of Euclid, the chapters on the theory of inversion and on the poles and polars being especially good. Its method skillfully combines the methods of old and modern geometry, and a student well acquainted with its subject matter would be fairly equipped with the geometrical knowledge he would require for the study of any branch of physical science. The /Practical Teacher. Professor Casey's aim has been to collect within reasonable compass all those propositions of modern geometry to which reference is often made, but which are as yet embodied nowhere. We can unreservedly give the highest praise to the matter of the book. In most cases the proofs are extraordinarily neat, the notes to the 6th book are the most satisfactory. Feuerbach's theorem, the 9-point circle touches inscribed and escribed circles, is favored with 2 or 3 proofs, all of which are elegant. Dr. Hart's extension of it is extremely well proved. We shall have given sufficient commendation to the book when we say, that the proofs of these, Malfati's problem, and Miguel's theorem, and equally complex problems, which we used to shudder to attack, even by the powerful weapons of analysis, are easily and triumphantly accomplished by pure geometry. After showing what great results this book has accomplished in the minimum of space, it is almost superfluous to say more. Our author is almost alone in the field, and for the present need scarcely fear rivals. The /Academy. Dr. Casey is an accomplished geometer, and this little book is worthy of his reputation. It is well adapted for use in the higher forms of our schools. It is a good introduction to the larger works of Chasles, Salmon, and Townsend. It contains both a text and numerous examples. The /Journal of Education. Dr. Casey's sequel to Euclid will be found a most valuable work to any student who has thoroughly mastered Euclid, and imbibed a real taste for geometrical reasoning. The higher methods of pure geometrical demonstration, which form by far the larger and more important portion, are admirable. The propositions are for the most part extremely well given, and will amply repay a careful perusal to advanced students. Preface. Frequent applications having been made to Dr. Casey requesting him to publish a key containing the solutions of the exercises in his Elements of Euclid, but his professorial and other duties scarcely leaving him any time to devote to it, I undertook, under his direction, the task of preparing one. Every solution was examined and approved of by him before writing it for publication, so that the work may be regarded as virtually his. The exercises are a joint selection made by him and the late lamented Professor Townsend, SFTCD, and form one of the finest collections ever published. Joseph B. Casey. 86, South Circular Road, December 23, 1886. Price 4/6, post free. The first 6 books of the Elements of Euclid, with copious annotations and numerous exercises. By John Casey, Doctor of Laws, F.R.S., Fellow of the Royal University of Ireland, Vice President, Royal Irish Academy, and CNC underscore 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 Dublin, Hodges, Figgis, and Co. London, Longmans, Green, and Co. underscore 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 opinions of the work. The following are a few of the opinions received by Dr. Casey on this work. Teachers no longer need be at a loss when asked which of the numerous Euclids they recommend to learners. Dr. Casey's will, we presume, supersede all others. The Dublin Evening Mail. Dr. Casey's work is one of the best and most complete treatises on elementary geometry we have seen. The annotations on the several propositions are specially valuable to students. The Northern Whig. His long and successful experience as a teacher has eminently qualified Dr. Casey for the task which he has undertaken. We can unhesitatingly say that this is the best edition of Euclid that has been yet offered to the public. The Freeman's Journal. From the Reverend R. Townsend, FTCD, and C. I have no doubt whatever of the general adoption of your work through all the schools of Ireland immediately, and of England also before very long. From George Francis Fitzgerald, ESQ, FTCD. Your work on Euclid seems admirable, and is a great improvement in most ways on its predecessors. It is a great thing to call the attention of students to the innumerable variations in statement and simple deductions from propositions. I should have preferred some modification of Euclid to a reproduction, but I suppose people cannot be got to agree to any. From H. J. Cook, ESQ, The Academy, Banbridge. In the clearness, neatness, and variety of demonstrations, it is far superior to any textbook yet published, whilst the exercises are all that could be desired. From James A. Poole, M.A., 29, Harcourt Street, Dublin. This work proves that Irish scholars can produce class books which even the headmasters of English schools will feel it a duty to introduce into their establishments. From Professor Leabody, Magee College, Londonderry. So far as I have had time to examine it, it seems to me a very valuable addition to our textbooks of elementary geometry, and a most suitable introduction to the sequel to Euclid, which I have found an admirable book for class teaching. From Mrs. Bryant, FCP, Principal of the North London Collegiate School for Girls. I am heartily glad to welcome this work as a substitute for the much less elegant textbooks in vogue here. I have begun to use it already with some of my classes, and find that the arrangement of exercises after each proposition works admirably. From the Reverend J. E. Reff, French College, Blackrock. I am sure you will soon be obliged to prepare a second edition. I have ordered 50 copies more of the Euclid. This makes 250 copies for the French College. They all like the book here. From the Nottingham Guardian. The edition of the first 6 books of Euclid by Dr. John Casey is a particularly useful and able work. The illustrative exercises and problems are exceedingly numerous, and have been selected with great care. Dr. Casey has done an undoubted service to teachers in preparing an edition of Euclid adapted to the development of the geometry of the present day. From the Leeds Mercury. There is a simplicity and neatness of style in the solution of the problems which will be of great assistance to the students in mastering them. At the end of each proposition there is an examination paper upon it, with deductions and other propositions, by means of which the student is at once enabled to test himself whether he has fully grasped the principles involved. Dr. Casey brings at once the student face to face with the difficulties to be encountered, and trains him, stage by stage, to solve them. From the Practical Teacher. The preface states that this book is intended to supply a want much felt by teachers at the present day, the production of a work which, while giving the unrivaled original in all its integrity, would also contain the modern conceptions and developments of the portion of geometry over which the elements extend. The book is all, and more than all, it professes to be. The propositions suggested are such as will be found to have most important applications, and the methods of proof are both simple and elegant. We know no book which, within so moderate a compass, puts the student in possession of such valuable results. The exercises left for solution are such as will repay patient study, and those whose solution are given in the book itself will suggest the methods by which the others are to be demonstrated. We recommend everyone who wants good exercises in geometry to get the book, and study it for themselves. From the Educational Times. The editor has been very happy in some of the changes he has made. The combination of the general and particular enunciations of each proposition into one is good, and the shortening of the proofs, by omitting the repetitions so common in Euclid, is another improvement. The use of the contrapositive of a proved theorem is introduced with advantage, in place of the reductio ad absurdum, while the alternative, or, in some cases, substituted, proofs are numerous, many of them being not only elegant but eminently suggestive. The notes at the end of the book are of great interest, and much of the matter is not easily accessible. The collection of exercises, of which there are nearly 800, is another feature which will commend the book to teachers. To sum up, we think that this work ought to be read by every teacher of geometry, and we make bold to say that no one can study it without gaining valuable information, and still more valuable suggestions. From the Journal of Education, September 1, 1883. In the text of the propositions, the author has adhered, in all but a few instances, to the substance of Euclid's demonstrations, without, however, giving way to a slavish following of his occasional verbiage and redundance. The use of letters in brackets in the enunciations eludes the necessity of giving a second or particular enunciation, and can do no harm. Hints of other proofs are often given in small type at the end of a proposition, and, where necessary, short explanations. The definitions are also carefully annotated. The theory of proportion, Book V, is given in an algebraical form. This book has always appeared to us an exquisitely subtle example of Greek mathematical logic, but the subject can be made infinitely simpler and shorter by a little algebra, and naturally the more difficult method has yielded place to the less. It is not studied in schools, it is not asked for even in the Cambridge Tripos. A few years ago, it still survived in one of the college examinations at St. John's, but whether the reforming spirit which is dominant there has left it, we do not know. The book contains a very large body of writers and independent geometrical problems. The simpler of these are given in immediate connection with the propositions to which they naturally attach, the more difficult are given in collections at the end of each book. Some of these are solved in the book, and these include many well-known theorems, properties of orthocenter, of nine-point circle, and c. In every way this edition of Euclid is deserving of commendation. We would also express a hope that everyone who uses this book will afterwards read the same author's sequel to Euclid, where he will find an excellent account of more modern geometry. Underscore 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 now ready, price 6s, a key to the exercises in the elements of Euclid. Typographical errors corrected in Project Gutenberg edition p. DEF 8 when a right line intersects, in original, amended to DEF 7 in sequence. p. 12 bisects the parallelogram in original, amended to match every other occurrence as parallelogram. p. ACH is half the rectangle AC.A, ICOR1, in original. The reference is to PROPI of the current book and misnumbered, it should be, ICOR2. P. The parallelogram CM is equal to diislyene, COR3, in original, amended to COR2 following miscorrection, there is no COR3. P. On CB describe the square CBEF islv. In original, clearly meant to read islv. P. The remaining parts of the line in original, obvious error amended to remaining. P. That which is nearest to the line through the center in original, obvious error amended to through. P. Then this line COR1 in original. The reference is to PROPI of the current book, so it should be COR1. P. OA is equal to OCI, DEFXXII in original. The reference should be DEFXXXII. P. The 4 points A, C, D, B are concyclic in original, evidently intended is concyclic. P. As P. P. Through though point E in original, obvious error amended to the P. Dot. P. The points A, B, C, D are concyclic in original, as P. P. EX2, or touching a given file and a given circle in original, obvious error amended to touching. P. 21 What is the locus of the middle points, in original, amended to 31 in sequence. P. In 21, the if-then line to intersect the chords, in original, garbled phrase amended to then if the. P. In 44, these circles intersect in original, misplaced space amended to these circles intersect. P. For the point of bisection, 1, of the line, op, in original, from the diagram and following discussion this should be, I. P. PROP9. About a given circle, ABCD, to describe a circle in original, clearly this is nonsense and must mean about a given square. P. Then the triangles ABO, CBO in original, obvious error amended to triangles. P. In 52, and also an equilateral circumscribed polygon in original, wrong letter amended to an. P. Heading prop. XXV problem in original, the preamble to this book says that every proposition in it is a theorem and this one seems to be no exception, so amended. P. Reference I is to proposition I of current book, amended to I. 4 times. P. SQQ. Reference 2 is to proposition 2. Of current book, amended to 2. 4 times. P. Prop V header subtended BG the homologous sides in original, obvious error amended to by. P. Reference 16 corrected to 16. P. From the construction is evident, in original, obvious error amended to it is. P. 20 Find a point O in original, obvious error amended to point. P. The lines GH, GK each perpendicular to F in original, obvious error amended to perpendicular. P. O when associated with a lowercase letter was wrongly printed as O, which is not defined. These have been corrected, 3 times. P. Reference 6, COR6 corrected to 6, COR6. End of the Project Gutenberg ebook. The first 6 books of the Elements of Euclid updated editions will replace the previous one. The old editions will be renamed. Creating the works from print editions not protected by U.S. copyright law means that no one owns a United States copyright in these works, so the Foundation, and you, can copy and distribute it in the United States without permission and without paying copyright royalties. Special rules, set forth in the general terms of use part of this license, apply to copying and distributing Project Gutenberg trademark electronic works to protect the Project Gutenberg trademark concept and trademark. Project Gutenberg is a registered trademark, and may not be used if you charge for an ebook, except by following the terms of the trademark license, including paying royalties for use of the Project Gutenberg trademark. If you do not charge anything for copies of this ebook, complying with the trademark license is very easy. You may use this ebook for nearly any purpose such as creation of derivative works, reports, performances, and research. Project Gutenberg ebooks may be modified and printed and given away. You may do practically anything in the United States with ebooks not protected by U.S. copyright law. Redistribution is subject to the trademark license, especially commercial redistribution. Start, full license. The full Project Gutenberg license. Please read this before you distribute or use this work to protect the Project Gutenberg trademark mission of promoting the free distribution of electronic works, by using or distributing this work, or any other work associated in any way with the phrase Project Gutenberg. You agree to comply with all the terms of the full Project Gutenberg trademark license available with this file or online at www.gutenberg.org/license. Section 1. General Terms of Use and Redistributing Project Gutenberg Trademark Electronic Works 1.a. By reading or using any part of this Project Gutenberg trademark electronic work, you indicate that you have read, understand, agree to and accept all the terms of this license and intellectual property, trademark/copyright, agreement. If you do not agree to abide by all the terms of this agreement, you must cease using and return or destroy all copies of Project Gutenberg trademark electronic works in your possession. If you paid a fee for obtaining a copy of or access to a Project Gutenberg trademark electronic work and you do not agree to be bound by the terms of this agreement, you may obtain a refund from the person or entity to whom you paid the fee as set forth in paragraph 1.e.8. 1.b. Project Gutenberg is a registered trademark. It may only be used on or associated in any way with an electronic work by people who agree to be bound by the terms of this agreement. There are a few things that you can do with most Project Gutenberg trademark electronic works even without complying with the full terms of this agreement. See paragraph 1.c below. There are a lot of things you can do with Project Gutenberg trademark electronic works if you follow the terms of this agreement and help preserve free future access to Project Gutenberg trademark electronic works. See paragraph 1.e below. 1.c. The Project Gutenberg Literary Archive Foundation, the Foundation or PGLOF, owns a compilation copyright in the collection of Project Gutenberg trademark electronic works. Nearly all the individual works in the collection are in the public domain in the United States. If an individual work is unprotected by copyright law in the United States and you are located in the United States, we do not claim a right to prevent you from copying, distributing, performing, displaying, or creating derivative works based on the work as long as all references to Project Gutenberg are removed. Of course, we hope that you will support the Project Gutenberg trademark mission of promoting free access to electronic works by freely sharing Project Gutenberg trademark works in compliance with the terms of this agreement for keeping the Project Gutenberg trademark name associated with the work. You can easily comply with the terms of this agreement by keeping this work in the same format with its attached full Project Gutenberg trademark license when you share it without charge with others. 1.d. The copyright laws of the place where you are located also govern what you can do with this work. Copyright laws in most countries are in a constant state of change. If you are outside the United States, check the laws of your country in addition to the terms of this agreement before downloading, copying, displaying, performing, distributing or creating derivative works based on this work or any other Project Gutenberg trademark work. The Foundation makes no representations concerning the copyright status of any work in any country other than the United States. 1.e Unless you have removed all references to Project Gutenberg, 1.e.1. The following sentence, with active links to, or other immediate access to, the full Project Gutenberg trademark license must appear prominently whenever any copy of a Project Gutenberg trademark work, any work on which the phrase Project Gutenberg appears, or with which the phrase Project Gutenberg is associated, is accessed, displayed, performed, viewed, copied or distributed. This ebook is for the use of anyone anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. You may copy it, give it away or reuse it under the terms of the Project Gutenberg license included with this ebook or online at www.gutenberg.org. If you are not located in the United States, you will have to check the laws of the country where you are located before using this ebook. 1.e.2. If an individual Project Gutenberg trademark electronic work is derived from texts not protected by U.S. copyright law, does not contain a notice indicating that it is posted with permission of the copyright holder, the work can be copied and distributed to anyone in the United States without paying any fees or charges. If you are redistributing or providing access to a work with the phrase Project Gutenberg associated with or appearing on the work, you must comply either with the requirements of paragraphs 1.e.1 through 1.e.7 or obtain permission for the use of the work and the Project Gutenberg trademark as set forth in paragraphs 1.e.8 or 1.e.9. 1.e.3. If an individual Project Gutenberg trademark electronic work is posted with the permission of the copyright holder, your use and distribution must comply with both paragraphs 1.e.1 through 1.e.7 and any additional terms imposed by the copyright holder. Additional terms will be linked to the Project Gutenberg trademark license for all works posted with the permission of the copyright holder found at the beginning of this work. 1.e.4. Do not unlink or detach or remove the full Project Gutenberg trademark license terms from this work, or any files containing a part of this work or any other work associated with Project Gutenberg trademark. 1.e.5. Do not copy, display, perform, distribute or redistribute this electronic work, or any part of this electronic work, without prominently displaying the sentence set forth in paragraph 1.e.1 with active links or immediate access to the full terms of the Project Gutenberg trademark license. 1.e.6. You may convert to and distribute this work in any binary, compressed, marked up, non-proprietary or proprietary form, including any word processing or hypertext form. However, if you provide access to or distribute copies of a Project Gutenberg trademark work in a format other than plain vanilla ASCII or other format used in the official version posted on the official Project Gutenberg trademark website, www.gutenberg.org, you must, at no additional cost, fee, or expense to the user, provide a copy, a means of exporting a copy, or a means of obtaining a copy upon request, of the work in its original plain vanilla ASCII or other form. Any alternate format must include the full Project Gutenberg trademark license as specified in paragraph 1.e.1. 1.e.7. Do not charge a fee for access to, viewing, displaying, performing, copying or distributing any Project Gutenberg trademark works unless you comply with paragraph 1.e.8 or 1.e.9. 1.e.8. You may charge a reasonable fee for copies of or providing access to or distributing Project Gutenberg trademark electronic works provided that, you pay a royalty fee of 20% of the gross profits you derive from the use of Project Gutenberg trademark works calculated using the method you already use to calculate your applicable taxes. The fee is owed to the owner of the Project Gutenberg trademark, but he has agreed to donate royalties under this paragraph to the Project Gutenberg Literary Archive Foundation. Royalty payments must be paid within 60 days following each date on which you prepare, or are legally required to prepare, your periodic tax returns. Royalty payments should be clearly marked as such and sent to the Project Gutenberg Literary Archive Foundation at the address specified in Section 4, Information about donations to the Project Gutenberg Literary Archive Foundation. You provide a full refund of any money paid by a user who notifies you in writing, or by email, within 30 days of receipt that he does not agree to the terms of the full Project Gutenberg trademark license. You must require such a user to return or destroy all copies of the works possessed in a physical medium and discontinue all use of and all access to other copies of Project Gutenberg trademark works. You provide, in accordance with paragraph 1.f.3, a full refund of any money paid for a work or a replacement copy, if a defect in the electronic work is discovered and reported to you within 90 days of receipt of the work. You comply with all other terms of this agreement for free distribution of Project Gutenberg trademark works. 1.e.9. If you wish to charge a fee or distribute a Project Gutenberg trademark electronic work or group of works on different terms than are set forth in this agreement, you must obtain permission in writing from the Project Gutenberg Literary Archive Foundation, the manager of the Project Gutenberg trademark. Contact the Foundation as set forth in Section 3 below. 1.f.1.f.1. Project Gutenberg volunteers and employees expend considerable effort to identify, do copyright research on, transcribe and proofread works not protected by U.S. copyright law in creating the Project Gutenberg trademark collection. Despite these efforts, Project Gutenberg trademark electronic works, and the medium on which they may be stored, may contain defects, such as, but not limited to, incomplete, inaccurate or corrupt data, transcription errors, a copyright or other intellectual property infringement, a defective or damaged disk or other medium, a computer virus, or computer codes that damage or cannot be read by your equipment. 1.f.2. Limited warranty, disclaimer of damages, except for the right of replacement or refund described in paragraph 1.f.3, the Project Gutenberg Literary Archive Foundation, the owner of the Project Gutenberg trademark, and any other party distributing a Project Gutenberg trademark electronic work under this agreement, disclaim all liability to you for damages, costs, and expenses, including legal fees. You agree that you have no remedies for negligence, strict liability, breach of warranty or breach of contract except those provided in paragraph 1.f.3. You agree that the Foundation, the trademark owner, and any distributor under this agreement will not be liable to you for actual, direct, indirect, consequential, punitive, or incidental damages even if you give notice of the possibility of such damage. 1.f.3. Limited right of replacement or refund. If you discover a defect in this electronic work within 90 days of receiving it, you can receive a refund of the money, if any, you paid for it by sending a written explanation to the person you received the work from. If you received the work on a physical medium, you must return the medium with your written explanation. The person or entity that provided you with the defective work may elect to provide a replacement copy in lieu of a refund. If you received the work electronically, the person or entity providing it to you may choose to give you a second opportunity to receive the work electronically in lieu of a refund. If the second copy is also defective, you may demand a refund in writing without further opportunities to fix the problem. 1.f.4. Except for the limited right of replacement or refund set forth in paragraph 1.f.3, this work is provided to you as is, with no other warranties of any kind, express or implied, including but not limited to warranties of merchantability or fitness for any purpose.
1.f.5. Some states do not allow disclaimers of certain implied warranties or the exclusion or limitation of certain types of damages. If any disclaimer or limitation set forth in this agreement violates the law of the state applicable to this agreement, the agreement shall be interpreted to make the maximum disclaimer or limitation permitted by the applicable state law. The invalidity or unenforceability of any provision of this agreement shall not void the remaining provisions. 1.f.6. Indemnity. You agree to indemnify and hold the foundation, the trademark owner, any agent or employee of the foundation, anyone providing copies of Project Gutenberg trademark electronic works in accordance with this agreement, and any volunteers associated with the production, promotion, and distribution of Project Gutenberg trademark electronic works, harmless from all liability, costs, and expenses, including legal fees, that arise directly or indirectly from any of the following which you do or cause to occur. A. Distribution of this or any Project Gutenberg trademark work. B. Alteration, modification, or additions or deletions to any Project Gutenberg trademark work, and C. Any defect you cause. Section 2. Information about the mission of Project Gutenberg trademark. Project Gutenberg trademark is synonymous with the free distribution of electronic works in formats readable by the widest variety of computers, including obsolete, old, middle-aged, and new computers. It exists because of the efforts of hundreds of volunteers and donations from people in all walks of life. Volunteers and financial support to provide volunteers with the assistance they need are critical to reaching Project Gutenberg trademark's goals and ensuring that the Project Gutenberg trademark collection will remain freely available for generations to come. In 2001, the Project Gutenberg Literary Archive Foundation was created to provide a secure and permanent future for Project Gutenberg trademark and future generations. To learn more about the Project Gutenberg Literary Archive Foundation and how your efforts and donations can help, see sections 3 and 4 and the Foundation information page at www.gutenberg.org. Section 3. Information about the Project Gutenberg Literary Archive Foundation. The Project Gutenberg Literary Archive Foundation is a nonprofit 501(c)(3) educational corporation organized under the laws of the state of Mississippi and granted tax-exempt status by the Internal Revenue Service. The Foundation's IN or Federal Tax Identification Number is 64-6221541. Contributions to the Project Gutenberg Literary Archive Foundation are tax-deductible to the full extent permitted by U.S. federal laws and your state's laws. The Foundation's business office is located at 809 North 1500 West, Salt Lake City, Utah 841-16801-596-1887. Email contact links and up-to-date contact information can be found at the Foundation's website and official page at www.gutenberg.org/contact. Section 4. Information about donations to the Project Gutenberg Literary Archive Foundation. Project Gutenberg trademark depends upon and cannot survive without widespread public support and donations to carry out its mission of increasing the number of public domain and licensed works that can be freely distributed in machine-readable form accessible by the widest array of equipment, including outdated equipment. Many small donations, $1 to $5,000, are particularly important to maintaining tax-exempt status with the IRS. The Foundation is committed to complying with the laws regulating charities and charitable donations in all 50 states of the United States. Compliance requirements are not uniform and it takes a considerable effort, much paperwork, and many fees to meet and keep up with these requirements. We do not solicit donations in locations where we have not received written confirmation of compliance. To send donations or determine the status of compliance for any particular state, visit www.gutenberg.org/donate.
While we cannot and do not solicit contributions from states where we have not met the solicitation requirements, we know of no prohibition against accepting unsolicited donations from donors in such states who approach us with offers to donate. International donations are gratefully accepted, but we cannot make any statements concerning tax treatment of donations received from outside the United States. U.S. laws alone swamp our small staff. Please check the Project Gutenberg web pages for current donation methods and addresses. Donations are accepted in a number of other ways, including checks, online payments, and credit card donations. To donate, please visit www.gutenberg.org/donate. Section 5. General information about Project Gutenberg trademark electronic works. Professor Michael S. Hart was the originator of the Project Gutenberg trademark concept of a library of electronic works that could be freely shared with anyone. For 40 years, he produced and distributed Project Gutenberg trademark ebooks with only a loose network of volunteer support. Project Gutenberg trademark ebooks are often created from several printed editions, all of which are confirmed as not protected by copyright in the U.S. unless a copyright notice is included. Thus, we do not necessarily keep ebooks in compliance with any particular paper edition. Most people start at our website, which has the main PG search facility, www.gutenberg.org. This website includes information about Project Gutenberg trademark, including how to make donations to the Project Gutenberg Literary Archive Foundation, how to help produce our new ebooks, and how to subscribe to our email newsletter to hear about new ebooks. The first 6 books of the Elements of Euclid, and Propositions IXXI. Of Book 11, and an appendix on the cylinder, sphere, cone, etc. with copious annotations and numerous exercises. Preface. Contents. Introduction. Book I. Theory of angles, triangles, parallel lines, and parallelograms. Book 2. Theory of rectangles. Book 3. Theory of the circle. Book 4. Inscription and circumscription of triangles and of regular polygons in and about circles. Book V. Theory of proportion. Book 6. Application of the theory of proportion. Book 11. Theory of planes, coplanar lines, and solid angles. The full Project Gutenberg license.